Professor Shaofu here. Okay, here I talk about the phonemic absorption, dark matter, and the neutrinos. Okay, let's welcome.
，slide 是好。Okay, first, thank you so much for having this chance to introduce my recent works on this phonemic absorption dark matter. So initially, actually, I wanted to prepare a brand new talk, but unfortunately, I didn't have enough time. So finally, I would mention something related to the neutrino detection. So the major contents has been summarized in these papers with my collaborators here. So the basic idea for this absorption dark matter is to overcome the detection threshold in dark matter search. So because of this threshold, typically in this light mass region, it's not that well constrained. So one possible way to boost the recoil is for this elastic scattering with a light target like electron. Or we can think about this exothermic dark matter. Part of the dark matter mass would be released from the heavier state to a lighter state, and use this to get larger energy recoil. And for this scenario, it requires two different dark particles, right? Dark sector particles. So that's not that minimal. So why don't we just go to the extreme? Replace the final state dark sector particle with this neutrino. Then all the dark matter mass would be released. So that's the basic idea. Then in this scenario, all the dark matter mass would be absorbed and converted to energy. That's the reason why we call it absorption scenario. This idea actually for the bosonic already been studied quite a lot. For example, dark photon or axion search. So there are several processes. One is this dark photoelectric effect. This dark particle fully absorbed it, and its energy would convert to the electron energy, or dark Compton, or inverse Primakov. Either electron or photon, they are absorbable energies. But for the phonemic case, it seems like it's new, but it has actually a very long history. If we trace to the neutrino search in the 40s, Gan Changwang proposed using this K-shell electron capture to probe a neutrino. So in his scenario, the basic process is this innermost shell electron would combine with the nuclei. And this effectively converts one proton inside the nuclei to a neutron. And then this becomes a neutrino in final state. So you can see, basically the electron mass would get absorbed, become almost a massless neutrino. And then this released energy would cause this nuclei to have one energetic recoil. And this signal is very unique, it's delta function. But unfortunately, at that time, the precision is not good enough. Even nowadays, it's very difficult. It's just a kV scale nuclear recoil. Since now we already know neutrino, we can use this to probe dark matter. One example is using this electron target. This process intrinsically is at low energy scale. So we can use EFT to study the phenomenological consequence. In principle, we have like 4 fermions involved. So we can write 5 independent operators. This is a scalar type, pseudo scalar, vector, axial vector, and also this tensor. And similar as the one Gan Changwang proposed, it's also kind of like monoenergetic. If the electron is at rest, then effectively the whole system is at rest. Because for the dark matter, although it's moving, but the velocity is very low. It's 10 to minus 3 velocity. But the electron is inside the atom. Right? The initial electron and also the final states, they would be affected by the positively charged nuclei. So we need to consider the non-prime wave electron wave function. And this would cause this monoenergetic coil to have some spread. It becomes a peak, but still the feature is very unique. The peak shape is determined by the atomic effect. So this kind of feature, one thing is it can be used to suppress the background. It's very easy to identify a tiny signal. Another thing is once we see the signal, actually we can use this thing to tell it's really is absorption on the electron target. So this is a very, very unique signal. I would skip these details. The atomic effect would be summarized into this K factor, we call it K factor effect. The calculation, we have this, actually, this is a very rough calculation. Currently, we are still working on this to the relativistic limit. Here, I just show these atomic effect. The effect actually is quite sizable. It can be as large as like 30%. So this is the ratio between the case with bound electron and the free electron. Okay, so let me skip these details. Then in our first paper, we used the Panax2 data to find, to fit the signal to see what's the preferred parameter space. In that data, you can see it has a little bump here. This place indicates that it prefers dark matter mass around like 100 keV. So you can see this mass is really very tiny. It's way below the GeV scale. So without changing the detector, we can detect very light dark matter. And later, Panax4 Tang used, they did this real analysis for this signal. And what the data prefer is around here. That's the, how to say, this is not a kind of like a discovery because we haven't seen these access yet. So this is just to give some constraint. And several years ago, there was this C1 Tang, this access around 2 to 3 keV. SAS prefers this regime. Anyway, both Panax and CDX actually used the data to give constraint on this signal. And for this scenario, actually, we can get a lot of constraints from, for example, cosmology and astrophysics. Cosmological side, we need to first consider the production, the dark matter direct density. It cannot produce too much. So from the overproduction, actually, we can get some limits on the cutoff scale. And another thing is this kind of dark matter, since it couple with neutrino and 2 electron fields, in principle, it can allow decay. If we close the electron loop, it can either decay to 1 neutrino plus 1 photon, 2 photons, 3 photons, or it decays to 3 neutrinos. All these particles are light. So dark matter would kind of like decay, but it depends on the operator. Different operator would have different major decay channels. For example, this S would mainly allow these 2 photon final states. And then observationally, we can use X-ray or gamma ray signal to get a constraint. For the sub-MU wave, it's mainly X-ray signal. For this X-ray signal, we need to consider 2 sources. One is inside our galaxy. That one does not have any redshift. And another contribution comes from in the whole universe. So that's very far away, so we need to consider the redshift. So I want to emphasize here that usually people use higher energy observation data to get a constraint, but actually at the low energy, the InSight HXMT, that's one telescope in China, actually it can get very, very strong constraint at the low energy range. That's below 10 keV. That's this curve. So if you consider all these, these data, actually we need to deal with different cases. For example, if it's 2-body final state, we need to consider this monoenergetic gamma signal. That one has a lot of spikes. For the 3-body or even 4-body decay, that would give us a continuous spectrum. That constraint is more smooth. So we combine all these constraints into this single figure. So you can see for some cases, actually the decay is very strong. For example, this tensor operator, it's mainly induces the 2-body decay process. Almost all the parameter space has already been excluded. But for some cases, like the vector type, it's still okay. So this is a 4-body final state. And even we consider the overproduction, we still have a large parameter space scale. And this part is sensitive at direct detection experiments. And later we also consider this operator, how it can be searched at future left-hand quadrants, for example, CPC. Naively thinking, for at left-hand quadrant, actually the mass would be important. So finally, it wouldn't be that sensitive for light mass range. But if we compare with the direct one, actually you can see even at future left-hand quadrants, actually it's quite sensitive for very tiny dark matter mass. And this is for the electron target. We can also consider the absorption on the nuclear target. And for that one, although the nuclear is much more massive, but still it can extend the sensitive regime to like below GeV, around like 10, above 10 MeV or 100 MeV is scale. And usually experimental search currently we only consider this coherent scattering. For coherence, it also induces these 2-body final states. So that's monoenergetic. And our recent study goes into the incoherent regime. Because for this kind of process, the momentum transfer actually is not small. It's uniquely determined by the dark matter mass. This Q is around M high. And as I mentioned that for this absorption on the nuclear target, the mass is typically at the tens of MeV. So this momentum transfer actually is quite large. It's already in the incoherent regime. You can see individual nucleons. We need to consider this kind of contribution. And then we just make a naive estimation to treat these nucleons as Fermi gas and try to see what's the effect. So this is a predicted event spectrum. So you can see it's no longer monoenergetic. It can have very wide spread for the required energy. And not just these Fermi motions, the form factor now also enters. And then for the coherent one, we just use this F square, form factor square. For example, the Helm form factor. For the incoherent one, as an approximation, we just use the 1 minus F square. And for lighter dark matter, the coherent contribution would dominate. But around like 100 MeV, the incoherent one would becomes more important. It would go beyond the incoherent contributions. That's these 2 flat curves. And we should also incorporate more details, for example, the polar blocking effect. And we also try to compare between these different elements. You can see for these, I think, heavier elements, actually this one is highly suppressed. So the major feature still around like 100 MeV, the incoherent contribution would becomes dominant. And this is the combined sensitivity. If you only consider the coherent contribution, for example, if it's spin independent, then it's this black curve. And it has this kind of spike structure. And for spin dependent one, it's a little bit worse, but the basic feature is there. Unfortunately, if you consider this incoherent contribution, it's completely changed. For the spin independent one, it mainly deviates from here. And for the spin-dependent one, actually its change is much larger. So you can see it differs by several orders. So this incoherent contribution has to be considered for this dark matter absorption search. And at collider, we can also try to see how to search these at hadron colliders like HC. So basically similar to the electron collider case, at a low energy, actually they would dominate the sensitivity. And finally, I would mention our ongoing work on this neutrino signal. So existing searches mainly focus on the direct detection. So that's the energy deposit directly in the detector. Sometimes some neutrino detector, but the neutrino, actually we can observe it. And the feature is also very, very unique. That neutrino energy is fixed by the dark matter mass. It is also kind of like a monoenergetic signal. And it's largely independent of the target nuclei. So doesn't matter what kind of target, you get almost the same energy. So the dark matter comes in, it would get absorbed in the whole Earth, for example. And the Earth is a huge target. That can produce very large neutrino flux. And these monoenergetic neutrino flux, actually experimentally, we can identify them. So this plot shows the neutrino production rate inside our Earth every second. Roughly like 10 to 20 neutrinos can be produced if the cutoff scale is at 1 TeV. And you can see due to the form factors of the effects, the largest flux appears for these dark mass around tens of MeV, 60 or so. And this energy range is exactly in the detection energy range, for example, at Juno. And they can use inverse beta decay to uniquely identify such neutrinos. So the plot on the right-hand side, we show the event rate at hyper K. We use these to estimate whether it's sizable or not. So the signal here we consider several sources. One is the Earth, another one is the Sun, and even Moon. So seems like the Sun is much larger, right? And it can produce even more neutrinos, but those arriving at Earth actually is highly diluted because of the distance. The background mainly comes from atmospheric and diffused supernova backgrounds. But these backgrounds, they are continuous. They are not kind of like monoenergetic. So it's possible to distinguish them. And for this measurement, as I emphasized, the inverse beta decay can reconstruct the energy. It's kind of like, how to say, one-to-one correspondence. The final state charged lepton would have exactly the same energy as the incoming neutrino. This is a very important feature at reactor neutrino experiments like Darby and Juno. For higher energy, it's roughly okay with some spread, but still it's a very unique feature. The background is kind of like a flat, but for signal, it would focus in a very narrow energy range. So we just need to cut the energy and try to select, use this shape to distinguish from the background. The final plot shows the sensitivity. So here we list the sensitivities at neutrino experiments, hyper K, super K, Juno, and Borzino. And you see to compare with the existing constraints at direct detection experiments. So in some mass ranges, the direct detection actually can do better. For example, Panax photon is very good in this range. But some energy range, for example, below like around 30 MeV, it wouldn't generate large enough nuclear recoil. So even for very low threshold dark matter direction experiment, actually it cannot get this sensitivity below 30 MeV. So in this regime, the neutrino experiments can actually do a better job here. And even for higher mass, That one would generate too large nuclear recoil. Actually, that's not good at direct detection experiments. And that part, usually people would just call it off kill. So wouldn't select events there. In these regimes, neutrino experiments also provides better sensitivity. There is already some constraint from some experiment like Maulana, but in this part, the sensitivity is not that good. This spike is because of the form factor. In some regimes, the form factor almost vanish. So this is work still ongoing. So probably would appear this month. So I didn't prepare too many details. So that's just a rough idea. Okay, so that's really my talk. The basic idea is we want to extend the sensitivity of existing experiments without changing it. So this absorption signal is one example. So the people don't need to change the detector at all, just try to find this unique signature. And in this process, for this process, we need to consider the atomic effects. And even for the nuclear targets, similar thing is the incoherent scattering, the forming motion of nucleons inside the nuclei. So that's actually essentially is kind of like a bonding effect, the atomic effect. And we need to consider decaying dark matter constraints from the astral and the cosmos observations, and the complementary searches from collider and the neutrino experiments. Okay, thanks.
Okay, thank you. Any question or comments? Yeah, Anna.
Okay, thank you for the nice talk. So yeah, although I'm late, but I was online. So yeah, I have a question. So the operator roll down is actually not gating environment, right? Because they only write down just like in the jazz talk before, right? So if you consider left-handed neutrino, it's actually in a doublet. So, if we have this kind of interaction, or we have 3 electrons with a dark matter interaction.
So model building side, there are some models actually. So one is like using Z prime. It can induce this kind of effective operator.
Yeah, you introduce a 3 electron with a dark matter interaction, right? And then you in the collider you can electron collider you can produce a mono electron signal with a dark matter, but it is a tree-level effect.
Currently, it's still, how to say, still okay, because using effective operator, the lambda from the direct detection is kind of like 1 TeV.
Yeah, I mean, even for 1 TeV,
it's just like 250 GeV. At left-hand collider, it's still okay.
That's still okay. Okay.
Any other question or comments? Okay, I have one. I wonder, when you consider the EFT operators, why you consider the operator related to the neutrinos? Can we consider other operators?
For neutrino actually we use the vector type as an example in order to compare with the direct detection searches.
Okay.
Yeah, direct detection is mainly use a vector type operator.
Okay, any other question? Okay, let's thank Professor Shaofeng again. Okay, thank you. The schedule for our next talk is changed yesterday. So this talk will given by Wei from Nanjing University. Let's welcome.
Okay, first I want to thank Solarizer for the invitation. So I have this opportunity to present you our 2 recent papers on dark matter study at the electron colliders. So I'm going to tell you to this form. Okay, so two studies on electron colliders. So in the first one, we propose a new diameter certain channel at electron colliders. So we focus on belt 2. In the second paper, we study belt 2 constraints on this so-called strongly interacting diameter. So these studies are carried out on belt 2, but it can certainly extend to other electron colliders, including CPC and future FCC. Okay, so the first one, new dark matter channels at belt 2. Okay, so dark matter has been studied extensively at colliders. So the typical strategy is to produce the dark matter, the primary vortex. So, but dark matter are invisible to particle colliders. So one has to add something visible. So the typical strategy is just to add a single SM particle in the final stage for the detection. So then use the energy momentum conservation to infer there's presence dark matter. So over the years, there are many channels for this kind of study. So here are at least some so-called mono X channels. So in our new channel, we do not produce dark matter at the primary interaction vortex. So instead, we only produce SM particles. So for the electron collider, we have electron-positron annihilation to a pair of SM particles. One of these SM particles will interact with the particle detectors to produce dark matter in the detectors. So this is actually, so if you're familiar with the fixed target experiments, so this is actually a fixed target experiments inside the particle collider. So this particle detector serve as both as a target and a detector. Okay, so as I said before, I'm going to focus on the belt 2 detector. So this is the top view of the belt 2 detector. It's a detector with the electron-positron collision. It's a asymmetric detector. The electron is 7 GeV and the positron is 4 GeV. So you can see there's the detector is asymmetric. So there are many sub-detectors of these belt 2 experiments. For our study, we mainly use the 3 of these detectors, the so-called CDC, the tracker, the central tracker, and the ECL, this is the calorimeter, and the KLM, the K-long and muon detector. Okay, so this is the transverse view of this belt 2 detector. As I said before, there's CDC, ECL, and KLM. Okay, so I'm going to use this simple process to produce first the SM particles, so electron-positron annihilation into a pair of electron-positron final stage. So the electron in the final stage will be fully measured by the detector, which means the electron deposits all its energy to the calorimeter. On the other hand, the positron will interact with the calorimeter. So the calorimeter is the ECL to produce a pair of dark matter. And then the pair of dark matter will just escape this detector, leading to missing energy. Okay, so this is actually a disappearing positron track. So I know there's some disappearing track study in the Large Hadron Collider. So this is similar to that kind of studies. Okay, so this is the basic topology of this channel, the dark matter. So let's take a closer look at this this channel. So first in the central detector, the tracker, so the CDC, both the electron positron can be measured very precisely because the CDC has a very nice resolution. So the for example, if the transverse momentum is 3 GeV, the momentum resolution is about 0.4%. So one can measure the electron positron momentum in the tracker, and so for the 2-to-2 process, after the measurement, we might expect to see equal and opposite momentum of the electron positron pair in the center mass frame. Okay, I said before because the Bell 2 is asymmetric, the center mass frame is not the same as the lab frame. So, but you have to work in the center mass frame, so find these two final states are equal and opposite momentum. Okay, next the positron will lose only a small fraction of energy to the calorimeter. Most of the energy will escape the experiments. Okay, so in our study, we require that only 5% of positron energy is actually deposited in the calorimeter. 95% energy will carried away by the pair, the dark matter pair. Okay, so the detector, the target we use are as I said before, the calorimeter, but the calorimeter at the Bell 2 have 3 segments, the so-called Bell region and the 2 end caps. So we only use the Bell region because the Bell region has some nice properties which can enhance the sensitivity. For example, it has a better hermeticity, and it has less non-instrumented setups, including some magnetic wires and etc. It also has a smaller beam-induced background. Okay. So for the barrel region, there are about 6 times 10 to 11 events from the Barbar scattering. So I'm going to use this Barbar events to produce dark matter at the Bell 2 at the calorimeter. Okay, so that's the basic idea. So next I'm going to tell you about the background. Okay, the background is very similar to the signal process. One just changed the pair dark matter to SM particles, and this SM particle is supposed to carry away the same energy as the dark matter outside the detector, right? Okay, so they are charged SM particles and they are neutron SM particles. So for charged particles, it's unlikely to be undetected to escape the detector. So we don't consider charged particles in our study. So we only consider neutron particles, including neutron, photon, and electrons. A quick estimate, we find that the neutron background is very small, right? Just a small cross section. So we only consider neutrons. Neutrinos is small. So we only consider neutron and photon induced background. So in other words, we will try to find the energetic neutron and photon produced in this collision between the positron and the detector. So first, the photon-induced background. So we use this analytic formula to compute the photon spectrum at the end of the ECL detector. And here the X is the energy ratio, the photon to the incident electron energy. In this case, is a positron. Sorry. So T is the number of radiation length. And the ECL has 16 radiation length. So we use this number, put into this analytic formula. We can find that the high energy photon, the high energy means there's 95% energy carried by this photon. So the probability is actually pretty small. Is roughly 5 times 10 to minus 8. Okay, so multiplied by this larger number, 10 to 11 bar events, we get like 28,000 high energy photons at the end of this calorimeter. So these are the potential dangerous SM events, right? These high energy photons at the end of the calorimeter will have a probability to escape the detector, right? So as I said before, there's another detector just after this calorimeter called the KLM, right? So the KLM is it has alternating layers of iron plates and active detectors. So it's rather difficult for photons to penetrate this detector, right? But unfortunately, there's some other factors make this complicated, because there's as I said before, there's some other equipment, for example, magnetic wires and some other non-instrumented setups between this ECL and the KLM. So if the photon just absorbed by these other non-instrumented setups, it will not detected by any detector. So it essentially is missing. Okay. To our knowledge, there's no the efficiency of the KLM detector for high energy photon detection has not been understood fully at the Bell 2. But there's a similar detector at the Barbar, which we call the IFR detector. So that detector is was understood very well before. So that efficiency is 4.5 times 10 to minus 4. So we just took the efficiency of that Barbar detector we use for the Bell 2 detector, and so multiply this efficiency that with the number 28,000, if you remember. So we end up like 13 photon induced background. So for 6 times 10 to 11 instant positron. Okay, so this is the photon induced background. So if you are okay with this, I'm move on to the neutron-induced background. So for the neutron-induced background, we use giant force simulations, and for the time, because the time my time limited, I will skip the details. So we try to select high energy neutrons from this. From the giant force simulations, and we select neutrons with energy larger than 3 GeV. And we then use this simple formula to estimate the probability of this high energy neutron to escape both KLM and ECL. So KLM has 3.9 hadronic interaction length, and the ECL has 0.8 hadronic interaction length. Combine these two factors, we find that the probability is about 1% for neutron to escape the both detectors. So we use this number, and the giant force simulation, we find that there are about 81 neutron-induced background. Okay, so both photon neutron-induced background is about 94. Okay, so that's the discussion on the background. Next, I'm going to test whether this channel can overperform or to outperform the monophoton channel and the other other existing limits on the dark matter. So I'm going to use the so-called invisible dark photon model to test this channel. Okay, so it's well known that kinetic mixing can lead to dark photon if the actual U1 is really light. And in this paper, we also find that if a mass mixing term is added to the mass matrix between the hypercharge and the additional U1, this also can lead to dark photon. So both kinetic mixing and mass mixing can lead to dark photon of this interaction Lagrangian. So the A prime is dark photon. It has a suppressed coupling to SM fermions. It has a very strong coupling to the hidden sector fermion chi. Okay, so the coupling to hidden fermion is much larger than the model fermion, and the dark photon mass is 3 times the hidden fermion mass. So this means the dark photon will dominant decay to hidden sector particle. So we refer to this as the invisible dark photon. Okay, so in our study, we consider these 2 production channels of dark photon and dark matter. So dark matter is chi, dark photon is A prime. So essentially, we produce the dark matter. Is the interaction is mediated by the dark photon. So the left one is the annihilation, the positron annihilation with the atomic electrons. So the right diagram shows the other process is the Bragstrom process. So it's the positron exchange a T-channel photon with a target nuclear, and it's radiate the dark photon. Then the dark photon can convert into a pair of dark matter. Okay, so I'm skip the detailed calculation of these 2 channels. So this is the result of the limits. So the x-axis is the dark photon mass. The y-axis is the mixing parameter epsilon, and the dashed line is the monophoton, the traditional monophoton channel at bell 2. And the gray shaded region is the limits from NA64. The solid line is the, if we use the background event says 94, we get the solid limits. And if this background is underestimated, we also use a background which is automatically larger, which is 1000. That correspond to the dashed line limit. As you can see, around the dark photon mass 66 MeV, this new channel can actually better than the monophoton channel. Okay. So I also want to emphasize that this monophoton limit is not a real limit. Is rescaled from previous studies. So as pointed out in this SNOWMAP study, there is a potential cosmic ray background which can affect this light dark matter region. Okay, so in other words, this monophoton limits can be much worse. Can be much weaker than shown here, right? So it's good to have a new channel on this light diphoton region. Okay. Let me move on to the second part. Okay, I don't think I have more time, so I'm going to tell you about the study we use BEL2 to probe strongly interacting dark matter. So usually dark matter is assumed to have a weak interaction with the SM particles, for example, WIMPs. But strongly interacting dark matter are also allowed if the mass fraction is small. One interesting aspect of strongly interacting dark matter is that this kind of dark matter can actually get boosted by a lot of astrophysical sources, leading to very nice, very interesting phenomenal signatures and dark matter direct detection, indirect detection experiments. Okay, so but the strongly interacting dark matter are very difficult to detect, right? Because they have strong interaction cross-section, and their mass fraction has to be small. Okay, so this the direct indirect signal are suppressed by a small abundance. For dark matter direct detection, the signal is suppressed by the small abundance. Also, the strong interaction cross-section can make it difficult for the dark matter to actually penetrate the the rock and even the atmosphere above this underground lab, right? There's also CMB constraint, but the CMB constraint is absent if the diameter fraction is less than 0.4%, okay? So to summarize, it's very difficult to study this kind of strongly interacting diameter because the factor I just mentioned, but colliders are ideal place to probe these strongly interacting diameter because at colliders, these factors are not bad, right? Collider search are not limited by the strong interaction cross section and are not limited by the small bandings. Okay, so but at the colliders, the strong interacting diameter will start to interact with the collider, so it's no longer missing, right? So it's so we no longer have mono X channels at the collider for this kind of diameter. So sometimes this lead to so this make people confused, right? So sometimes lead to people think there's no collider constraint on the strongly interacting diameter particles. But fortunately, there's already some studies on the strongly interacting diameter at the Hadron Collider. So at least some papers here. So to our knowledge, there's no studies on the electron collider. So that's why we want to study this in our paper. Okay, so as I said before, strongly interacting diameter will start to interact with the colliders. So here showing is again the Bell II detector. So we have a pair diameter in the final state and the chi and the chi bar. So chi and chi bar will interact with the detector, right? Instead of missing. So the interaction of diameter with the detector is very similar to diameter direct detection experiments. So the diameter will interact with the calorimeter with if the cross section very large, so it will have multiple scattering with the detector, leading to multiple electron recoils and nuclear recoils. So it's produced some so-called cluster signatures at the calorimeter. So this is very similar to the SM photon signature in the calorimeter. So the SM photons events will essentially become the background to this process. Okay. So this is the model we use to study this kind of strong interacting diameter. In order to get a large cross section, so we use a mediator. So the meteor mass has to be small. Okay, so this is the sensitivity of the Bell II for strong interacting diameter. So the x-axis is the mass, the y-axis is the cross section. So it's evaluated at the reference frame Q alpha ME. So this is in order to compare with the diameter direct detection. So there are three channels here. So this is a monophoton. If the cross section is small, it's the monophoton constraint. If the cross section increase, and then there's a visible signature called a monocluster and dicluster. Okay. So as you can see, for large cross section, the electron collider can actually cover these large cross section parameter space. Okay, let me skip this one. So this is the other case for ultralight mediator. So one has to change the form factor to a different form factor, then leads to some somewhat different constraints. Again, so the constraint as here is the direct detection limits. So it cannot probe the parameter space above here because there's the interaction is so strong, right? So the collider can probe that parameter space. Okay, so this is a summary. So I have told you about our recent studies. In the first study, we proposed a new diameter channel electron colliders. So this new channel is a fixed target experiment inside the hadron collider. So we find that this can probe new parameter space invisible dark photon, surpassing monophoton and Na64. In the second paper, we study electron collider constrained on strongly interacting dark matter. And so for this kind of dark matter, it will actually produce visible signatures. And we find that the current data can actually produce the parameter space beyond the reach of dark matter direct detection and the indirect detection. Okay, thank you.
Okay, any question or comments? Okay, I have one. For the second part, for the strongly interacting dark matter, what's the signature at the collider?
So, it's like SM particles. So the dark matter scatter with the calorimeter. It produces a recoil, and that recoil is recorded by the calorimeter.
Yeah. In my opinion, it's very like the long-lived some particle, neutral particle, especially. It's invisible and just then some energy deposition appears. This is very like the long-lived neutral particles.
Yeah. It's a neutron. Yeah.
Yeah, it could suffer from the background like the long-lived K-long, the K-meson.
Okay.
Yeah. Yeah, I think so. Yeah. Okay.
Yeah. So we use the photon as the background.
Yeah, photon is also neutral. Yeah. It's also true. Yeah. Okay, let's thank Professor Zhou Liu again. Yeah. Our next speaker is Shenya Matsuzaki from Jilin University. Let's welcome.
Okay, thanks. It's really honored to be here for me to give a talk on the recent couple of the research developments related to this kind of topic. It's gonna be like a docu-city scenario, but precisely something new. So usually when people talk about docu-city, the typical scale is lifted up to the higher, like a TV scale or much more higher scale to avoid the possible existing experimental data, cosmological data. But today, I'm gonna focus on the kind of challenging scenario. Still, we try to have the chance, try to have a possibility to talk about the docu-CD beside QCD first transition epoch in the summer history. Okay, let's begin. Let me start with the general motivation, like introductory part. Back in the Higgs discovery epoch, yes, we have been excited, but since then, nothing else. That's all about the discovery arising from LHC. So then, this is like kind of the disastrous scenario. Somehow, we have nothing. We have no more chance to talk about Pearson model up to the T10 TeV or sub TeV scale. But it cannot be like that story in reality, since we already know there's still lots of stuff left necessary to account for. For instance, this is a typical list, I think, related to the kind of necessities going beyond the sun model. So, for instance, where is the laser? Is come on. Yes. For instance, baryon symmetry of the universe. This is completely mysterious. Within the Sun model, no chance to provide the precise amount of baryon number symmetry. So this is the kind of characteristic, and it is kind of a definitive signal, definitive hint to go beyond the Sun model. And also dark matter, might be kind of an ingredient beyond the Sun model, or might be just a astrophysical big compact star, kind of a primordial black hole compact object. And also neutrino mass. Within the original Sun models, there is no right-handed neutrino coupling, unequal coupling. There is no neutrino mass generation. They still need to go beyond that. And also dark energy and inflation and possible detectability of gravitational waves. And also we can consider the unsatisfactory ingredient related to Sun model, like a strong CP problem, and also the electric vacuum stability within only the framework of Sun model. And closely related to the dynamical origin of the Higgs potential involving the Higgs mass, and so on. So still a lot of stuff left for us. So we need to account for all of them. So that's why we need new physics anyhow. Then today I'm going to introduce the kind of a counterpart idea in contrast to the conventional scenario, not going up to the higher scale, but instead going down. Let's cool down up to the QCD scale, around 1 GB or sub GB. Anyhow, suppose you have around there, you're gonna observe the QCD phase transition in the sense of thermal history. Then beside QCD phase transition, we try to talk about the missing ingredient related to the beyond Sun model, like this kind of list. So in particular, I'm gonna introduce this type of dark QCD. S is coupled to QCD at the QCD scale. So that means the dark QCD quarks import, they're still having the QCD colors. This implies suppose we have dark QCD quark, these quarks will be charged under both QCD color and dark QCD. It's going to be like a bifundamental representation under the dual QCD, dual color charges. Okay, let's get it. Then, given this kind of setup, we can have a lot of fun related to the beyond Sun model. For instance, we're motivated by the rich phenomenology arising from this setup. So basically, now we're going to have dark QCD, the charged also under the QCD. Then we have the generical possibility to talk about the solution to the strong CP violation in the sense of the composite axiom. Can you imagine like that? So axiom presumably necessary to couple to the G mu tilde, gluon field strength. Yes, this type of coupling arising from the dark QCD sector as a composite axiom coupled to the QCD gluon. This is doable to make up. So this is the one motivation. And the next, actually, in another aspect, actually, this is the biggest advantage in this scenario. We can also talk about the baryogenesis related to the kind of non-perturbative dynamics and non-adiabatic dynamics in QCD, thanks to the coupling to the dark QCD. Yes, this setup allows us to talk about the baryon number symmetry generation based on the what we call preheating mechanism. Somehow it's happening in QCD, just like the same way as in the post-inflationary epoch. Yes, this work has been done in a separated publication. Since I have no time today, I will skip the detail of this kind of scenario. Anyhow, suppose we have also the baryogenesis, successful baryogenesis in this setup. Then, this is also going to be related to the nice interpretation of the possible detectability of nanohealth gravitational production. Because this is the dark QCD set up the QCD scale. Presumably it can produce the first order phase transition since the dark QCD generically can have the many flavor structure, because presumably coupled to QCD as well. At least you're gonna have at least 3 flavors in the sense of dark QCD sector. Then 3 flavor or more flavors in the QCD type scenario, you can observe the kind of first order phase transition. Yes, this kind of flavor argument related to the non-abelian type QCD is still favored, even in the current status of that is QCD, or this is QCD, this is not CD. Anyway, then you still have the possibility to talk about the nanohealth gravitational wave production in this along this scenario. It's good. And still one more, or more two. Yes, so because again, this is set up around the QCD scale. Then we gotta have the new physics spectra arising as a composite dark hadrons. It might create a lot of the dark matter, like a composite dark matter. And for instance, dark neutron can annihilate into the lighter hadrons, just like the same way as happening in the QCD for the neutron annihilating into the pions, like that. Then the symmetric part of the neutron will be gone at the low temperature due to the annihilation cross-section. But only the asymmetric part will be left. This is gonna be a neutron asymmetry. I mean, this is gonna be a major part of today what we gotta observe in terms of the ordinary matter. Yeah, just like the same way. So dark neutron can annihilate strongly coupled, due to strongly coupled, the annihilating into the lighter hadrons, then only the asymmetric part will be left. Yes, exactly the same way. Yes, this will be motivated by what we call the asymmetric dark matter. Then mass scale, yes, can be easily set up, naturally set up around the QCD scale. It can reach the 5 GeV. This is the desired amount of the dark matter mass if it is related to the asymmetric dark matter scenario. Yes, it's so nice. And still one more. Again, it is around QCD scale, like 1 GeV or 5 GeV. Then if we take a look at the current status of the WIMP nuclear cross-section against the mass, like this kind of plot. Here you have the big amount of neutrino flow background. Due to the neutrino flow background, the sensitivity gets lower and lower as you go down up to the QCD scale, like 1 GeV scale. This is still being unexplored regime. Probably the near future will be explored and improved better and better. Then related to this kind of future prospect, that this QCD cross dark QCD is a good candidate to explore like that. Yes, this mass scale is completely natural, arising from this kind of setup around the QCD scale. And also cross-section can be strong, can be large enough, and so on. Maybe if I have time left, maybe I can talk a little bit more later, in detail later. Okay. Then, and still we have the bunch of the physiological consequences arising from this kind of setup. Because anyhow, we're gonna have the kind of dark hadrons, presumably coupled to the photons anyhow. Because anyhow, so here is the bridge between the QCD and the dark QCD. It's going to be a bifundamental representation. The presumably dark QCD quark also eventually coupled to the photon. Then hadron also coupled to the photon. Then the lighter hadron can decay to the photon. So diphoton signal would be like a characteristic in this kind of scenario. Then again, the mass scale is going to be around the QCD scale, like 1 GeV or sub GeV. It's a good mass scale range for the target. I mean, target at the Bell 2 and the Bell 3 or electron ion collider experiment. All right, that's all about the like outline related to this kind of scenario, dark QCD cross QCD. Okay, then you might worry about the current status on the QCD extension, it's kind of extension of QCD, because now we try to talk about like Equistral quark, right? I told you, so it's gonna be like QCD cross dark QCD in a bifundamental representation. So dark QCD quark can carry the QCD charge as well. It's gonna play the role of the like Equistral quark coupling, I mean, significantly contributing to the running behavior of the QCD coupling. Yes. Then, but still, it turns out it's still possible to think about the Equistral quarks due to, I mean, it's thanks to the current accuracy of the measurement of alpha S around the high energy scale and also IR scaling, IR scale. It's still possible to have the Equistral quarks as long as the size of the number of degree of freedom is like a dark QCD color is less than 5. It's like if ND equals to 3 or 4, it's still viable at the current status. Well, in that sense, in other words, this kind of scenario can be proved. I mean, by this exploring the deeper and deeper by using the FRG, for functional renormalization group method, toward the clarifying in IR running, deeper IR running structure. Could be near conformal or not nearly conformal. Then, what about the hadron experiment, hadron signature? Since we're gonna have the kind of Equistral quarks, presumably they're producing the Equistral hadrons, you might worry about like that kind of extra hadron has been already detected through the like you know light hadron scattering the events. But it turns out it's still possible to think about that story, because now it's gonna be like QCD cross dark QCD. It's a dual. So eventually we have to keep the QCD color and dark QCD color invariance. In particular, at low energy, we're gonna realize the like confining phase for both two colors. So all the physical spectra arises as the totally color singlets, all right? In that case, we can't have this kind of a crazy idea. This is little q plays the role of the normal quark. It's like up and down. And capital Q is related to the Equistral quark. Yes, having the dark charge, I mean dark QCD. Yes, precisely this breaks the dark QCD invariance, right? This combination is forbidden by the dark QCD invariance. In the confined phase, you can't see this kind of hadrons, right? Then what kind of type of hadron can be generated in this confining phase? It's going to be like this. Like literally in terms of the original quarks and original dark QCD quarks, you have to have the tons of the quark field to realize the total singlet combination. This is like a high enough protection due to the dark QCD cross QCD setup. So in this sense, it's almost no chance to observe this kind of the exotic hadron spectrum through the normal, the light hadron scattering processes. It's highly challenging. Might be probed, but it's, the current it's really hard, really challenging. So that's all about the current status related to the existing experimental data and the prospects there. So then let's talk a little bit more detail. Can I have, how many times I'm there? Only 5, okay. Then can I talk about a little bit more the details? Yes, this is the model setup in detail. This is one example. Anyhow, the central concept is gonna be the QCD cross dot QCD. For instance, you have the dot QCD quark having the dot QCD charge, and which one? Oh, alpha denotes the normal QCD color. So in this sense, you have the triplet in the sense of color. Here you have 3 and extra chi. The both capital Q and chi will be charged under the dot QCD color, but only capital Q carries the QCD color, all right? So in total, you have the 4 flavors. It's gonna be like a 3+1 structure, all right? Then, yeah, this is the key idea to produce the composite action. It's just gonna, following the original idea proposed by the Jin Kim long time ago. At the high enough energy scale, composite action can be generated to produce the solution to the strong CP. Yes, it's just gonna be like that way. Anyhow, the current scenario is completely follows from the original idea, but more like the the alternative extension from the original idea back down to the lower scale. Now the typical scale set up QCD, not at the higher scale, right? Then we're gonna have the composite action eventually. But since I have no time almost left, then, or maybe, but I still need to talk about this guy. So in addition to the composite action to be generated at low energy scale, at the beginning, we also have to introduce another Pechet-Quinn scalar. So in this sense, in total, this system is gonna be like the hybrid ALP system. This phi or P, and also composite action A, like that. Then given that kind of setup, we can settle the dot QCD vacuum to be free from the CP phase. Here A denotes the composite action. It's gonna be constructed from this kind of this representation. Capital Q and this is QCD charged dot quark, and this is the QCD singlet dot quark, like that way. And also we have the eta prime-like state arising from the dot QCD side, like that. Then skipping the detail, anyhow, the vacuum potential and the potential involving this A composite action and also the elementally the ALP-P, yes, can settle the vacuums to be free from the CP phase, like that way. There's like a linear combination of QCD dot QCD, like this will be gone through the vacuum, okay, vacuum condition. Yes, this is called hybrid relaxation. Yes, then anyhow, yeah, it's good. So in this scenario, for instance, we can nicely talk about the strong CP problem, solution to the strong CP problem. And still we have the low-lying spectrum like the ALP, composite action, and also originally introduced the elementary scalar P, and also the other lighter ALP. Yeah, we can say this is gonna be also the ALP, eta prime-like state. Then typically the mass scale is going to be on the overall the QCD 1 GB scale, and presumably coupled to the photon through the loop processes. And it turns out that this composite LP must be pionic. It must be kind of the fake. No, it's kind of mimic particle of the pion. It should have the same mass and it should have the decay. I mean, it should have the lifetime, same lifetime. Yes, otherwise it cannot survive. And also we have the baryonic state. This guy is gonna be the kind of dark baryon, I mean, as a dark matter. Maybe let me quickly go through that point. And maybe I have only 1 minute. Yes, this is the dark baryon scattering process. They scattered off the lighter hadron. Yes, this is like what's that? Summer freeze-out scenario to produce cosmological abundance. Through that, then freeze-out scenario, it's gonna give this kind of tiny amount of radical abundance for this guy. Given this, the tiny radical abundance, now we're gonna talk about the present day scattering process at the dark matter detection experiment, scattering between the dark neutron baryon, and the nuclei. Yes, this will be generated through it's gonna be like QCD sigma meson portal scenario. It's kind of perfect analog of the Higgs portal in the standard model. Yes, instead of standard model Higgs, now you're gonna have the sigma meson. The sigma meson coupled to this dark matter, because this guy is also dark QCD stuff. This guy is also dark QCD stuff. Presumably, this guy coupled to the sigma through the gluon exchange, because they're sharing the QCD colors. I mean, inside this composite. Then through the QCD Higgs portal, this kind of spin independent, the cross section can be generated. Well, then maybe I need to skip the detail. Then eventually it hits this parameter space. It can be probed and necessarily accessible soon or not, I'm not sure. But it's really interesting possibility. And also, I didn't talk about it in detail, but this kind of process, I mean, this kind of coupling, mixing coupling between sigma and sigma D is also closely related to the realization possibility for the QCD baryogenesis. Okay, let me stop here just by showing the summary. Come on. Yeah. Yes, okay, let me stop here. Thanks.
Any quick question or comments? Okay, I have one. I wonder, for this model, do you have any new signatures, experimental signatures compared with, for example, the usual action model?
Compared to usual action model, for instance.
Please use the microphone. Yeah.
Well, many things actually. For instance, maybe I just can pick up one. What's going on? It's like this. Basically, now I have the equistral ALP, this guy, E. This is not like an action. This is just like eta prime. It's kind of a dark eta prime. Dark eta prime can decay to the photon. This is the dark eta decoupled to diphoton. Yes, this can be proved at Bell 2 or Bell 3 or the electron ion collider, in addition to the Norman axiom.
Okay, but the fellow state is the same. It's still the diphoton, correct?
Yes, but mass range is different. I mean, I have the hybrid ALP. Like in addition to the normal ALP, it's gonna be like this guy. The lighter ALP and ultra lighter ALP, and I have the either D at the mass scale of the QCD scale.
Okay, I understand. Okay, let's finish our session, the first session this morning. Because we still have 5 talks for the second session, so let's get back at still 10:35. OK, 大家10点还是10点35回来，因为我们后面的报告数目还比较多，然后我们不要影响我们中午吃饭。OK。
各位老师，我们今天的茶歇安排在会议室后方，大家从后边这个门出来就可以看到了，谢谢。
韦连福老师在现场吗？麻烦你在这里拷贝一下你的 slides。韦连福老师。 好，我们报告马上要开始了，要听报告的老师请就座。好。好，接下来我们有请西南交通大学的韦连福老师给大家介绍。好，大家欢迎。好，韦老师开始。
感谢这个组委会的邀请哈，给我这个机会来给大家汇报一下我们的工作哈。我本来是做理论的，对吧？后来这几年呢，这个建了实验室。所以呢，我们做一些和引力波探测和暗物质有关的一些这个一些技术的一些实验啊，那现在主要包括这个，我今天主要讲的是我们超导探测器，对吧？超导探测器啊，那么我的这个团队呢，我们有做理论的，对吧？今天呢，明天啊，这个郑浩和那个何翠荣啊，分别要讲一些具体的一些2个理论方面的工作，对吧？然后呢，做实验的这几位呢，没有来啊，对。就是我们看面向这个射频波段引力波和暗物质探测用的一些技术。我们这个技术呢，主要是超导探测器，而且叫超导光子探测器，对。但是呢，这不是光学波段，是射频波段，这个微波，微波，好，那么我今天的这报主要是简单的讲这一下这个思路，对吧？就首先呢，我们看呢，这个为什么做引力波和暗物质探测的需要超导光子探测器，对吧？尤其在射频波段探测呢，为什么需要这样一个探测器？然后呢，就是讲一下这个超导探测器的是什么东西，比如它的最灵敏的探测，比如说到单个能量光子的能量探测，这量子探测器是什么东西？那我们做了哪些工作？然后就要聚焦在在微波射频频段的一个灵敏的信号探测所需要的一种超导探测器，叫做约瑟夫森结，基于约瑟夫森结的一个微波光子探测器。对吧？最后呢，我对工作做一个总结，我展望，对吧？那么我们首先回顾一下为什么我们需要光子探测器来测引力波，对吧？大家都知道，对现在低频段的引力波探测，对吧？我们引力波的目的实际上是测2个时空点呢，由于引力波来了，使得它相对的距离，对吧，发生调制变化。那么我怎么样去测这个东西呢？我要给大家一把尺子，这把尺子呢，对低频来讲，意味着它引力波的波长是非常大的、非常长的，所以要有一个非常长的尺子。这个尺子呢，就是用激光来做，对吧？那你要量这个尺子的变化，量了尺子的变化，对吧？要求呢，这个尺子的灵敏度呢，你要是能够达到引力波的无量量整幅的量级，那么如果你极光的波长够了长度的话，那么你要测的灵敏度呢，要到比如说如果是引力波10^21的话，你测的精度要到10^21。那么通常呢，我们的通常的干涉仪没考虑噪声量极限的情况下，大家知道对吧？那你极光干涉仪，那你能测的是整个波长，极光的波长除上引力波的波长，所以呢，一般的情况下你只能到10^10，所以现在的极光干涉仪能够到亚皮米纳米是非常非常不错了。但是对我们测引力波是远远不够的，还差10个量级呢。那为了提高这个量级，那我们要考虑它的噪声。我们要把噪声，把它闪离噪声给它用起来。那么这个时候你要激光的强度要强， 对吧？强，那么可以把那个补上来。这就是整个用激光尺子去测这个低频引力波它的基本的要求，对吧？所以你看那个你要这个测好这个磁场干涉仪测相位，这个相位的精度实际上与这个用激光的功率是有关系的。那所以呢，在通常的这样的我们就要测这个用激光来测距，用激光测距呢，我们就是一般的测距，我们就是用这个外差办法，对吧？就可以测了，这可以到10的负9量级是比较好的了。那么你要测引力波，那是不够的，对吧？好，我们把这个思路理了一下来，就是我们最近的这个在中国科学上呢刚发了一篇文章，就是这个现在正在排版吧，对，就是我们设计了一个1赫兹附近的引力波约级激光干涉，对吧？啊，这个是明天的这个郑浩啊，他要这个给大家分享一下，对吧？那么你从这个LIGO的这个装置里看，对吧？除了这个激光系统，它外面还有一个探测器，这个探测器就不是一般的那个光强的探测器，是一个光子的探测器，对吧？那呢，它要用这个功率来把这个灵敏度提上去。那么它所用的探测器，因为它激光的波长，它用的是微米，比如1微米。那么它用一个1微米的对1微米光子响应灵敏的这样一个单光子探测器，这个就是不是超导，是半导体光子探测器，对吧？半导体光子器。啊，那么把这个用上，把这个利用这个法布利波的腔来补偿这个尺子的长度，那么就可以做出这样的灵敏度曲线，对吧？探测灵敏度曲线。啊，他们确实做到了，然后呢就实现了引力波地引力波探测，对吧？大家知道。当然了，这个就是说你这个尺子呢，不是说越长越好，对吧？不是越长越好，你就是一个引力波的这个波长量级就好了。你太长，那么也不行，太长了灵敏度就变低，因为呢这个灵敏度呢是跟这个函数有关系，你看这个函数 L 如果大的话，它后面的话这个因子变0了，所以没有用，对吧？啊，那么从这个角度来讲呢，就是你用激光来测引力波的话，你还是需要单光子探测器的。这个单光子探测器要工作在你激光的波长能够探测的这情况下，对吧？好，那么实际上呢，这个引力波的这个频谱是非常宽泛的，对吧？大家现在都知道，你看这个有低频的，高频的，但虽然说波源呢比较少，但是也有很多理论工作中也有很多高频的波源，对吧？那前面的这个激光的干涉呢和这个太极、天琴还有 LIGO， 对吧？还有小型的桌面的都是激光干涉，对吧？那么它也都需要有个对激光敏感的单光子探测器啊。包括你如果是测这个阿里计划，对吧？那么它也要去测那个微波背景的，所以它也要这个一个微波这个敏感的这样一个接收装置。那我们今天呢，主要是focus 在这个兆赫兹到 G 赫兹这个频段的引力波怎么探测它。在这个频段来探测引力波，刚才我们说了，你可以用一个激光，它对吧？它跟这个兆赫兹和 G 赫兹波长比拟就可以了，但是那个灵敏度太低了，所以在这个兆和 G 赫兹范围里面，是基本上是不可能用激光干涉来测的，不能用激光干涉来测的。第一呢，这个频率越高的话，它实际上相对振幅是非常低的，这是一个初步的估计，初步的估计。那么要测这样一个频段的引力波，我们只能够用其他办法，对吧？这个办法呢，就是把引力波的能量，把它 转到电磁波，对吧？那这个就是这个尼克森效应。大家可能很多人知道，可能很多人也不知道，对吧？其实上呢，这个用激光干涉来测引力波，最早也是这个人提出来的，后来才被美国把它完善了，用起来，搭建起来LIGO这个激光干涉。最早的引力波用激光干涉来测的也是他提出来的，后来呢，对高频部分来测，那么也还是他。所以呢，对低频和高频原初的想法怎么测引力波，都是这个人。低频的已经LIGO他们已经做成功了，现在的大部分推广的低频。那么高频呢，目前为止实验做的还是非常少的，对吧？非常少的。它的基本原理和低频测的不一样，低频是靠激光干涉，它这里是靠呢在一个强磁场里面，这个引力波它会变成这个有一部分能量会反转到变成了电磁波，那你就去测电磁波。好，最早的他的想法呢是在这个伽马，对吧？那伽马波段呢，这个刚才说频率太高了，无量感整幅太弱，所以呢实际上是很难测到的。那无论怎么样，你最终要去测引力波转成电磁波的信号，那你要用非常灵敏的光子探测器。那比如说你要测它转成伽马光子的话，你用伽马光子的探测器来测，对吧？那我们关心的呢，就是不要那么高频，对吧？我们关心的，比如兆赫兹在射频波段和几赫兹。那么实际上呢，这个很难测，为什么呢？因为呢，这个引力波的能量转成电磁波，它这个转换率呢是非常低的，是10⁻38，对吧？你在这个以前这个在一个通常的磁场里面去转，是很低很低的，产率很低的，对吧？所以这个英国人他们用欧洲核子中心曾经去试过，他们试的是太赫兹波段，那么离这个要求它探测到的灵敏度低很多很多，所以呢是只能给一个实验的限制，是不可能测得到的，不可能测得到的。那我们的目标，我们就说不要在那么高的频段，我们在这一个这个射频频段，就是说在几百兆到几十 G 这个范围里面，我们来看看引力波有没有可能在强磁场里面转换成电磁波，对吧？好，那么这里有一个很大的 bug。就是说你在这个磁场里面，一般的为什么那么弱呢？是因为呢，在强磁场里面，这个引力波变成电磁波是一个二阶效应，它是跟引力波的无量感整幅的平方成正比的，所以这是很难测的。那么我们就想办法让它变成一阶效应，对吧？好，最早呢，我做这个课题实际上也是受李方玉老师的影响，对吧？他在13年左右，他跟我说，因为我一直在做这个单光子探测器，他说了，你能不能用单光子探测器来测引力波的电磁响应？那后来我们就受到影响了，我们就在考虑这个问题。这是李方玉老师早年提的一个，现在叫做李贝克探测器。他就说，在强磁场里面，引力波转成电磁波的转换能量率非常低。我怎么提高的这个转换呢？他说我加一个高频场，跟这个转换率很小的这个转换率呢，很弱的呢，做一个相干谐振。那这样的话就是使得信号放大，对吧？他的想法就这么简单，就是说我加一个外场和它相干。当然了，这个方案呢，这个也这么多年来，20多年来也引起了很多的争议。对吧？很多争议，有网上有个这个东西影响还是比较那个的，对吧？但是呢，我们认真考虑了他没有发表在正规期刊上，他只是发在网上，对吧？所以我们也没办法去 comment 他，对，只能说是的，就是说分析他这个为什么他认为不可行的原因，我们就一个个问题把他的 问题的解决了，对吧？解决了，那不是不可行，是因为他对这个理解呢，或者是他的角度不一样，对吧？比如说他说这个强化力太低，那是按照这个2阶静止场的2阶响应来说的。如果我们用相干来给它放大，这是一般的技术，对吧？比如我们手机信号这都是相干放大的。另外一个他说这个致使你相干以后，这个也很这个强度很多。那么他呢是认为是2个电场的相干。其实我们这里呢，李方宇老师这里方案是电场和磁场相干，对吧？相干出这个波形矢量出来，对吧？好，所以我们重新去算了一下他的问题，对吧？发现了这个李方宇老师的这个原来的方案呢，肯定有了，只不过呢数量级估计有点大了。那我们重新算了一下，数量级是少了一点，对吧？但是仍然是可以测的，至少从不是那么2阶了，它是有个放大的。对，但是呢，李方玉老师那个里面的探测器，它是靠外面加一个高斯数进去的，那个是技术上是比较难的，所以我们对这个方案做了一下这改进。我在里面产生一个射频场，对吧？以后呢，相当于给它在里面产生，要提高它的能量转换率。然后呢，我跟这个郑浩呢，我们一起呢，就是在18年的时候就做了这样的估计。结果发现，要探测这样一个转换呢，那我们需要能够数到这个光子，这个微波光子数呢，必须是，比如说1秒钟我要能测到1个，对吧？以上，那需要很灵敏的微波单光子探测，对吧？微波单光子探测，如果有这个东西的话，我们去做一个这个系统，我们标一下它的探测灵敏度、可达灵敏度。发现呢是可以测得到这个原初引力波的，在这个高频段1 GHz 左右的这个信号的，对吧？这是我们这个原初引力波的这个要求的灵敏度，这是我们这个系统可以达到的这个灵敏度，对吧？好，刚才说了，那么这引力波探测我们要这个光子探测器。同样，我们暗物质也要光子探测器，对吧？这是暗物质，大家都很清楚了，对吧？比如说我轴子，在氢轴子，那么它是一个波，它是在射频波段。要探测这样的一个射频波段的轴子，我们还是需要的叫一个，还是在放到强磁场里面，然后，对吧？对它进行的这个轴子转成这个电磁波的信号进行探测，这是大家讲前面讲了很多了，对吧？那么我们就分析实验上能不能行，对吧？我们比如说你估计一下，在一个腔里面如果有磁场，那么它产率，对吧？轴子转成光子的产率，这个功率。1秒钟的10⁻23瓦，这个就是差不多到了大概是几十个微波光子的水平，对吧？几十几倍，那你要求非常灵敏的微波单光子探测器，对吧？那就是现在有很多的实验装置来测轴子，为什么现在还没测到呢？对吧？当然，轴子本身是一个很弱的信号。另外一个很多呢，当然国外也有这个微波的单光子探测器，但是那个探测器呢，他们一般呢都是比较窄带的。好，那么我们就是看又怎么用超导？对，超导跟光电探测器不一样的地方呢，它的 gap 非常低，所以呢，它能够测到频率非常低的这个电子信号。好，那么最灵敏的就是单光子，那么什么是单光子？就是1秒钟，就是一次呢只发射一个光子叫单光子，对吧？好，我们去数这个单光子，要找这个单光子探测器，那么它可以区分不同的光子数， 这是我们在做这个超导单光子探测器的过程中，先做一个超导写真器，品质比较高，比如说我们首先做出来一个超过100万的，然后我们去测，先用这个红外去测，看到能够测到亚皮瓦，对吧？那这个是我们比较好的结果，这是在红外情况下测的。那么我可以分辨到8个光子数，对。我们也做了一个阵列，就99个探测器在一个阵列，那么像最重要的要测微波，微波呢我们就是要用这个优生节来做，对吧？这是我们最早的实验理论的想法，怎么样让它这个能够实现微波光子探测，而且这个探测效率比较高，对吧？这是后来我们就扩展了这个想法，对吧？这个想法，那么一个呢是用这个把它当那个力来测量，这是今年发的 PIR 上的，对吧？这今年我们发了个 PIA， 就是我用几个把它串起来，变成一个阵列，对吧？它就可以效率比较高。那所以核心的东西就要造这个器件，这个器件是蛮难造的，是一个优生节非线器件，我们有微加工工艺把它做出来，对吧？做出来也要我们首先测对红外的有没有响应，对吧？这是我们测的红外的响应这个叫做预值探测然后呢，我们最近呢就把这个性能指标把它这个优化了一下，所以我们给了这个对微波光子它能不能够来就优生节能不能测微波单光子宽带的，我们这个文章呢给出整个设计和数字仿真。确实是可以的，这个 PRB 在接受了，对吧？而我们就做了个实验，这个实验呢，目前呢是算是比较成功的，但是灵敏度还没有达到我们预期的最灵敏的程度，对吧？那么最后呢，用了这个东西，我们怎么去测引力波和暗物质就是像这样，我们在搭建这个系统，这是我们对这个系统灵敏度的标定，是可以在7个G赫兹上面的。是能够测到这个轴子的，这个轴子的要求的，这2个模型要的灵敏度是这样，对吧？好，大概我的汇报就这样了。好，谢谢大家。
大家有没有什么问题？
感谢韦老师精彩报告。我想问一下，就在那个约瑟夫森节里边，你们测的实际上是量子比特从基态到激发态的震荡还是什么？
不是，就是超导微波光子探测有2种，一种呢就是量子比特来测，那个是要共振才能够基态到激发态，那个载带，如果你不共振，它打不上去。我们约瑟夫森节这个是宽带，它是测微波的变化的影响节的这个有效温度。和节的这个作为相位粒子它的振动的出相位，所以它是个宽带的。超导比特测呢是个载带的。
所以你们测的是，比如说轴子 dark matter 产生的光。
对。
那么这里你需要加入一个磁场，在约瑟夫森节里是吧？
对，你要加一个磁场，它才能够轴子才能变成光子嘛。
对，这会不会影响这个节的那个功能？
不会的，你作为一个系统的噪声嘛，你把它扣掉就完了，这只是影响节的某些参数。对，
好，
这个不会整体影响这个节的性能的。对。
还有没有问题或者 comments？我想问一下，就是刚才讨论的，如果是跟我们普通的这种谐振枪比的话，我们这里如果是宽带的话，它的灵敏度会有下降吗？
是这样，因为我们枪做定了，它的频率是定的，对吧？那 Q 值越高，它的这个就是响应的频率让越窄。那么你要少，怎么少呢？就是我们现在要加一个调节杆，比如说我这个月我扫这个频段这个频率，下个月我加调节杆，我来扫另一个频点，
好的，
是这样的。
那其实就是说，我们做实验的时候，还是一个频率一个频率的去扫描，是吧？
对。
好的。
对。
你跟共振箱实验有什么区别吗？就是说，你这个跟共振箱实验不是一样吗？共振箱我也是调调节杆。
对，共振箱的调节杆只是调节，比如说我哪个质量的轴子，对吧？
对，调频率就是。
对，调频率。对，然后呢，就是你调了频率以后，你能够共振上了，跟那个有共振了，然后呢，你再去测那个信号，我们就做这个探测器测这个信号。
你做的是探测器那一部分是吗？
对，
后端系统是吧？
对，
我们叫后端系统，好的。
对，我们做的这个今天讲的这是后端系统。对。
好，那我们再次感谢一下韦老师。好，我们下一位报告人是理论所的李田军老师。好，我们欢迎。
首先非常感谢这个组委会的邀请了，这有那个PowerPoint的是哪个？
下一页，然后下面是几个。
好的。然后非常高兴参加这个北京暗物质研讨会我报告题目，我这个报告实际上是以前讲过几次，都是英文讲的，然后这次我也是略微改一下，用中文来讲这样的话，那么这个题目我有时候可能会夹杂一点英文The right-handed left-arm bulk region for diameter in the generalized no scale FSU5 with effective supernatural supersymmetry。那么这个如果我有时间的话，可能会 comment 一下 PMSM 有一个新的 scenario， 就是 the right-handed simulon NSP scenario。这个当然，这下面这一部分实际上主要是 LHC SUSY search， 因为 LHC 的比较 senior 的人找新物理也是有点迷茫，他们找什么东西这个实际上主要是那个 motivation。那么这个报告呢是基于以下的这些文章比较多，我就不一一讲了。那么我们知道，这个随着 Higgs 粒子被发现了以后，标准模型已经被确定了。但是呢，标准模型不可能是我们粒子物理的最终的一个理论因为各种 motivation 的for new physics 比方说，一方面呢，我们有一些新物理的一些证据，比方说暗能量、暗物质、中微子质量有混合、重子不对称和 inflation etc。或者，那么从标准模型自身看的话，我们标准模型是有两类问题的，一类是精细调节问题比方说这个宇宙学常数问题、规范等级问题 （strong CP problem） 费米质量这里面质量有个等级费米质量有混合的 issue。另外一个，我们看这个模型，当我们把一个模型写下来以后，看这个模型是不是优美。那么这里面就很明显，从 theoretical 是有些问题的。标准模型有3个 interaction fundamental interaction 有4个，那为什么不是1个呢？对吧？这是我们这个 interaction unification graphite theory 或者一个 string theory 来描述的。另外一个，我们另外一个非常 confused 的是，标准模型有3代费米子，每一代费米子也有很多，有15个。我们45个费米子为什么45个费米子或者更多48个加3个又是中微子，不能形成一个单独的表示那么这个就是个我们就是做大统一的叫 Fermi unification 我们通常大统一理论是一个规范相作用的一个统一理论，实际上还有更general一个 Fermi unification， 那么这个也是一个理论。那么还有一个就是一个规范耦常是统一，然后我们不能解释不能得到规范耦常统一，也不能解释电荷量子化，然后标准模型呢有太多 parameter。当然我这里不会 comment 这个电路真空稳定性问题，因为这个问题非常 trivial， 你 New physics model 非常 easy 可以解释这个问题。那么简单来说就是说，我们的确需要这个超出标准模型的新物理。那这样的话就是说，如果是10年或者15年之前给有这个，比方说有 workshop 或者 conference supersymmetry is very hard， 但到现在的话就是说基本上没人做但是为什么我依然why do I still believe supersymmetry？这样的话，我们就可以看一下，就说我们从理论上看的话，超对称代数是对彭加莱代数一个推广这是个基础理代数。超对称呢是这个 S matrix 是最 general 的对称性类似这个 整体对称性到局域对称性，我把超对称呢局域化呢会得到 supergravity 啊，这理论上非常 strong 的 motivation。那从唯象上看呢，这个超对称呢就是自然解释了规范等级问题，同时基本上解释了宇宙学常数问题的一半啊，把 m Planck 的4次方到 m 数的4次方。所以 in general 就是我们来说呢，就是超对称呢是一个什么联系非常有希望的低能唯象和高能基础物理像大统一理论或 string 理论的一个桥梁。当然，我们也可以反过来问另外一个问题如果我不做 supersymmetry 这个报告我给的是一个纯粹一个作为一个理论物理工作者来想的，我 work on what kind of theory I work on, which theory can compete with supersymmetry? Looks at least right now there's no. 所以这个原因就是说，也是从上看的话，超对称依然是一个非常优美的理论但是我们就是说，我们做这个超对称标准模型的话，你会就是说我们可以得到规范耦常统一可以通过辐射修正破解这个电路对称性。也如果考虑 Z2R symmetry 的话，我们会有自然有这个暗物质候选者。然后这个规范耦常统一呢，就强烈的暗示了大统一理论比方说 SU5、SO10。那么这些理论呢，实际上是个规范相互作用统一的理论。同时，像 SO10模型的话，它是把一代非粒子可以统一在一起一个16维表示选量表示，也就是15加1又是中微子。那么这个时候的话，因为我是半单理群，所以我能解释电荷量子化，然后等等一些唯象还是非常优美的。那么这样的话，实际上我们4维大统一理论是有一些问题的就是说，简单来说，主要是一个黑克斯二层同态分裂问题和一个量纲位物质衰变问题通过交换 Carlo-Casino 的一个东西。同时呢，一般4维大统一理论是运用了一个错误的非粒子质量的 ratio 这 m1/m1 等于这个 md/m strange quark。那么这些问题4维大统一理论的问题呢，实际上是你把它作为高维理论的话，就自然能解决我这里仅讲 string model、orbifold gap 也是能解决的。那么就是说，比方说我们考虑这个 Calabi-Yau 或者 orbifold complication of pathological E8 cross E8 string theory， 这个呢 Calabi-Yau complication 呢，你可以解决这个问题，是因为 Wilson-Lang gauge symmetry breaking。orbifold 的情况是一个 orbifold projection。如果我们考虑 deep brain model 的时候，实际上是个 deep brain splitting 的时候，就是 gauge symmetry breaking 这是等价的一个描述。然后还有一个就是我们还有一个 string model 叫4维费米旋模型 construction 4维费米旋这种模型的话，他们在 cosmology level 1是仅仅 construct 什么呢？仅仅 construct 的这个free PSU 帕特萨 model 和标准模型的模型，这类模型呢是没有上述问题的。还有一个类问题呢就是大概17、18年前的 F-series model building。那么这个 model building 有个特殊情况，就是 U1X、U1 flex 的对称性破缺。那么这里这些告诉我们，这些模型都能解释这个4维大统一理论的问题。这样的话，我们就会有一个物理图像，就是我通常跟学生讲，你学物理，我先有一个物理图像，整体物理图像，我再去做一个 physics。那么就是说，这个我通常会说 grand particle physics paradigm。From string theory to string model to graphite theory to supersymmetric standard model to standard model， 你会跟物理图像在心里，然后我再去做 physics。但是 unfortunately， 就是说我们 LHC 数 Z search 呢，实际上是给了很强的限制了比方说 Guglielmo mass 大概是要大于2.3个 TeV 前2代 Squark mass 大概要大于2个 TeV 左右，第3代 Squark mass 大概要大于这个1.3个 TeV。那么这样的话，我们就通常会说超对称标准模型是 fine-tuned 的。这个时间关系我就不勾数了那个。那么这样的话，我们就会想一些问题，在超对称理论里面，我们会做什么呢？第一件事就是这个超对称这个 fine-tuning problem 是不是可以自然解决？另外一个呢，就是我们要做暗物质，暗物质要 nature， 我们要是 principles of nature 简单，自然简单。那么这样的话，我们是不是有这个 bulk region for dark matter？如果存在的话，我们是不是在以后的实验能够把这个 bulk region 都给检验就这个东西我 predict 了，我能够检验，就这样的一个 game。那么首先看这个fine-tuning issue。fine-tuning issue 的话，就是说我们相信超对称是因为我们 believe associated graphite theory 和 string theory， 所以我们是一个 high energy definition for fine-tuning measure。就是说我们首先定义 fine-tuning measure， 那是个高维定义通称我们这个叫 EENZ 或者B 界就是 Barbier-Gil dish， 通常你们可能会知道是 Barbier-Gil dish， 但实际上是2年前那个86年是 ENZ 的话，他首先提出来的。那这是什么？就是说，如果我在 gas scale 或者 string scale 有个 fundamental parameter AI， 那么它的 fine-tuning measure 是 partial log mz partial log AI。那么这个得到 AI 呢，会形成一个 set， 比方说它是 finite 的，你取最大的一个就是我的理论的 ENZ-BG Phantom Image 啊，这是非常明确的。那么这样的话，我们就是说，我们是不是可以提出一种 scenario， 这个 ENZ-BG Phantom Image 是 automatic order 1的，而且我们做理论物理，我们有自己的 philosophy， 那么这个 principle 就是简单性 natural 自然性啊，简单性自然性。我通常举个例子，就是说我到美国，大家知道美国的中学生水平比较低，我到美国的中学去的话，我给美国的相当于我们的高2或者高1的学生，他们就能 get the point。其实就是一个简单的 calculus 啊，通常他们大概在中国相当于中国的高2、高3的时候，高2左右或者高1的时候就会学微积分。那么这个 solution 就是这样的。啊，这个solution非常简单啊，实际上是我也不能说首先在理论上发现的，实际上是实验实际上是那个做扫描Tristan 计时自然反推的时候发现，在考虑这个 no scale FSU5 的时候，这个反推 image 一直是 10啊，就是相当于 10%。当时我觉得很奇怪，但我很快意识到这个 point 非常简单。假定我有个 theory 啊，尤其仅有一个 mass parameter m star，m star 呢是来源于 supersymmetry breaking， 那么 mg 呢也是正比 m star 啊，那么你计算 partial log mg partial log m star is automatic order 1啊，所以是非常 natural 一个，所以我们叫 supernatural supersymmetry 啊，是非常 natural 的。这样的话有2种可以考虑啊 realize 的情况，我们 discuss 跟 no scale supergravity m star 是给 G mass。M0 on S1 G2 M star 是一个 gravitational mass 啊，就是这样的一个情况。所以这个情况就是说，我有一类超对称 scenario ENZ-BG Phantom Image 是 automatic order 1的。然后我们可以形式上可以更准确的定义啊，这是基于这个 string theory string model 一个定义。然后呢，我在这里要说啊，另外一件事啊，就是说这个是我和丁兰啊教授啊。朱斌教授和 Florian 做的一个工作啊，实际上是一个，当我们有 supernatural supersymmetry 可以把它推导一个 effective 的，就是说 ，yes， 这个就是说，如果我在一个理论里面有一些 fundamental parameter， 他们给的 ENZ-BG Phantom Image 很大，如果这些 mass parameter 是 correlated 的，那么这时候的话，你可以证明啊，这个超对称 scenario 依然是 natural 的。这个证明实际上是一个半解析的证明啊，基本上可以完全证出来这个事情。我们叫 effective supernatural supersymmetry。好，那么另外一个呢，就是跟这个研讨会的主题是一致的 ，symposium 主题是一致的，就是数据 dark matter。我们通常数据 dark matter 是有4种 scenario， 一个是 bulk region 啊，这个是说 spectrum 是比较 light， 这是肯定是最 natural 的一个情况。一个是 Z Higgs 啊，我们说 Higgs funnel 或者 Higgs resonance 啊，这些 Z Higgs resonance 等等之类的，这个当然是。由于你可以说是一个反 tuning， 为什么质量是接近的？然后是 correlation 啊，你也可以认为它有一点点反 tuning。然后另一个是 mixing scenario 或者 well-timed scenario， 那么就是说 LCP neutrino 是有一定足够的这个 Higgsino 和 Wino component 啊，这4种情况。但是我们很早刚开始也都知道，这个唯一的 natural region 就是这个 bulk region 啊，就是没有什么反 tuning 进去。那么这样 bulk region 很明显是个 most natural case。但是呢，我们 LHC 数据 search 呢，已经给了非常强的这个限制，所以呢，你可能得到 bulk region 呢仅仅是这个右是 lepton 是比较轻啊 ，LCP neutrino 也比较轻，然后他们的 annihilation 啊，只能得到这个情况。然后这个情况呢，实际上是我这个报告通常是给什么？就是给这个 Future Collider 给的啊。实际上这个主要是为什么呢？为我们 FCCE、CPC 呢提供一个比较具体的scenario 可以去探寻的一个scenario。然后是否我们可以真正 realize 这种 bulk region 啊？这是一个非常 interesting question。其实我刚才也是没有想，刚开始也不太相信，但是后来的确是把那个字做出来了。那么这样的话，我们先考虑一下什么是flip SU5， 它的 gauge group 是一个 SU5 cross U1， 这可以镶嵌到 SO10，SO10 只有3种 breaking chain 啊，这是其中一种。在 SU5 啊，类似 George Galassi SU5， 我可以定义这个 generate U1 prime 啊，这个是瑞士定义这 U1 prime， 然后 U1 prime 和 U1x 一个线性组合给我一个 hypercharge 啊，就这样的一个情况。那么这样的话，标准模型惠米子是形成11、5 bar -3和15。11表示中是有quark doublet 右手下夸克，右手中微子。5 bar 呢是有一个右手上夸克和 quark doublet 和 lepton doublet。那么单从单态呢是一个右手的带电 charge particle 像这个 electron 之类的。 那么 Higgs 粒子呢非常简单啊，我们通常做 SU 模型，这个 Higgs 是肯定要伴随表示，这里面的 Higgs 实际上是一个反对称表示，就是11、18负1，其实很简单，因为这里面有个中性分量，让这个中性分量得到真空期望值就可以了。那么 Higgs 呢还有一个55巴，这两个是给破解电路对称性需要的 Higgs-Doppler 的粒子，这个呢中性分量得到真空期望值呢就会把 Flip SU 破解到这个标准模型。然后这个我们通常会有10、10巴、55巴的原因是什么呢？就是要说关对称性破解的时候要 keep 这个 D flatness 和 F flatness。那么这个 flip 是什么意思呢？就是 up down NE neutrino 和 electron charge lepton 的一个和 HDHU 的一个 flip 就 exchange 这个意思。好，那么这个 scenario 呢，我可能没有很多时间因为这个报告可能是1个小时的报告，就我没有时间解释。就是说我们有这个就是给出一个 missing pattern mechanism 来解释二层同类分裂问题，所以这个情况是没有量纲为伍的质子衰变，通过 Calor-Casino exchange 这个就在这里给出来，这个 potential 就给出来了这个结果。那么这样的话，就是说我们还会想到另外一个问题我们做一个 graphite theory 做过以后 ，long RGE 就unification scale 是2乘以10的16次方 GeV。而我们做 string model 的话，我们发现 string scale 是多少呢？大概4或者5乘以10的17方 GeV， 所以这里面有 gap factor 20， 为什么我们不太理解？所以呢，这时候的话，我们就提出来一个 test flip SU5 model， 就加入 TV scale vector particle， 然后得到一个 string scale 的 unification 这是一个想法。那么这样的话，这类模型的话是为什么叫 FSU5？ 因为我们在4维费米学模型构造中可以把它给构造出来通过 F-series model building 也可以把它给构造出来，所以我们就叫 FSU5 是比较简单的一个名字取出来。好，那么这样的 vector particle 呢是什么？就是11、18负1，然后是1负5和15这样表示。然后我可以看一下 gauge capacitance unification， 首先是 SU2 和 SU3 呢，统一在这个传统大统一能标大概2乘以10的16次方 GeV， 然后 SU5 乘以 U1 呢，统一在这个 string scale 大概是这样的一个情况。这是 two-step string scale unification。那么另外一个就是 no scale supergravity。no scale supergravity 是非常简单，就是说我们做 supergravity 的通常会到一个 ADS vacuum， 但是我可以找到一类 Calor potential， 非常简单，就是这个 Calor potential -3 log T 加 T bar。这个的话，你去算的话，你带进了你的 scalar potential 的话 ，automatically equal to 0，automatically 得到这个 Minkowski vacuum， 所以这个是一个 no scale 这个情况的话，这个就是一个 no scale 的情况。那么 no scale 的名字呢是应该是 John Ennis 取的。那么这个 no scale supergravity 呢，实际上是可以在weak couple hydraulic string 中做紧致化得到，这是威腾以前的一篇文章其实如果所有的年轻人要做 string phenomenology 的话，第一件是要把这个看到比较紧致化要算一遍基本上就是这个做子。然后，那么在这个 MC-S1G2 呢，这是我和我的合作者做了就是也是可以在这个是在 leading order 也是得到 no scale supergravity no scale supergravity 只是 leading order 或者 tree level 的一个结果。那么我们看这个 boundary condition 是个什么就 M supergraph CMSM 呢是一个 gauge mass M1/2 scalar mass M0， 然后 Chinese coupling A tan beta， 然后 sin of mu。那 no scale boundary condition 是一个 gauge mass 是不等于0 M0 A B mu 所有其他东西都等于0的这样一个情况那么这个情况的话，实际上它是自然解释了我们通常说的超对称的 CP variation 和 FCNC problem。原因呢是这个情况非常类似什么呢？就类似我们的 gauge mediation 情况。但这个 scenario 呢是对微项来说是 disfavored， 原因非常简单。如果你 run RG 从 traditional gas scale run 的话，从2乘以10的16方 GeV run 的话，你会得到 light star 是一个 LSP，Bino 呢是比它重一点点，但是呢，这个我们的指出来的 interesting point 是什么呢？如果你 run RG 是从 string scale 开始 run 的话，你会发现 Bino 是 LSP，Bino 是 dominant 的 LSP 然后呢，我的 right hand lepton 包括 light star 它们都非常轻所以我们就会预言它们是非常轻的。其实这个情况我们说有个 correlation light star correlation， 这个情况是 predict， 不是说我去找这个参数空间，而是这个 scenario 就 predict 这个情况是这样的一个结果 啊，这个我就不讲反 tuning 的 issue。那么这个我们做 generalization 实际上是什么呢？就是说 no scale supergravity 仅仅在 tree level valid， 你会 gauge can function 和 calculation 都有 vulnerable correction。那这样的话，我们可以考虑什么 ？gauge mass non-zero。M naught A 和 B mu 呢是在 order of like gauge mass 的1%的这个量级啊，就这样一个情况啊。那么这样的话就是说，我们会只有就是说这个情况就会跟那个 no scale 是一个很小的 generalization， 然后考虑这个 effective supernatural supersymmetry， 实际上这个情况是个非常简单的 effective supernatural supersymmetry， 所以这种 scenario 呢依然是非常自然的一个情况。那么下面呢，我就时间也不是很多，我就简单说了一下，我们来找这个情况，是不是能找到合适参数空间？那么就是说，我们要求这个 neutrino LSP 这个参数空间，我们要求 neutrino LSP。consider 这个 LHC SUSY search constraints， 然后 consider B 物理的 constraints， 考虑 Higgs mass range 是122到128个 GeV， 然后考虑了这个暗物质直接探测的限制，然后也考虑了这个Planck 给出的 document density 的话，6会考虑，我们考虑大于或者小于的情况都会考虑。那么这样的话就是说，我们要 suppress correlation， 其实这个时候我们可以计算。不考虑 correlation， 这个 document density 是给在这里面，MER 是 right hand selection 的一个 mass，R 呢是一个 M1 就 binary mass，M1 square over MER square 啊。那么这样的话就是说我们可以计算 density with and without correlation。那么这时候定一个 parameter 就非常重要的是 R phi，phi 呢是比方说 right hand selection 或者 light tau， 那么是 M5 minus M_10 over M_0啊，这个 parameter 非常重要。然后呢，如果这个 R5 呢是5到8% deviation from correlation 大概是大于50%。如果 R5 是10到12%这个时候呢 correlation 实际上就很小了，主要是 annihilation 啊。这时候就是说，如果 R5 大于10%，实际上是通常会定义为8%，但我们定义10%，就肯定是一个Bark region 了。然后这样的话，我们说 Bark region， 我们必须要有一位的这个 well-tamed 的 scenario， 就LSP 呢，基本上是99.99%都是一个 binary 的 component， 然后同时我们要一位的是 Higgs resonance 之类的，所以 make sure 这是一个就是 Bark region。那么这样的话，我们要求真的要求是 R5 大于 10%， 是非常一个保守的一个估计。这样的是给出的结果这个是就 R tau 1 R light tau versus M_10。然后这个 cyan 这个 magenta gray points 呢，它们分别对应的 undersaturated and saturated and oversaturated document density。如果你要求给出正确 density， 就在这条线 magenta line， 那么你要求 10% 在这里，那么你的 M_10 呢是要小于103个 GeV。然后你可以把这个东西 project out 到这个MER 和 M tau light tau， 那么你会发现这个区域的话 ，light tau 呢是小于115个 GeV， 我的 right hand selection 呢是小于150个 GeV。那么我们看实验去看这个参数空间第一个我们看我们直接探测就 LZ1000 的话是很明显能够把这个 parameter space 都给探测到，所以这地方是就直接探测 LZ1000 就可以探测到了。那么另外一件事呢？我们的 CPC 240 GeV 很明显，因为我light tau 是小于115个 GeV CPC、FCCE 都能探测。然后下面就是说还有一个事情，就是说这个情况的话，我们还可以计算 proton decay、proton lifetime 是多少呢？3到4乘以10的3次方年，所以它以后呢的 future hypercase 实验这个参数也是能够观测到。那么唯一的就是说，这个 scenario 预言的如果我不考虑 back particle 的 contribution to G-2 的话 ，delta mu 是很小的。那这跟我们的如果你考虑 BMW result 这个是 OK 的。如果你让 delta mu 有5个 sigma 的5.1个 sigma 偏离的话，你只需要考虑 back particle 的一个贡献就可以了。那么这样的话就是说，这个情况的话，如果我们仅仅考虑不从理论上考虑不考自然性和简单性的话，我们可以考虑这个 PMSM 的话，结果，因为我想我时间可能差不多，就 PMSM 的话，就可能有更多的参数空间，就像这个 LZ 实验呢，就只能 probe 部分参数空间。 然后呢，我们也 check 了啊，它满足所有的LHC 的设置的限制啊。另外一个呢，我会略微啊简单提一下这个 right hand handy 的 Smuon NLSP 的 scenario 啊。其实你现在去 send 的话，他们也感到很多做实验的也感到很迷茫啊，我寻找什么样的新物理？如果我们考虑超对称只是解释 dark matter， 只是解释，如果我们相信 G-5.1 sigma 偏离的话 ，G-2 的话，如果我们只是要求光耦场统一和辐射修正导致电阻对称破缺，然后 forgettable 的反推尼issue的话，那么最简单的 scenario 就是什么？一个 LSP neutrino 很轻，然后右手的 Smuon 很轻，那个这个 scenario 就可以得到。然后这个 scenario 实际上是我们也跟合作者，就他们像包括他合作者的合作者，像 Dimitri 和Johannes 都想给 Sen propose 一个 scenario， 让他们怎么去寻找这个超对称。我想我的时间可能也差不多，我就讲在这里吧。
好，我们首先感谢一下李老师。大家有没有什么问题？我有一个，就是除了这里考虑的这种 slapdown，在这种 gut 情况下的话 ，squark 这些gloilo 呀都是什么情况呢？
这个时候都是取得比较重的情况。
都是全是
对，都是比较重的情况。因为现在是这样的，就是我们收集已经限制很强了。我们现在唯一的就是说，希望有些粒子比较轻，然后我们能 probe。比方说这个 Smuon 这个情况也是，就是说我们需要一些简化的 scenario， 有一些简化的东西我可以去看，要不然反正我因为 Dimitri 也是去Sen访问吧。他是感觉到很多做 senior 的那个实验物理学家都感到很迷茫，我们去找一个什么东西，对吧？其实你从新物理上看，就是说我找个什么东西，必须要一个东西让他去找。那么就是我们在想就 probe 这个事情。
Top squark 就 stop 的话，对这个反 tuning 还是比较重要的。
Top quark 这个反 tuning measure 的话是这是很好的一个问题啊，就是说我们要把反 tuning measure 做一个定义啊，就是说如果你考虑这个。low energy 反 tuning measure 的话，那么 top squark 贡献是很大，所以你会通常要求它不能太重。但是个高能的像 no scale 这个情况的话，它是个特殊的，就是所以它那个时候是可以比较重的。你认为 top squark 很轻的原因，是因为你用了 low energy 反 tuning measure 的 definition 去做计算，就这样的一个原因。
好的，就我也想讨论一下，就是说大家注意一下，其实 LHC 它给这个 squark 呀 gloino 做限制的时候，它其实里面是加了好多假设的。我觉得这个也很重要，对 Moscow 来说，就是大家一看这个图，发现 squark gloino 怎么都到2TU 以上，甚至到3TU，然后觉得好像很重，其实是说，我觉得它里面有很多假设，你如果把这个假设更改一下的话。它也许实验限制其实并没有那么强。
是，这个课程讲的是很对的。这个所有的做理论的可能都知道一件事情，就是说那些 bound 实际上你可以 reduce 大概几百个机位是没有任何问题，对一个具体模型而言，它那个限制像你可以问很多人都意识到这个事情，就这是非常重要的一个 point。对，
好的。
非常感谢您的报告，就是因为刚才那个主持人老师提到这个问题，我也想就是接着问一下，就是您就是那个刚才那个 LSP 的第一个你放的限制图是100个 GeV 左右，然后后来好像到 LHC 就后来的有好几个限制图的到 LHC 又到500个 GeV， 我想问一下您在这两个里面差别是什么？
你说什么？我没搞懂。
就比如说这个
这个只是他们实验，他们做的一个图。
这个也是
他们自己选的，对，这是实验。
到100个。
你
那个中性的那个纵轴也是。
对，他们是因为我们用 slapdown search 都以前也有一些结果，他们一般会从这边开始做。从100以上往开始做。
对，我就是说最高的那个好像到了几百，对吧？
对。
然后
但是你有一些参数空间在这里面，它是在那个
就您感兴趣，就是您这个
在那个没有
在
100
个，
对，
还是在100个 GeV
对，但是这里面我没有讲的特别详细， 实际上这些图的话，实际上都不是我们真正做的情况。像他们是什么？是把所有的左右手的这个 light spectrum 都放进去。实际上我们最近才开始做，我们当然跟高能手庄夏老师在一起合作了，就是说其实这个实验限制比这个还弱一点。我们这个考虑的是比较强一点的实验限制。像因为 LGC 的收集设计是把左右手都放在一起，我们实际上是只有右手的比较轻，左手的比较重。像这个，而且左手 cross section 要大一些，因为左手有 SU2 的 interaction。但我们现在可能会做一个比较更 precise 的一个计算。
哦，好的，好，谢谢你。
好，
好，我们再次感谢一下李田军老师。好，我们有请下一位报告人 Nick Houston。好，from Beijing University of Technology. Okay, let's welcome.
Okay, hello. Right, perfect. Okay, so to start off, let me just thank the organizers for inviting me to give this talk. Yeah, my name is Nick. I work at Beijing Dashi. I'm junior faculty, and I'm going to be talking about some work that we published earlier this year as part of the APEX collaboration. So we have a paper in PhysRevD and another one in Chinese Journal of Physics C, which is talking about dark photon constraints from the APEX cavity haloscope experiment. So let's see. So I can talk briefly about the big picture of what we're doing here. Of course, this is a meeting about dark matter, so I think people already understand the motivation overall. We know in general that very good indirect evidence exists for the existence of dark matter, whether that's anomalous galactic rotation curves or gravitational lensing, CMB observations, etc. But of course, beyond that, we don't really know much, right? Dark matter hasn't been detected, and we don't know the precise details of what dark matter is made of. So this talk is about using a particular experimental technique, which is more and more common these days, which is called a haloscope, which is a resonant microwave cavity, to search for a particular dark matter candidate, which is the dark photon. Now, we've heard a little bit already today from, for example, Liu Jia has talked about dark matter, dark photons. Let me just introduce a little bit of what we need here. So there are, of course, many different dark matter candidates out there in the literature with varying levels of motivation. I would say that arguably the primary motivation for dark matter is just simplicity, right? One of the easiest extensions of the standard model is to add some new dark one, where we end up with a Lagrangian that looks like this once it's canonically normalized. So we have the ordinary kinetic term for electromagnetism. We have a kinetic term for our dark photon. We have a mass term for the dark photon because, of course, it must be massive to give us a dark matter candidate. And we have this kinetic mixing term. So this is the term that's really gives us the interesting phenomenology, because the dark photon field can directly mix with the standard model photon. And the probability of that happening is controlled by this dimensionless parameter chi. So in just perhaps as is familiar from the Axion case, if we have very light dark photon, dark matter, whereby light, I mean like, sub-electron volt masses, we have a particular mechanism called the misalignment mechanism. I have a slide where I'll talk about that, where basically the field is best described as a coherent wave which is oscillating at a particular frequency. The frequency set by the mass of the dark photon, rather than necessarily individual particles. And just as in the Axion case, this can provide a natural dark matter candidate. So there's lots of interesting experimental, phenomenology possibilities here, because for one thing, you're creating single photons, and we already have lots of good experimental technology for dealing with photons. I would say also from a theoretical point of view, it's quite a nice target because the parameter space is broadly parameterized by just the mass and this kinetic mixing parameter there. So it provides quite a kind of like an easily characterizable theoretical target. Now, for people who are familiar with axion physics, you know that an axion can convert into a photon in the presence of a background magnetic field. But in this case, we don't need any magnetic field, right? The mixing happens directly, so it's a little bit simpler experimentally. And also, we don't have any particularly favored value of the parameter space. So for axions, there is a region of the parameter space for so-called QCD axions, which are those axions that solve the strong CP problem in the standard model. In the dark photon case, we don't have that. So since it's a little bit important here, let me just explain a little bit the misalignment mechanism, how this gives us the correct dark matter relic density. So when people were first studying axion physics, they realized quite early on, so I think originally with this paper, that actually there's a bit of a problem phenomenologically, which is that if you consider the equation of motion in the early universe, when the Hubble parameter is large, the field is frozen at a particular value, but then over time the Hubble decreases, and at a certain point it crosses over the constant value that's set by the axion mass. So now this becomes the dominant term in the equation of motion, and the field starts to oscillate, right? And, potentially, this is essentially like the moduli problem that people are familiar with. If you have too much energy density here, it will overclose the universe, which is not good. But of course, if you have the right amount, it just happens to explain dark matter, which is good. So, I'll give a little bit more detail. So in the case of the dark photon, if we have a field which is just oscillating about the minimum of its potential, right, we can write it like this. We'll have some cosine dependence like this. When you insert this profile for the dark photon into the equation of motion, you find that it scales as the scale parameter to the power minus 3/2, which means your energy density redshifts like 1/a cubed, right? So this is the same redshift as you have for ordinary matter. And if you calculate the equation of state parameter, right, you can see, for example, at the top of the potential, this looks kind of like a cosmological constant. So you get omega is equal to -1, and at the bottom, it's more like a free scalar field because the potential has no effect. And so therefore, the average value of the equation of state is 0. And these are the parameters for ordinary non-relativistic cold dark matter. So even though the mass of the field is much, much lighter than what we would normally think of for, WIMP dark matter, for example, you can still have a non-relativistic dark matter candidate. So let's talk a little bit about APEX. So this is the collaboration which I'm part of. So you can see, obviously, there's a lot of names, roughly 25 people or so, all based in China. We have theorists, we have experimentalists, and we're all working together to do some experiments to search for axions and dark photons. One of the nice things I would say, this is just my personal feeling, but phenomenologically, it's quite nice that you can do small scale experiments. People often nowadays, they talk about tabletop experiments to search for dark matter, So that's primarily what we've been focusing on. Now, why did we decide to form this collaboration? Well, there's a few reasons, but one of them is that if we just think, let's say, geographically, you can see that there's a lot of experiments which are searching for axions and dark photons around the world, right? You have many in North America here. You also have many different experiments here in Europe, but Asia is somewhat less represented in that sense. So we thought, okay, there's some interesting possibilities here because this is nice physics. So I've got APEX is here. So for what I'm talking about today, APEX was originally based at Hunan Normal University in Changsha. And then some of the data was also taken at the Institute of Physics at the Chinese Academy of Sciences, which is here in Beijing. And then I think from now, so whilst we're currently waiting for a laboratory to be prepared at Henan Normal University. So while we wait, the experiment is currently based at Anhui University. So, okay, this is just geography. So let's talk a little bit about physics. So I said in the beginning, one of the nice things from a theoretical perspective is that the parameter space is broadly parameterized by just two quantities. So we have the kinetic mixing, this is our chi from before, and the dark photon mass. And there's a few things that we can take away from this figure. One thing you can see, it's very busy, right? There's many, many different constraints. The colored regions are regions that are already excluded by experiments or observations. And there's a lot of activity, right? I'm sure everyone here reads the archive. You see there's more and more papers talking about these topics. And yeah, the white region obviously is what is currently unexplored. So we are focusing on this particular region here where you're talking about masses which correspond to frequencies around about 1 gigahertz. So that's like micro electron volt masses, because this is a region that's quite amenable to this haloscope technology. Right, so let's talk about haloscopes. So we've established already that essentially the dark photon, dark matter behaves like a dark wave, let's say, right? So it can convert directly to photons without the presence of a magnetic field, but the problem is the conversion probability is very small, right? If the conversion probability was not small, it wouldn't be a good dark matter candidate. So we need some experimental technology to try to increase our chances of detecting this. So the haloscope is, let's go back. The haloscope that's an experimental concept. It was first developed by Pierre Sakivi for axion searches. And basically the idea is that when you have a resonant microwave cavity, you can actually enhance the conversion rate from axions to photons and also correspondingly from dark photons to photons. Basically the effect is that the boundary conditions provided by the cavity modify your transition rate, right? So you can enhance the conversion probability, but only at a certain frequency, right? So only in the range of frequencies that are resonant with your cavity. So that's sort of what we're trying to show here. You have a dark photon, comes into the cavity and converts. So we pick up that signal. We have a small antenna here. The signal comes out and it needs to be amplified, first of all. It's going to be amplified because the power that you would expect for a typical experiment is very, very low, like 10 to the minus 24 watts or something like that. It's very small. So you amplify the signal, you digitize it, you do a fast Fourier transform, and then the output from your spectrum analyzer looks something like this, if you're very lucky, of course, and you find the signal. So we can see here, this is a power spectrum, this is the power, this is the frequency, and here we have a candidate signal. It has a certain width, which is inherited from the width of the dark matter velocity distribution, right? It's peaked at the frequency, which corresponds to the dark photon mass here. And we have some background noise here that we always have to deal with. So in principle, you have black body radiation inside the cavity, but you cool the cavity right down, so that's not really a factor. The primary factor that comes, the primary noise that enters is Johnson noise from the receiver chain. So basically because your amplifiers operate at a finite temperature and that introduces their own source of thermal noise, and that's called Johnson noise. So in general also, what you want to do, you want to be able to search it, over a range of frequencies. So you have a rod inside the cavity, you move the rod, and then that changes the resonant frequency. It allows you to scan across the parameter space. So the peak power, so this is when you're on resonance, right? So in other words, when the frequency of your dark photon matches the resonant frequency of the cavity, is written like this. So we have a few parameters here. So beta is the cavity coupling coefficient. So this is basically how strongly your antenna couples to the radiation inside the cavity. You change that by basically just putting the antenna further into the cavity. We have eta, it's a signal attenuation coefficient. So you lose some signal, let's say resistive losses and things like that. As you get the signal out of the cavity, we have our kinetic mixing parameter, we have the mass, we have the dark matter density, We have what's called the effective volume. So the effective volume is defined like this. It's basically just the overlap between the cavity mode and the dark photon mode, right? So you need to make sure that obviously they overlap so that the dark photon can efficiently convert into a photon. QL is the loaded quality factor. So probably maybe you remember from undergraduate physics, you want to have a high Q because that means your resonator has, better performance, let's say. Okay. So in practice, how this actually looks, the way that we have set up for Apex, we have a network analyzer. So the network analyzer sends a signal out, which gets strongly attenuated, right? So through the black trajectory here. So we put a signal into the cavity, and then we measure what comes back. So that enables us to determine the cavity parameters like beta, like Q, for example. So we determine those parameters, and then what we can do is we use the spectrum analyzer to actually measure the power that's coming out of the cavity when the network analyzer is not connected. So we have the cavity here. These are circulators, right? But we shunt them so they function as isolators. So this is to prevent any power from going back into the cavity. And then we have amplifiers. So here, this is a high electron mobility transistor amplifier, here and here. And you can see, obviously, we operate in different temperature stages. The coldest stage here is 22 millikelvin. That's where the cavity is. Right, so in practice, this is how it actually looks. So the white object here, this is the dilution refrigerator, and this is the stack that goes into that. So the lowest temperature zone is at the bottom. This is where the cavity is, and we have some different pictures of the cavity. So the cavity is about, I think it's about 9 centimeters in height and 3 centimeters in diameter, so it's quite small. You can see, as promised, the whole experiment only occupies a small amount of space. And with that, we can get constraints on this dark photon, dark matter. The cavity is made of copper, coated with gold, just to prevent oxidation. Okay, so how do we actually proceed here? So we need to know the parameters of the cavity, right? So if you remember, the signal power depends on beta, it depends on Q, and so on. So what we do is we measure, using the network analyzer, we measure transmission and reflection from the cavity. So that's what these curves here and here, this is transmission, this is reflection. And you fit them to a Lorentzian profile, which allows you to then determine these cavity parameters. You can see the fit is quite good. So we know that the cavity is behaving properly. The effective volume, we can only find that by simulation, right? It can actually be measured. So we have to simulate the TM010 mode in some software. And this is the type of result that we get out of this. And it allows us to numerically determine what the effective volume is, like this. Okay, so then summary of key parameters for the data that we're talking about today. So beta is close to 1. So if you're measuring just at a single frequency, the optimum value of beta is 1. We have a center frequency. It's about 7.1 gigahertz, which corresponds to about 29 micro electron volts. Loaded quality factor is about 10,000. Effective volume is 17 ml. That's quite low. And then our gain, which comes from the amplifiers, we have 88 dB. Once we subtract any losses, we have, okay, eta, this is just an attenuation coefficient. The measurement bandwidth that we were using for this data is 20 hertz with an integration time of 22 seconds, roughly. Okay, thanks. Okay, so, right, let's see how this looks. Okay. So the data that you actually get out from the spectrum analyzer, once you've processed them, look like this, right? So we get power spectra. So you have some figure here, you have the frequency. F0 is the resonant frequency of the cavity, which is here in the center. And here we've rescaled the power excess in units of the standard deviation, right? Just so we can see, statistically what's going on. So a few points here. The mean power when we take these measurements is about 10 to the minus 23 watts. So it's very, very low. Each point here is actually the average of many, many, many measurements, right? So I mentioned on the previous slide, our integration time is about 22 seconds. What that means is for a given data point, we're measuring it over and over and over again. And we want to get, in total, we get something like 10 to the 8 measurements per point. The idea being that if you're dominated by the statistical uncertainty, you want to do repeat measurements so you can bring the standard deviation down as much as possible. Yeah, so the uncertainty here we can see in the analysis is primarily statistical. We get 1.7 relative uncertainty in the power. There are also other systematics, for example, how accurately can you determine the cavity parameters like beta, like Q, like F naught, etc. But those uncertainties are all subleading. They're all certainly below 1% in terms of relative uncertainty. So that's good. That's typical for this type of experiment. And of course, what we can see is there's no, here we're in units of the standard deviation. There's no excess greater than 3 sigma. Right, so everything is contained within 3 sigma, so the result is compatible with the null hypothesis, right? Sadly, we didn't discover dark photon, dark matter. So we need to convert this power excess into a limit on our dark photon parameters. So the way that we do that is you construct a reference signal by taking the dark matter velocity distribution and you convolve that with the detector response. Right, so that gives us our P ref, and for the reference signal, we just choose chi equals 1. It's just a normalization, it doesn't matter. And then what you do is you compare your reference signal to the measured power excess in each bin via the corresponding likelihood, like this. And then up to an overall normalization, you can use this to calculate limits on the parameters. Okay, so let's take a look at the limits. So this is the result that we find. This is 90% confidence level limit. We have the frequency is around about 7.13 gigahertz. Qualified here is another haloscope experiment. I'll talk about that in a second. And we can see the limit for the kinetic mixing goes down to roughly 10 to the minus 13. So this is very zoomed in. So we can get a zoomed out picture which looks like this. So obviously our constraint is here. And then we have a variety of other constraints. So qualified is another type of dark matter. I guess you could call it a haloscope experiment, but they use, I think it's like a reflecting dish. You have Chouquet, which is another one. We have one of the ADMX experiments here, so ADMX sidecar, and also SUPAX, which is another haloscope experiment. And we can see, we're stronger than other constraints by roughly an order of magnitude, right? Which is a nice result. Okay, so I think I can summarize. So yeah, we have performed a cavity haloscope experiment, which is searching for dark matter. Of course, we didn't find dark photon, dark matter, so we just place a constraint. We put an upper limit on the absolute value of the kinetic mixing parameter around about 29 microelectron volts, which exceeds other constraints in this range by roughly an order of magnitude. The plan going forward is from October of this year, so the experiment's based at Anhui University, where we're going to be working on scanning the cavity with the addition of a 9 Tesla magnetic field, so the idea being to search for axions as well. And we also have some ideas for, let's say quantum enhanced measurement schemes. So for example, dual path interferometry, which, okay, if anyone's interested, we can talk about that afterwards. And then from 2025, the plan is to move the experiment to a dedicated laboratory at Henan University. So thank you for listening.
Any question or comments?
Very nice talk here.
Thank you.
I would like to know, so what is limit your available sensitivity?
What limits the available?
This you hope the sensitivity right here, and what is limited enhanced sensitivity?
Oh, right. I see. You're talking about this dual path interferometry.
Yeah.
Right. So, for example, there's a paper which was written by Yang Chaoli, Gao Yu, and Peng Zhihui, where they had an idea to Essentially, for a cavity experiment, you can split the output in two, and then there's a certain type of measurement you can perform on the correlations of those two, output. This is why it's called dual path. You perform interferometry on the dual path, and then it gives you some enhancement with the sensitivity. I'm not an expert on the details.
Okay. Thank you. Yeah.
Okay, yeah.
So hi, Nick.
Hello.
So I have a question about the noise spectrum. So this is normalized excess, right?
Yeah.
So which means it's in principle should be flat.
It's normalized in the sense that we've subtracted the mean power, which is this 10 to the minus 23, and so you're basically looking at fluctuations just about the mean.
So you don't have like a Gaussian profile.
No, because the scan width here is so narrow that you don't actually see the width of the profile. Do you mean Gaussian?
I mean the noise. For the noise, you didn't see like a Gaussian profile because it's a resonant cavity.
Right,
should
exactly.
have a width of quality factor.
Because we're just looking essentially at a very, very narrow portion of that curve, right? So if you look at the full cavity width, yeah, you're right. You'll see something that looks like this. But of course, there's not really much point in looking at the either end because you don't really get good sensitivity. So we just focus on the narrow part that gives us the best sensitivity.
That's true, but for example, for the ADMX, what they do is they in principle will see a thermal noise spectrum. Then they do the fitting using a Gaussian function. Then they check the normalized excess.
Right.
And in here, you don't see such kind of noise spectrum, or?
Well, but are you thinking the noise spectrum that's coming from the change in the cavity response?
Yes.
Yeah, exactly. We don't see it because this is just the very, very top of the Gaussian.
Okay. Thank you.
Okay, yeah.
So I have a naive question about so if I remember correctly, as for the action searches, they sometimes use the superconductivity in cavity to extend their searching region, the mass region. As for the dark photon searches, this kind of superconducting cavity is efficient for.
So actually, for dark photon searches, the superconducting cavity is usually better because you don't need a magnetic field.
Okay.
The problem in the axion case is you need a magnetic field, but then that interferes with the superconductivity.
I see.
Yeah. But here, we don't have a superconducting cavity.
I thank you.
Okay, let's thank Nick again for the wonderful talk. Okay, our next talk, 近代物理研究所的葛博新老师，好，我们欢迎一下。
我看不到激光笔，这个是激光笔吗？
这个是激光笔。
这个下一页，好，谢谢。大家好，我是近代物理研究所柯博新。我首先感谢组委会给我这个机会来介绍一下我们是一个基于加速器的一个来寻找新物理的一个新的实验方案。我们这个实验中呢用到的是极化氢靶。这是我的报告内容。首先呢，我要讲一下，是我们现在在实验中观测到的，用横向极化电子束流打那个氢靶，还有重靶，这个过程中观测到的是一些趴噪，这个趴噪就是实验信号和理论计算的一个非常大的一个差别。然后基于由于有这个趴噪呢，我们想是不是有新的物理在里面然后我们想到的方法是把这个极化电子束流换成极化电子靶来做这个实验。当然 换成这个方案呢，有2个好处，我会在后面的报告中讲。在最后一部分，我讲一下我们在国内的装置上呢，怎么去做这个事情。我首先我想就是因为我前面可能铺垫比较长，前几页，我首先想先把这个事情抛出来，就是我们研究的呢，就是说看在这个电子散射过程中，看有没有就是说除光子之外的其他粒子作为媒介子。其实这是一个相当于第5例的一个寻找。好，我先讲一下这个背景。这个背景呢，就是这个有点长了，就是说，在这个我们这个电子它没有结构，所以这个电子散射呢，它是研究我们强子结构非常好的一个方法。比如说呢，看这个过程，如果这个电子和质子散射，因为我们这个电磁相互作用的耦合常数非常小，所以在大多数情况下，我们呢就是把这个过程呢，就是用一个单光子交换就可以近似的，就是可以描述的非常好。所以以前的弹性散射，包括现在的深度非弹散射，大多数理论框架它提取这个核子的这个结构信息的时候，它都是单光子交换啊，但是呢，就是说我们在实验过程中测量的一个质子的一个量叫电磁形状因子。电磁形状因子呢，它是描述这个质子电磁结构的一个非常基本的量。所以呢，历史上对它的观测是非常多的。研究它呢，就是有2种方法。他们这2种方法，我这个写在这个地方，它2种方法都是基于这种单光子交换的这种图像的。第一种方法就是 Rosenbroth 分离法，它呢就是说是你改变你的入射的束流的能量和探测器的角度来测一个电子质子散射的一个微分截面。从这个微分截里面，你就可以提取出来你的电形状因子和磁形状因子。这个电形状因子我们这报告里面叫 D1， 磁形状因子呢我们把它叫做 GM。然后呢，第2种方法就是说是它是用的极化方法，就是你用纵向极化的这个电子束流来打这个质子，然后测这个墨态质子的这个极化度，你测它垂直于法相的这个极化度和法相平面内的这个极化度，这2个的比值呢，你一比呢，你就能得到这个 G1 和 GM 的这个比值。这个方法就是这种实验呢，方法早就有了，70年代人就提出来了，只不过是实验呢，一直到90年代末才开始做，因为这个墨态极化度的这个测量这个技术上呢，一直到90年代末才发展出来，对吧？就是说，这张图就展示的就是这个电磁形状因子的比值关于这个四动量转移的这个平方的一个依赖关系。这个黑白色的这些数据呢，它是用第1种方法 Rosenbroth 方法得出来的。这些彩色的这些点呢，它是用第2种方法，就是极化转移这种方法得出来的。按理说，它俩呢都是基于单光子交换的这种一个图像的一种方法，那应该是一致的。但是你看到之后，这个差别是非常大的。当时呢，就是说是引起了这个理论上、实验上的一个非常大的一个关注。你看这个实验上，我就来说吧。实验上从2000年发现这个事情之后，后来呢一直在做到2012年，它确定确实有这个差别啊。理论上呢，就是说2000年之后，大家都在研究，有说是有新物理但是呢，最终就是说是有理论家他用一个定性的一个分析呢，他说是最有可能的就是双光子的这个贡献。我们前面一直没有考虑的，因为这个耦合常数比较小，所以大家认为这一项不重要。但是后来呢，认为这个呢差别呢就是由这个双光子交换这个过程来导致的。那我今天的报告呢，其实大家不要被我这张就是带偏了。这张只是就是它引发双光子交换这个研究的一个事件。就是说这个是定性的认为是双光子交换导致的。那么定量的呢，我们就要去研究它。实验上主要是2种手段，一种是我正负电子束流打这个质子把比它的这个截面对比呢就可以提取出来。还有另外一种呢，就是我要介绍这种方法，就是说是你用横向极化的 横向极化的电子或者横向极化的质子也行做实验，然后去测它的一个叫单自旋横向不对称度。这个不对称度呢，如果它是0，就说明单光子交换贡献是没有的；如果有那就是有单光子交换之外的这个贡献。我们为什么说，就我首先简要介绍一下这个观测量吧。我们这样一个考虑这样，首先看左上角的这个图，如果比如说电子打质子，电子是横向极化的，你看这个是跟它的运动方向垂直的这样一个过程。你把现在把它动量和自旋呢都反向，就是反向之后呢，它就变成这样一个过程。这样一个过程，有一些人说这个是时间繁衍，其实它不是时间繁衍。时间繁衍的话，在这个基础上，你还要把这个出没态给坏过来。这个地方出没态没有坏，是吧？但是呢，理论上就是这个是很好的证明了，教科书上写的，就是说，如果你这个过程是一个波恩过程，也就是单波色子交换过程，那这个其实就相当于一个把出没态交换过的一个时间繁衍的过程，对吧？然后我们把这个图呢，转个180度，就变成了这个图。这个图跟这个图的区别在哪？就是说是自旋的方向变了，也就是说，我们可以用这个极化实验改变你这个极化粒子的这个自旋方向，就可以做什么研究呢？要么就是说，如果你确定你是单波色子交换，那你就是发现了时间繁衍破缺的这种效应。如果对于我们这种，因为我们的电磁相互作用，我们确定它不是时间繁衍破缺的，所以呢，它肯定就是单光子交换之外的过程，也就是我们所说的双光子过程，对吧？好，我们实验上呢，就是说是测的呢，就是说是你的粒子极化了，我们测的就是墨态的角分布。墨态角分布它关于方位角呢，它有一个 cosine 的一个分布然后我们把这个我们把它叫做不对称度，不对称度是除以这个你的靶的极化度或者数流的极化度呢，这就是个物理观测量我们测的就是这个东西。这个东西呢，电磁采样中它就是跟单光子交换、双光子交换整幅呢就是这样一个关系，对吧？我们这种实验呢，可以把电子极化、电子数流极化，也可以把质子或者叫核子极化，就是说是从2000年开始一直做的实验呢，就有这2类，大部分呢就是电子极化这种电子数流极化的这个实验，有那个 MIT 的sample 实验，还有 JLab 上的3个什么 Hypax、G0 Q-week， 这个还有德国 MAMI 上的这个 A4 实验，这个实验呢我是参与了的。你看的就是说是还有 JLab 它是极化的是靶，它极化的是中子的，就是氦3的靶，其实中子。大家可能注意到了就是说是这个质子靶极化的呢，它这个信号是10的-2，这个呢电子极化呢信号是10的-5到-6，这为什么呢？这就是我想让大家这个地方能记得住的，就是这个为什么这么小？你从这个关系上来看的话，它是这个信号是个10的-2，是吧？为什么我们测出这个这么小？它是因为你这个横向极化的电子做实验的过程中，它有一个相对论压低的一个效应基本上就会让它变得很小，10的-5到-6。OK， 就是看那个实验数据之前，我先讲一讲理论上它算这个是怎么算的不好意思，我跟大家强调一下，就是说这个观测量它只是跟双光子交换的虚部相关的，那我们只要把虚部算出来就可以了。虚部怎么算呢？就是说双光子交换它是这样一个过程，电子跟质子呢先交换一个光子，然后那个质子呢它就会变成一个中间态，它到了一个中间态，中间态有可能是质子本身，也有可能是其他的更高能量的态，然后再交换另外一个光子，那这个中间激发态回到了质子，对吧？回到质子，你的这个整幅的虚部怎么算呢？就是你这个费曼图中间凯刀呢之后，这个 x 表示中间态，对吧？你把所有的中间态都考虑到了，在相对应的运动学空间呢积分，然后你就能得到这个振幅的虚部。这是基于这个腰正性的一个计算，就是它们基本上没有它没有模型依赖。唯一不确定的就是说你中间态你算的时候，你考虑的是哪些中间态跟真实情况是不是一致？再就是中间态的这个振幅你带进来的是不是准确的，是不是对的？我现在就介绍一下有2个组的一个计算，最早的呢是2004年，一个是帕斯奎尼，他是意大利的一个理论学家，还有美因茨的维特哈根2个人呢，他们就是 算的时候，它只考虑中间是质子态，所谓的态性态，还有所有的派恩态，包括这种共振的，还有非共振的都加进来。这样算的时候呢，如果是质子态的时候，那很好算，你只要把电磁形状因子带进去，这个只需要电磁形状因子，那我这个振幅我就知道了。那派恩态呢，它是带的是这个美因茨的一个数据库，麦的数据库，它里面的这些振幅呢，就是派恩的这些振幅呢，是通过对实验数据，就是电子产生 X， 还有光子打靶产生 X 这些实验数据进行分波分析得出来的。第二个呢是更近的，就是去年的一个计算。去年的一个计算呢，它是也是当然是质子态是考虑的。它除此之外，它考虑的是更高能量的这些 X 的呢，就是能量更高。它的这个实验数据呢，主要是来自于对这个 JLab class 这个实验的一些分波分析得出来的。这是两种技术两种输入，其实它的后面的套路是一样的然后接下来我就是看一下这个实验和理论的对比。这是第一种计算，这是第二种计算。这一行呢是前角区的这个小角度的实验数据，这个是大角度的实验数据。这些比如说是美因茨的实验数据，这个点呢是 MIT 的实验数据。你看到，就是说主要的信息呢，就是说实验跟理论呢差别非常大，对吧？这个去年的最新的实验结果差别更大所以这个地方呢就发表出来，我当时参与的就是这个蓝色点的这些测量的工作出来之后呢，我们就觉得很奇怪，反正是就一直对这个事情一直是在考虑。另外一个就是同样的实验呢，我用同样的横向极化电子打的不是质子靶，打的是重靶。这个在 JLab 做过，就是 P-Rex 的 C-Rex 实验呢，它是2012年做的时候，他发现那个电子打在铅靶上，跟这个理论呢差别很大。它这个理论呢跟我前面介绍的理论稍微有点差别，它是基于这个光学定理的就是差别非常大。然后呢，他们过了大概10年，又做了一次实验，这个差别还是这么大，20倍的 sigma。也就是说，这个现象不光是在电子质子散射中有，就是电子重离子散射中也发现了。好，那我们就是说一说我们的思考，就是说这个过程呢，那我们为什么观测了这么大的差别？第一种就是说你中间的还有其他一些中间态呢，你没有考虑全。第二种就是你带入来的这些振幅呢，产生振幅呢，可能需要改进，对吧？但是呢，我们跟就是做理论的 Pasquini、Verhagen 都讨论过，就是说这个地方我们的四动量交换呢，大概是0.1或者0.01这个量级，就是这么小的四动量转移呢，它中间呢也就考虑核子本身还有派恩态呢，其实也就足够了，其他的贡献应该是非常小，可以忽略的。但是呢，还是有这个差别。那我们就想，就把脑洞放大一点，是不是有新的东西，对吧？你除了这种，比如说我们考虑的标准模型之内是交换2个光子，那有没有可能是标准模型之外的，把一个光子换成爱光子或者轴子之类的，对吧？甚至呢，就是说单波色的交换过程，但是交换的呢，这个是一个 CP 破缺的一个波色子，对吧？这就是新物理的内容。但是呢，用电子打质子、电子数流打质子这些我刚才介绍这些实验数据来说这些说新物理的事情呢，你还是不够。因为啥呢？就是我刚才说过，一个是在这个地方的由于这个非围绕 QCD 引起的这个理论的这个不确定度太大。再一个呢，就是说我们实验上做起来还是很困难的，就是说你的这种信号呢是10⁻⁵到10⁻⁶这个量级，对吧？好，我们现在的新的想法就是说我们之前是用极化的电子打质子靶，我们现在是用非极化的质子数流打极化的电子靶。那有什么好处呢？第一个，我们看一下这个图，这是数流能量，质子的数流能量，这个是它的四动量交换。就是说，在这种逆运动学过程中呢，这个四动量交换呢，它是非常小。我们刚才说过，就是一般实验，我们之前的是四动量转移是0.1、0.2这个。现在呢，你看，就是我们国内正在建设的 KF 上，你看对应的这就是低了好几个数量级10⁻⁴是吧？这样就是说这个四动量转移就非常小。我们这个电子靶怎么来？不好意思， 我们这个电子靶怎么来呢？电子靶就是说我们在粒子物理、核物理中有一个非常成熟的一个工具，就是极化氢靶。极化氢靶就是你用电磁的方法，你就把氢原子呢给它极化了，里面的质子也是极化的，电子也是极化的。到目前为止呢，大家都是用里面的极化质子来做实验。我们就想用里面把它用这个极化氢靶里面的电子把它做一个电子靶来做这个实验。好，有什么好处呢？这是我刚才说的用电子束流打质子靶的两个困难，是吧？那我们用反过来之后就都可以解决。第一个是 Q² 非常小，数量转移非常小之后，小好几个数量级，那中间态呢只可能是质子，没有可能是其他态。那理论上算的时候就非常干净，你只要把电磁形状因子带进去，你就能把这个双缝的交坏的这个整幅算得非常准确。另外一个附带的好处呢，就是说我这个是用靶，我刚才说的就是你用横向极化的电子束流做实验的时候，它有一个相对论的一个压低。我们现在用的是靶极化静止的电子，所以这个没有这个效应之后呢，信号就会增大3个数量级。这就是主要刚才我说的就是主要的想法了。我们现在看一看就是这个实验呢怎么做。我这个地方展示的就是一个探测系统。我们因为这个地方如果把极化靶画出来就比较乱了，所以我就用一根线，这个表示极化的氢原子，这样从上往下来之后，这是加速器中的质子束流，在这个靶室里面它进行散射，弹性散射啊，散射之后那个反冲电子，我用黄色的这个线表示，反冲电子出来之后，从靶室里面出来，我们呢首先用一个屏蔽墙，中间开孔。只让这些电子的在电子这个几何接受度内的粒子让它过来之后，我这个地方加一个环形磁场，就像一个甜甜圈一样的一个磁场，然后呢它就会偏转。我们这个磁场设计的呢，就是让这个不同能量、不同角度这个电子呢，它就是聚焦在一个点上，这样呢其他的本底粒子呢，它就基本上不会走到这个地方，这样就是我们可以实现一个非常干净的一个探测。那这种实验在我们国内怎么做呢？这个是我们现在国内静物所正在建设的一个国内大科学装置。你看，这是现场的一个图片，谢谢。就是说明年就会建成出数。我们呢可以在这个地方作为一个内靶实验，放在这个地方做实验。也可以在我们现在正在推的就是将来 EICC 的这个 P-ring， 就是这个质子环里面来做实验。这个的质子束流的能量呢，可以达到9个 GeV， 这个呢可以达到26个 GeV， 啊。好，最后呢剩几分钟，我来讲一讲我们就是说是现在我们需要用到极化靶。我们国内的这种极化实验呢，其实之前是空白的，基于加速器的极化实验真的是空白的。我们现在静物所呢有一个团队，就是说是个跨部门的团队，我们正在呢就是研究极化粒子的产生之后呢，加速过程中如何保持极化度不丢，还有呢就是极化靶。我们这是我们的团队你看这个呢是极化粒子源，因为它是起步最早，所以现在呢已经是在安装调试阶段，估计明年就可以出来极化粒子。国际合作方面呢，就是国际上这个经验比较多，所以我们和德国还有意大利的都现在有合作。这个和德国的合作比较长，时间比较长了。我在那边呢是做博士阶段，就跟那边一直是保持联系。今年年初呢，我们是开了一个静物所跟 GSI 的一个关于极化物理的一个研讨会好了，我就讲这么多。我再就是总结一下，就是说我们在实验上呢看到就是横向极化电子打那个质子靶还有重靶呢，看见就是非常大的理论跟实验的这个偏差。那这个偏差呢有可能是新物理导致的。那我们用一个把电子束流换成电子靶来做这个实验呢，有2个好处：一个理论上非常干净，再一个信号呢能增加3个数量级。那这种就是对于新物理探索，这是一个全新的方法了。我们觉得是值得在国内的大科学装置上来推进的。好，谢谢大家。
我问一下，你们这个极化靶是连的是他们那个广东那个靶，那个在实验在广东是吗？就是广东那个加速器那块是吗？
对，就是我们静物所呢在兰州有加速器，兰州的那个加速器呢，就是说能量到动量到3.7个 GeV， 但是呢，由于这个加速器之间匹配问题，它现在质子数一直没有加速出来，原则上是可以加速。那这个呢是我们静物所在惠州新正在建的一个加速器，你看明年就要出数了，甚至要做第一个实验，所以呢，将来是打算就是在这个加速器上。
我好像听说是在惠州建这个，那你们这个基本上就是本来就是应该研究重离子的吧，就是没有新物理的，至少目前还没有。但我知道国外有很多这种 fixed target 的这种工作，你可能听过。
对 fixed target， 因为我之前做的就是说是质子打质子的这种强子加速器上也工作过，在电子加速器上也工作过，所以之前的这种 fixed target 来寻找新物理，现在到目前为止，比如说精确测量那个电弱混合角，对吧？这是和我们比较类似的，只不过它是精确测量混合角。我们提出来的呢，就是说是用强子数流来做电磁散射，用的是电子极化靶，这是一个全新的国外没有的一个实验。国际上的 fixed target experiment 基本上都是
电子打质子，我记得你们是质子打电子。
国际上大多数实验就是电子打质子，电子数流打质子靶或者是氦三靶这类的。我们现在呢反过来，我们的数流是质子，靶弄成电子，这是之前从来没有做过的。
那这个就是说质子的话，它可以能量加速的比较高，你的能量比较高。那你们有做什么模拟啊之类的，看一下它可能比如说精度啊，在哪一些能区可能分辨率比较好啊之类的吗？
我们实验上呢，就是做过的模拟就是这个探测装置了。我们觉得这个探测装置可以把质子电子弹性散射势力呢，测得非常干净。你看有几何的开孔的这种屏蔽，还有这种磁铁的这种挑选，就是可以弄得很干净。至于就是说哪个能量上它的这个sensitivity 最高，我们就是说是要理论上要算一下，把那个新物理的贡献加进去，看在哪个能区呢，它是和标准模型的这种信号呢差别最大。我呢就是说从去年到现在呢，就是跟东南大学张永超老师也联系过，张永超老师对这个很感兴趣，他答应给我算。还有廖毅老师，他们呢也是
可以找一下国科大的马腾，我记得他做过这个 fixed target 的，是跟国外的 collaboration。国科大的马腾。
好，谢谢。
好的，谢谢。
我问一下，你这个不自洽的情况这么久的话，没有人用新物理去解释吗？难道是或者说这些新物理模型去解释都被 excluded 的？
就是说是这个实验数据啊，李老师您看，这也不是这么久，它比较新，
对做新物理的来说，应该是很快呀，就是说那个几年已经算很久了。
不好意思啊，这个总是把键摁错。就是说您看这个结果呢，就是说非常大的这种差别的结果呢，我们是2020年看到的，到现在也时间不是特别长。之前这个是2000年附近这个 MIT 的工作，它是有差别，但是差别不是特别大。再就是刚才我说的，就这个吧，还是中间态，大家就是用电子打质子的这个过程呢，大家好多人还是觉得这个差别主要来自于这个。
就中间态是这个没做好，是这个计算。
对，所以大家觉得还是要从这个 QCT 这方面去解决。
实际上是大家还是认为就是一个，就像其他的有一些那个，也是大家觉得可能就是 nuclear physics 之类的，但可能这里也许就是简单的 QCT 的一个原因。
但是呢，就是我跟做理论的 Pasquini 和 Weidhagen 都讨论了，就是说他们已经考虑了质子态和派 n 态在 Q² 是0.1或者0.0几个 GeV 的情况下，他觉得考虑派 n 态和 n 态已经就足够了。
我也是这样感觉了。
所以为什么就是我们后来觉得是不是有新的东西在里面？但新的东西在里面，你们现有的这个1P 的数据呢，你又没有办法去说这个事情，因为有这个 non-positive QCD 的 这个不确定度在里面，对吧？所以我们就想，反过来就有我说的这两个好处，这个理论上很干净了，没有这种 QCD 的这个不确定度。另外一个呢，实验上好做很多，信号增大3个数量级。
好，谢谢，非常有意思。
好的，因为时间关系啊，我们就讨论到这里啊。如果还有问题的话，我们线下再讨论。好，我们再次感谢一下高老师给大家做的精彩报告。好，我们有请我们最后一位老师袁瑞老师，他来自上海交通大学李政道研究所。好，大家欢迎。
好，非常感谢也很高兴今天有机会能够在这里给大家介绍一下我们这个 DarkShine 实验组的一些进展和就近期的一些结果。那就是我们知道这个物理学的大厦自从建立以来头上就一直是有乌云的。19世纪末20世纪初这2朵乌云就后来催生出了量子论跟相对论嘛，然后到现在21世纪我们说有这个暗物质和暗能量。那其实从天文观测的角度呢，为这个暗物质的存在提供了很多有力的支持，但是我们仍然会希望能够从粒子物理的角度，就是研究暗物质粒子的存在与否以及它们的这个性质。那其实也陆陆续续的这个设计出了很多实验，当然其实讲白了，设计实验就是针对我们这个暗物质粒子和标准模型粒子之间到底可以以什么样的方式去发生反应或者发生作用，然后就也相当于从不同的这个方向去读这个费曼图，那就可以设计出对应的这个实验。然后我们整个这个实验的理论背景，然后当然在座各位都是很资深的这个暗物质方面的专家，我就不仔细讲，就quickly go through 一下这个freeze-out 的机制，它可以允许这个暗物质存在于很宽的一个这个质量的这个区间。然后当然我们对这个 WIMPs 的这个理解就是相对深入一点，也有很多实验已经有了这个很好的这个结果。但是我们对于这个 light dark matter 其实仍然有相当大的这个空间等待我们去探索。那么在大部分的这个 light dark matter 的这个模型当中的预期，这样一种就类比于这个光子在 standard model 中的作用，就称之为这个暗光子的一种媒介子，然后作为暗物质粒子间相互传递相互作用的一个媒介，并且也是连接 standard model particle 和这个暗物质粒子之间的一个桥梁。那么比较直接这个引入方式就是引入一个这个额外的右翼对称性。然后我们这里用的这种 minimal 的 dark photon model 呢，就是含有3个自由的参数，包括它的质量，然后这个混合epsilon 的混合系数，以及就这个暗物质到底是否是只衰变到这个 dark sector 还是衰变到 standard model 的这个 particle。当然这个暗光子的产生和湮灭的这个模式也不止一种包括这种什么产生跟衰变模式不止一种，包括这种湮灭产生，然后质而湮过程，然后我们 DarkShine 上找的这个组合就是通过这个认知辐射产生和不可见的这个衰变模式，然后相比起这个可见的衰变模式，就是到 standard model particle 的我们这个不可见的衰变模式就是少了一个这个暗光子和 standard model particle 的这个顶点嘛，然后就是可以不那么被 suppress， 然后这个认知辐射产生方式呢，也就意味着它是一个固定码实验，所以简而言之，就 DarkShine 是一个通过电子打靶来寻找暗光子的这样一个实验。然后既然是电子打靶，需要一个这个电子的源，在上海有一个上海 InX 射线自由电子激光装置，然后他们这个缩写叫 Shine， 其实也是我们这个项目 DarkShine 的这个名字来源的这个一部分原因吧。然后他们预期可以提供这个8个 GeV， 然后重频在1兆赫兹的这样一个超高重频的单电子数流，然后他们的整个工程建设的这个时间线跟我们预言的这个时间线其实也是挺 match 的。然后他们大概位置就是沿着这条红线，然后旁边这个圆圈就是上海光源，一个这个同步辐射装置。对，整个DarkShine探测器的设计就是基于我们信号过程和背景过程的差别。然后信号过程很清晰，对吧？我有一个这个电子在打完靶之后，它自己还剩下一部分能量，然后同时会有一个带走了大部分能量的这个暗光子，然后同时它不会被我剩余的探测器探测到，也就意味着一个很大的这个 missing energy momentum。然后这中间这张这个表上是显示了我们主要的这个背景过程相互relative 的一个比例。然后当然这个最 leading 的其实还是 Bremsstrahlung 这个伽马。但是其实这部分不是最难处理的，因为这个伽马只要它角度 OK， 它总是会在这个电磁探测器里面沉积能量的。相比之下的话，会有很多一系列的这种 rare process， 包括 电子核还有光合核，还有这个 Bosch 的这个伽马，然后 conversion 到一对 mu， 然后呢，它们在整个探测器里面，就前面的部分，包括电磁量能器和静电探测器里面，它的这个表现其实跟信号是很像的。然后所以说我们后面加了一个这个强子量能器来排除这类势力。然后另外还有跟中微子相关的这个产生部分是经过计算和验证是对于我们的这个实际上是可以忽略不计的。那么这是我们最新版的一个，可能有老师之前听过我们这个组的报告，这是我们最新版的一个3D 的一个模型示意。当然这里的话，为了方便看，其实它相互就3个子探测器之间的这个比例其实并不完全正确的哈。然后总共3个部分，第一个经济探测器的部分，然后电磁量能器，然后最后这个大的是强子量能器。此外还有当然配套的这个磁铁啊，然后 DAQ 还有这个 trigger 的这个系统。除了这个硬件的设计以外，我们整体现在合作组也有了一个可以说相当完善的一个软件框架，然后包括从这个势力的产生，然后我们还有不同的模式，从 CareHub 直接读它的产生的这个，或者从 MetaGraph 里面直接接进来也好，然后包括到整个探测器的模拟，包括数字化，还有后面的这个分析重建等等，然后整个 framework 是基于这个 Gen4 和这个 X 的。然后同时，我们合作组在去年初的时候也上线了第一篇这个，应该说这个 expected 的这个灵敏度的这个结果，可以看到我们在这块，对，我们在这个100兆电子伏特往下这个区域，其实还是有很好的这个灵敏度的。然后同时这些结果也已经总结，包括加上前面的这个detector 的这样的一部分，也总结成了我们的。概念设计报告，然后在上个月已经上线到 archive 上了，然后有兴趣老师可以看看，然后提供一些意见。对，然后同时这个虽然我们说它目标是通过电子打靶寻找暗光子嘛，但是其实它也是对其他的很多种不同的 BSM 的粒子，其实也是有这个探测的潜力的。然后另外我们也考虑过，比方说这个扇装置它如果可以提供这个正电子的话，那么比如说这个正电子打靶，然后也同样也是寻找暗光子的情况下的话，它比电子打靶就多了2个这个S channel 和 T channel 的这个湮灭的过程，对。然后同时对于这个limit 来讲的话，它会有一个correspond to 这个入射能量的一个往下的这个区域，可以获得更高的一个灵敏度。然后如果我们对这个正电子的这个数流可以调整它能量的话，那么其实也是可以做一个更精细的一个扫描。对，然后介绍完前面的部分，下面是关于探测器的这个研发的一个进展。然后这个是Gen4 导出来的这个图，然后这里的话三个子探测器部分的这个比例就是正确的，可以看到其实前面 tracker 的部分还有这个电磁量能器就滤框，它是被整个大的这个强子量能器给环绕在这个里面了，对。然后首先是这个 tracking system 的这个部分，然后我们整个 tracker 使用的是这个 ACLGAD 的硅条探测器，然后作为整个这个技术，然后包括在靶前方区域的7层 tagging 的 tracker 和靶后方的这个反中区域的这个 tracker， 然后每一层的话是由2层这个sensor 以稍微错开一个角度来组成的，然后相互之间有一个这个0.05度的这个错位，然后在水平方向、垂直方向分别是10到60这个微米的resolution 的要求，然后这里右边的就是结构的一个示意图哈，然后左边是我们测试用的这个一个样品的一个照片，然后还有中间是一些模拟的这个结果，包括它在这个测量 momentum 上面的 resolution 等等。OK， 然后这里是我们在我们就理所的这个大名就在上海的这个实验室里面已经搭建起了这个测试系统，然后探针台，然后旁边是测出来的IVCV 的一些特性啊。然后当然之前也有去别的单位，这个是在高能所做的一个测试，就是做的一个扫描，就是对沿着这个2条线路去扫描这个strips， 然后给得出来的一个结果，然后对位置的分辨率的一个研究。然后对于电磁量能器来说呢，整个电磁量能器是用这个纯的硅酸乙卤这种晶体做设计的。其实这个晶体 它的光产额啊，然后光产额很高，然后衰变时间相对较短，然后有非常出色的抗辐照性的。然后这种晶体就纯用这种晶体做这种探测器也不是没有，但是基本上是在比如说核医学领域，就它们的其实尺寸是很小的。然后像我们这里的话，其实这么大尺寸，然后完全用这个设计的电磁量能器，应该在粒子物理这块还是第一个做出这样的这个设计。然后整机的话大概是一个半米见方，然后每一个单元是2.5乘2.5，然后乘4厘米的这样一个条，然后全部 XY 方向是21乘21，然后纵向是11层。这边是这个晶体，还有包括后面用 40PM 直接读出，然后以及后面电子学和冷却系统的一个位置关系。那么层与层之间做了一个小的这个错位，用来保证它的这个死区几乎是没有的。然后这边是我们对于，因为实际现在这个工艺上来讲，这个晶体它可以做的，甚至可以做得更大一点。但是我们为了保证它的这个颗粒度，所以说我们对它到底要怎么去分块大小做了很仔细的这个研究，关于这个能量的 resolution， 然后得到的一个结果。然后目前这个可以说是结合了成本和这个模拟得出的效果最好的一个颗粒度的一个组合。OK， 然后这个我们也是。对于这硅酸乙醯晶体做了很多的研究，然后就之前包括对于这个晶体 unit 单元的一个测试，其实已经做了很多了。然后这里放的照片是之前也是借助这个 CPC 在 DESI 做测试的一个机会，然后我们对于一个2×2的一个小的模块，然后做了一个数流的测试。然后此外的话，因为我们之前提了这个电子源过来1兆赫兹嘛，所以其实对于这个电磁量能器来讲的话，它需要具备这个同样重频的这个响应，所以有专门的去为它做了一套这个电子学的这个读出系统。然后这个单独的这个工作也已经是投稿到了那个 JINS 的，然后正在这个 review。然后当然这个结果近期也是召开了一次那个专家的一个论证会，然后也是效果比较好的。然后对于强子量能器的部分，这个强子量能器作为整个探测器最大的一块，它其实除了本身要实现它的物理目标以外，它还有工程上其实可能还会遇到很多限制，包括在未来的这个实验装置的实验大厅里面怎么能把它放得下，然后就对此做了一系列研究，因为通常来讲肯定是越大越好，对于物理来讲，对吧？但是对于工程来讲，它是另外一个方向的事情，所以我们对它的整个尺寸上可以存在的几个自由度吧，包括它整体的尺寸、横向的尺寸，包括里面，因为这里强子量能器用的是一个铁吸收体加塑料闪弱体这样交错排布的一个设计，所以里面铁其实占非常dominant对于重量的这个贡献。那么对于这个铁的吸收体怎么去排布，然后我们也做了仔细的研究。这里我们采用的是一种吸收体在整个探测器前部用了一些比较薄的，然后在后端用了一些比较厚的这个吸收体的这个设计。这个是由于我们因为之前说过，我们对于主要是想要去排除那些含有中子、含有妙的这些势力，然后妙的当然相对而言好处理一些。但是对于含有中子或者这个其他中性强子的这种势力呢，我们仔细的研究了我们这个遇到的这个 background 里面它可能存在的这个能量分布的这个区间，其实它是从然后几十兆电子伏特到几个 GeV 的这个能量范围之间都是有的。那么对于低能量的中子和高能量的中子，其实我在探测器里面敏感的这个区域是不一样的。对于高能量的这个中子，我们需要有更多的这个吸收体去让它能够 shower， 然后让我们有这个足够的shower 出来的这种粒子可以去探测。然后对于低能量的，如果它太厚了，其实前面的话可能它就全部沉积在这个铁里面，就没有办法去怎么说呢？就是可能我探测器没有收集到足够的信号来排除它，所以总的来说，我们最后就提出这样一种hybrid 的这个设计。然后此外，因为我们之前提了，我们整机的这个尺寸可能会受到一定的限制，因此我们在电磁量能器的周围又增加了一圈我们叫 side H core， 就是侧边的这个强子量能器来保证它的这个接收角。对，然后右下角就是我们从模拟上得到的它对各种这种主要中性强子的一些排除，当然这个数值叫做排除的，就 Veto efficiency， 就排除的失败率，就是这个东西应该是越低，然后它的这个排除效果是最好的。然后当然这是为什么直接研究对这个粒子，因为对于这个强子量能器来讲，我 研究它对于这个粒子排除率，其实一个 event 的排除能力，其实就是相当于它对里面这个粒子排除能力的一个 combination 嘛。然后强子量能器这边的硬件也做了很多的这个测试，这里展示的是一些包括材料，包括我们实验装置。然后这个是75厘米长的这个塑料闪烁体，然后因为用的是这个波长位移转换光纤的读出模式，然后所以这里是这个光纤直接耦合到这个 silicon PM， 然后其实当然实际操作的时候，外面会有一个用3D 打印出来的这个结构来保证它的准值啊等等。然后这里2个实验。暗箱里面的实验这个 platform 就是对应了一个光产额的和一个 noise 的这个test。其实关于这个东西类似的讨论在这2篇报告里面很多，但我们在做这个之前，其实一开始没有这样的feeling， 就是我需要去做它的这个 noise 的这个到底有多高。但是最后我们发现。即使 common sense 里面觉得这个塑料闪烁体的 noise 是很低的，但是实际上我们在当前的实验环境里面，如果说我要做一个这个 noise 的这个突破，它肯定会有很多的成分混在一起，包括这个能用这个曲线 fit 出来的这个宇宙线的这个残余的部分，然后包括前面的到底是环境还是材料本身，然后我们都做了一个很仔细的研究。然后另外对于这个强子量能器，它虽然没有专门去配套设计电子学，但是我们用了其他组已经研发成功的一个电子学。相对而言，对于这重复频率的要求低一点，然后用在我们的这个批量探测上。然后总体来讲，我们3个子探测器的这个预研的部分已经基本进入了从这个 unit 的测试性能测试，然后到一个 mini prototype 的这个研发的这个阶段。然后除此以外，我们也一直保持了跟这个SHINE装置团队的密切的沟通联络，然后及时的去汇报我们的进展啊，还有跟他们这个工程方面的一些联络。对，然后总结来讲的话，这个 DuckShine 就是一个高透明单电子打靶的一个固定码实验，然后目的是寻找暗光子以及其他的各种这种 BSM 的这个 particle， 然后我们的第1轮的这个灵敏度的一个结果也已经发表了，然后同时在过去1年里面3个子探测器加上电子学的一个部分，投稿了4篇文章，然后其中有2篇已经发表，然后电磁量能器的是被接收，然后电磁量能器的这个电子学是正在 under review， 然后同时我们的这个 CDR 也已经上线。好的，谢谢老师。
我们感谢大家，有没有什么问题？
好像你最后用的是这个硅基光电倍增管是吧？
对。
那前面你做的电子学是为光基倍增管前面做的呢，还是后面做的？
就是全是后面的，就是
后面
这块板子上，另外就是放的这个 silicon PM， 然后这后面整个电子学就是读出 silicon PM 的一个。
那光基光电倍增它本身有自己的这个后面的电学系统，为什么还要去做它
？silicon PM 它配套的这个电子学系统就是很简单的，就是只是一个读出嘛。因为我这边的话，我其实未来会是。比方说电磁量能器有5000条，应该5000个 channel， 然后我需要，当然现在的这个设计只是为了能让它达到这个1兆赫兹的这个读出，然后后面其实还需要据此去研发新的这个 trigger。对。
第二个问题就是你前面你是一种量能器是吧？不是量热器是吧？
对，量能器。
量能器就是你是工作在这个连续的这个。驱动下还是这个脉冲驱动下的这个，就是你是用电子去打光子是吧？
电子打靶，然后
打靶，
对，
打出来暗光子，
对，
暗光子再进到你的闪烁体。
那个暗光子我们认为是不可见的衰变，就那个暗光子的话不会跟我的探测发生作用，但是 OK， 但是它会剩下，但是它会就是那个电子还是会带一部分能量，以及它还有其他的这个正常认知辐射的光子啊等等。
就是要扣掉的吧？
对。
也就是说你认知辐射以后，就是再打到一个闪烁体，闪烁体产生一个信号，再进到你这个硅基光电倍增管，是这个逻辑吧？
对。
就是那这个要求，这个你闪烁体要求很高的这个能量这个阈值啊，你否则闪烁体闪烁不出来啊，对吧？
其实因为这个用的这个电磁量能器这边用的硅酸乙卤，它就是光产额是非常高的。
就是它的这个能量，这个光子的能量，就是你要沉积的能量比较高，才能够闪烁体才能发光嘛，对吧？
在我们这个 context 里面，其实它不需要很高，
大概是什么个量级？
就是兆一微量级或者以下的，其实都可以。
兆一微的可以是吗？
对，兆一微已经相对而言已经是很高的一个。
不，兆一微是比较高了，K 一微行不行
？K 一也可以。
K 一你看好，谢谢啊。
我想请问一下，你们这个探测器现在设计的这个方案的成本是多少？
看一下这个能授权说这个话？哎，现在是这样的，因为我们这部分可能是1000万量级的，然后后面这部分强子量能器，因为这个尺寸还没有最终决定下来是这么大还是会更大一点。对，反正是这个量级往上吧，因为同类型的实验其实差不多也是这样。
好，没有看到问题。好，那我们再次感谢袁瑞老师。
谢谢。
宋老师有没有什么要宣布的？好，那我们注意一下，我们下午2点钟正常开始啊。好，我们最后感谢一下我们早上所有的报告人。
请下午发言的王少江王老师、李然李老师将您的发言 PPT 拷贝到控台，谢谢。各位老师，我们今天的午餐和昨天是同一个自助餐厅，在1楼的艺景厅 A 座客梯下去左拐，谢谢。
say so. Maybe it's time to get started. 让我们先欢迎下午第一个报告人，中国科学院大学的郭和科老师。然后报告题目是Dark Matter Detection with LIGO and 太极天晴 Lisa。
好，谢谢介绍。我是郭艾科，来自中国科学院大学。然后我主要介绍我们这几年的工作吧。当然，有些老师可能已经听过，可能不止一次这个报告了。当然里边可能会有一些新的东西加进去。我的研究的话，主要是围绕着用引力波来探测基础物理的啊，然后当然也包含探测暗物质的。引力波的话，最近几年的话是取得的在实验进展方面有很多的相关的重要的一个发展，比如说地面、LIGO 空间，我们的太极、天晴以及Lisa 以及脉冲测的阵列方面。都有了非常多的相关的一些进展啊。昨天罗子仁老师有过相关的一些介绍啊。今天陈翔老师可能会介绍一下月际引力波相关的探测。当然除此之外呢，还有探测原初引力波的阿里，比如说阿里 CPT 以及 BSF 以及高频引力波，比如说我们会务组的孙春老师他们的一篇综述文章。 噪声来类比一下。如果我们考虑噪声的话，这2个探测器它大部分噪声是那个好的噪声它是不相关的。这样的话，我们就可以想象把这2个探测器想成2个随机数产生器。这样的话，它们之间没有任何关联。然后，如果我们做互关联，然后把这些数据相加的话，你会发现它增长的非常慢，类似于一个随机行走。但是如果有一个东西它可以同时影响这2个探测器的话，然后我们再做这个互关联的话，你会发现它这个就增长的非常快了。所以说，我们就可以用这种技术很好的这个增强这个信噪比。我们基于 LIGO， 我们是大概在19年完成了基于 LIGO O1 数据一个相关的一个探测。这个红色的曲线的话是对于这个暗光色耦合做的一个 upper limit。当然我们在做这个 upper limit 的前提就是说我们审查了所有可能出现的这个outlier， 就信噪比比较强的那些信号，然后逐个去排除，然后没有看到信号的前提下，就做了这么一个 upper limit。在我们后边加入 LIGO 之后当然有更多的组去加入我们的探测当中，比如说那个安卓他们那个 BSD 的方法，他们会得到一个稍微更好的一个结果。这是我们目前基于O3最好的一个相关的一个结果。我们在明年的中或者会有一个更新，利用 O4A 数据的一个相关的一个结构，然后在今年末的话会有一个利用 O4 所有数据的这个对这个探测现状的一个更新。到时候我们看一下到底是有发现还是那个更好的一个 upper limit。当然，在这个领域当中，其实大家可以看到，各个探测器就是已经都开始对这种超轻暗物质进行相关的一个探测。当然，这 LIGO 的话是这些相关的工作。空间引力波探测器的话，这里边最主要的就是我们汤永老师做了大量的一系列的工作，把这个信号研究非常清楚，它的探测预期也都得到了。然后这个的话也是我们空间引力波探测，比如太极，我们国科大嵌入这个太极一个很重要的一个相关的一个目标。此外的话，在脉冲测试阵列方面，他们也进行了相关的一个探测。这些不同的探测器的话，就探测的相当于对应的它那个质量不同。另外一个的话，我简单提一下我和我们那个组委会这个曹伟老师的一个工作。当然，这个工作都是我们那个曹伟老师他们做的。我的话只是大概讨论一下那个探测预期方面。这个讲的就是说，这个暗光子可以在一个原初的这种原初根源的这种暗磁场当中，它可以那个震荡转化成那个引力波，通过这个混合矩阵。这样的话，我们就可以收到来自于这个暗物质晕当中的一个暗物质信号。当然，这个简单的几句话是一个很简单的一个描述。因为可能大部分都不是同行，它这个信号的话有个特征，就是说在这个黑洞当中它产生的一个信号的话，基本上类似就和我们的暗光子差不多，它就是类似一条窄的那个风。所以说我们刚才探测暗光子的方法的话，同样的话也可以对它进行探测。当然除此之外的话空间引力波、脉冲测试阵列相关的探测的话，都可以对这个目标进行探测。当然的话，在这是在黑洞当中产生的这种引力波的一个信号，在那个早期宇宙中的话，它同样可以产生一个相关的一个信号。这个的话，它是有比较宽频的，这个是相应的一个结果。接着我简单的介绍一下另外一类，就是说我们就是说在明年可能有更多新结果的另一类方向的工作，就是关于对于这种奇异致密星体相关暗物质的一个探测。这里主要的话就是包括这个圆柱黑洞以及波色星。当然，在此前的探测当中，大家主要是集中于圆柱黑洞这种致密的星体。但对于类似于波色星这种，它可以没有那么致密。一般的话，我们用这个 m 除以这个半径这个compactness 来描述它。对于地球的话，你会发现它是大概是10^-10；对于太阳的话，大概是10^-6。LIGO 的话，在迄今为止已经探测到90多例的那个接到 O3 引力波的一个相关的一个双星并合的一个示例。然后其实，在 LIGO 探测到首例示例之后，人们就在猜测 LIGO 是不是已经探测到这个暗物质了。所以说，当时他们就起了有一个很好的一个标题，就 Did LIGO detect dark matter？ 但后续对一些奇异的一些示例的话，大家也看到，就是说这种比如说比较重的这个示例的话，就是说它是不是可能不是黑洞，而是一种类似于一种波色星呢？这个是他们考虑的是一个矢量波色子组成的这么一个奇异致密星体。他们这种的话，相应的就叫 Procastar， 然后他们做了数据模拟，发现那个和数据其实是拟合的更好的。当然，在所有的当中，你会发现你很难区分这种正常的这种天体源的黑洞，还有这种奇异致密星体的黑洞，因为它们特别是对于这个圆柱黑洞来讲，它们和天体源的黑洞只要质量差不多，它们没有本质的区别。所以说，我们怎么来能够探测到 这种比如说这种奇异致密星体的暗物质的存在呢？其中一个比较好的一个 discriminator 就是这个质量。如果我们能探测到一个亚太阳质量的这种奇异致密星体，那它肯定就是背后对应着一种可能的一个新物理。所以说，在最近几年的话，大家也纷纷的，无论是 LIGO 核的组内还是核组外，都开始进行了对相关亚太阳质量这种原子挥动或者是奇异致密星体的一个探测。这个的图的话是这个是马博所的那个王一帆和Alex Nitz 他们给出了一个图。这个横轴的话是横轴和纵轴代表了这个双星系统的这个质量，然后带颜色的区域是代表已经被探测过的一个区域。但在这里边的话，会发现有一个问题，就是说，如果我们想探测到一个想探测一个奇异致密星体的暗物质的话，我们大概有2种策略。特别是第一种策略的话，大概就是大家此前所探测的一个策略，就是说这2个星体的质量差不多。但是你会发现，随着这种奇异致密星体的暗物质的质量越来越弱的话，它的引力波信号会降低的非常的厉害。那有没有另外一种方法让我们可以探测这种让它信号降低的比较弱呢？我们可以对比一下这2个系统。这2个系统的话，它的所谓的 check match， 它基本上大体可以决定这个引力波的强度，它们是一样的。但是有一个本质的区别，就是说这个系统的第一个质量，它远远小于这个中心天体的质量。这样的话，通过这个同样的 check match 的这么一个关系，你会得到这么一个关系，就是这个质量远远小于这个质量。所以说，大概是在同样引力波强度的前提下，我们可以通过一种比较极端质量比的情况来探测一个更轻的这种类似于原子挥动这种奇异致密星体。所以说，我们就很自然的被引到这种所谓的 Emory 或者是Emory 这种系统来进行探测。Emory 的话，可能对于很多做粒子物理同行可能不太熟悉。它的话是我们比如说太极、Lisa 和天琴一个很重要的一个目标。我们台下也做了一位 Emory 的专家陈翔老师。它的话是标准的一个 Emory 的话是由这个星系中心的这个超大质量黑洞和它附近的一个小的一个天体，比如说一个天体起源的黑洞，或者是一个中子星或者是白矮星组成。它们的质量比的话，一个大概是10⁶或更高的相应的一个质量，另外一个的话大概是10个太阳质量左右。这样的话，它们质量比是一个很极端的这么一个情况。这是一种我们可以利用这种系统来探测这种比较轻的这个，比如说原子挥动或者玻色星。但是 Emory 的话，大概要10年之后、10几年之后才可以探测。我们在 LIGO 可不可以做相同的事情呢？所以我们就提了一个概念，就是说的 mini Emory。什么东西呢？我们在这个系统上对这2个质量，我们可以同时乘一个10⁻5或负4。或者这样的话，你会发现这个整体的这2个质量都降低了。比如说这个可以降低成质量可以是10，这个可以是10⁻3、负4，它同样是极端质量比的。但是它的频率的话，因为这个质量降低，所以说它那个世界半径比较变小，它2个可以靠得比较近。这样的话它可以转得比较快，所以它的频率可以比较高。这样的话，我们就可以把它这个系统的这个频率移到我们这个 LIGO 的频段当中。这个图的话展示的是这个系统当中所能达到的大概一个最高的一个频率和这个中心天体比较重的天体的质量的一个关系。我们保持它的质量比是一个比较极端的情况。标准的 Emory 的话是处于大概是这么一个位置。如果我们降低这个中间天体的质量的时候，根据这个公式，我们可以得到这个频率的话是在增高的。所以说，如果我们把它降到这个范围当中，我们就可以看到它的频率可以跑到 LIGO 频段当中。所以我们可以用 LIGO 的数据来探测 Emory。当然，这里的 Emory 是一个非标准的一个 Emory。我们这2个图的话，表示的是我们通过这个标准的 Emory 对这个奇异致密星体这个参数空间的一个探测的一个灵敏度的一个区域。然后右边图的话是我们用 LIGO 的这个数据所能探测到一个相应的一个灵敏的一个范围。这个的探测的话，我们目前正在进行。首先关于这个探测方法主要是关于统计学方法的一个文章的话，可能在这1-2个月内就会出来。然后后边基于数据的结果的话，会相继在明年的话可能都会出来。最后呢，我简单的介绍一下另外一类就是说我们此前所经常研究的 WIMP 这种粒子类的暗物质，它们是怎么能通过引力波来进行探测呢？我们这个话就可以这种引力波的探测的话，就可以很自然的可以和我们在粒子物理当中很常见的一个新物理源的引力波，就是相面引力波来联系起来。 相变的话，我们这里指的是一个早期宇宙发生的一个相变。这个相变是一个一阶的相变，它就是类似于水沸腾这么一个图像。在这个过程当中，它其实实现的是一个对称性的一个破缺。这个过程当中可以产生一个引力波，而 WIMP 的话，它很自然的可以在电容相变当中会产生一个作用。比如说，这是这是我做的第一篇关于引力波的文章，是和我们曹伟老师做的。那时候我还是一个博后。我们考虑的是一个 WIMP trigger 的一个电容相变，它会通过2步相变来发生。第一步的话是由暗物质所吹导，在暗物质这个方向所发生。第二步的话才是电路的相变。当然，我们也可以考虑更复杂的有一个 dark sector 相关的一个这种暗物质和和标准模型有个相互作用，比如说通过 Higgs portal。它相应的也可以改变 Higgs 的 potential， 然后可以在可以通过引力波进行一个探测。当然，这是一个很简单的一个探测。相变的话，是我们一个很重要的一个新物理源的一个水景的背景。无论是 LIGO， 比如说 LIGO， 我们在20年对它进行了一个相关的一个探测。空间引力波探测的话，瞄准的是我们最为关心的一个电容能标的一个相变。在未来的话，我感觉对于我们太极这种探测器来讲，是一个最重要的目标之一。对于 PT 实验来讲，它的频率大概是10⁻⁹赫兹，它对准的是 QCD 能标。对于不同的探气，大家会发现相变的话都可以不同能标的相变都可以作为一个可以有很多相关很重要的一个物理目标。然后相变这是既然是一个很重要的目标，所以说我们也可以通过相应的引力波的探测来找到背后到底有没有可能有暗物质的一个痕迹。当然，这里会遇到一个问题这里左边展示了一个图，就是我们和韩涛老师做了一篇文章的一个图。这里我们试图去对于和暗物质相关的模型进行一个梳理。这是我韩涛老师的学生刘洪凯当时所能达到的一个最好的程度。当然我们也可能漏掉很多模型。你会发现的话，所有不同模型大概得到的相变参数乃至背后的引力波能谱大概都是一样的。这样的话就会导致一个问题，就会出现一个参数简并的问题。那我们怎么样才能通过引力波探测来区分找到背后的暗物质信号，然后区分找到它们的性质呢？这是一个目前在这个领域当中一个很棘手的一个问题。当然，大家目前也是考虑了很多其他的一个观测量，比如说相面当中所产生的曲率扰动相面当中圆周黑洞的产生以及产生引力波的各项异性以及等等。但是我们能不能从谱本身能读出一些相关的信息呢？一个可能的方向就是考虑这个系统当中这种暗物质或者其他相互作用比较弱的粒子导致的这一种所谓的一个耗散的一个效应。因为这个效应的话，在此前的话是基本上被忽略掉的。考虑这种耗散的效应的时候，它会导致这个系统主要是流体，一个极端相对粒子组成一个流体，它这个动能，它这个速度会有一个相应的耗散。而我们知道引力波的话是由这个体系的大概是质量它典型的一个整体的一个动能所决定。所以说，一旦这个速度被比如说粘性类似于日传这种所耗散掉的话，你会发现它的引力波的相应的速度会压低，然后导致它最后产生的引力波的能谱也相应的被压低。这边图展示的是这个引力波能谱作为它的一些对于不同的耗散系数所得到的相关的一个谱。这个蓝线的话是没有耗散效应的时候，然后相应的虚线的话是有耗散效应。然后你会发现它首先在高频区受到压低，因为这其实是不需要进行复杂的相对性流体的计算，通过牛顿流体力学就可以找到这个行为。它这个速度的压力是一个指数型的，而且它是速率的话是正比波数的平方，是越高频的越容易耗散。这其实也和日常生活当中的经验比较相似。如果你拿一个棍子搅水的话，你会发现它很难激起很短波长的或者很高频率的一个水来，或者它们虽然产生，但是也是耗散的最快的。这是一个很基本的一个现象。然后这种东西的话，这种粘的系数的话是比较它们的产生的微观机制的话，大概是和这个系统当中相互作用弱的一些粒子所引起的。然后所以说它将来有可能在暗物质的关联方面可能会有一些相关可以被用来探测相应的暗物质，这也是我们目前所试图去看的一个方向。这个的话其实是在宇宙学当中有一个对应，就是 Circuit damping。Circuit damping 是在宇宙学当中光子退偶的时候，它频率自由程越来越长，所以它可以传播得更远，导致了一种对于各项异性的一个压低。 在宇宙学当中，我们有 circuit damping， 在这个领域当中，我们会有一个类似的一个 damping 的一个效果。这大概就是我讲的所有内容，我大概就是简单的过了一下，就是说可能的用引力波进行探测的一些相关的一些研究的方向主要是我们的一些相关的一个工作。目前的话可能没有太多新的东西，但是在明年的话可能应该会有很多相关的工作。好，谢谢大家。
好，非常感谢。我们有问题欢迎提问。
华科。
好，行。
就是你谈到那个 Emery 的搜寻和 Mini Emery 的搜寻了，就是 Emery 的波形呢一直是个问题，我们现在没有很好的波形。那么你搜索 Mini Emery 的时候，用的是什么波形呢？微向的吗？还是？
对，这是一个很好的问题。首先呢，我先翻到那页吧。哎，好像过了。这个对，这是目前是这个领域当中的一个问题。我们首先采用的是一种所谓的互变换的一个方法，这是目前搜寻亚太阳质量那个我的确没有展示那个技术。这是目前搜索亚太阳质量那个圆头黑洞的一个标准方法，或者说是连续引力波探测的一个方法。它的话主要是基于它那个时间频率图上它那条线来决定。当然，我们的探测分这么几步。第一个的话是基于这种比如说这种视频关系的这种一个探测，这是最初找安卓合作的原因，因为他们是就在连续引力波当中那个组里边，他们做的就是这种方法。我们首先就是考虑这种方法。第二步的那个可能就是借助于匹配率波吧，但是那个目前的话还是取决于这个领域的一个进展。其实如果这个两个星体离得远的话，它的探测的话和目前它们它相对性能比较弱的话，其实还好比较处理。但是如果近的话，可能比较难。我们用的这个结果的话是基于那个 Kip Thorne 他们自己模拟出来一个对圆轨道一个解 Tchaikovsky 方程解出来的一个结果，所以它还是相对准确一些。而且这个 Emery 相对于这个 Mini Emery 相对于标准的这个 Emery 的话，它那个时间没有那么长，它是可以比较短，所以说它积累的误差可能没有那么高。
既然你提到了，就是你们现在假设的是圆轨道，对吗？
我们从最简单的来，对。
OK， 明白了，好，谢谢。
好，谢谢。
我也是问那个 Emery， 就是这个里面那个大的黑洞是一个恒星级黑洞，对吧？在这样一个系统里。
大的可以，我们的条件就是说，我们大的话，它的选取使得我们在这个最稳定圆轨道这个频率在LIGO频率当中，所以它的最大的可以在小1000就可以。
OK，
当然可以任小的。
那你们考虑的就是说，大的黑洞是一个 target source 还是一个就是？
这是一个我们在探测的时候，首先选一个我们其实不能叫 targeted， 叫 directed， 因为它的参数没有那个完全确定。然后后续当然我们是同时展开了一个 targeted 的一个directed 的一个 off sky， 然后这么探测的。
那就比如说那个最近的应该是什么 CYG X1 对吧？那个应该可以用来做这个搜寻吗
？CYG， 不好意思，
就是说你如果利用比如说就是你两个 LIGO 之间的这个干涉，你可以取得一个相对比较好的这个空间分辨率。然后你们有没有就是比如说盯着一个 source 看，这样可以提高灵敏度？
对，我们就是类似于这种direct search 对吧？但我们采取的方法，技术层面就是陈老师问的，就是类似于连续引力波的方法。所以说这个工作也是在连续引力波组里开展的。
但是连续引力波很多都是就是他们不知道方向，就是随便就是
但是他们最终的目标还是那些已知源的那些。对。
好，多谢。
好，我们感谢郭老师的精彩报告。好，我们下一位报告人是这个中国科学院理论物理所的这个王绍江老师。题目是dark matter break and dark matter flip。欢迎。
首先非常感谢这个会议的组委会的邀请来做这样一个报告。那么今天我想跟大家分享的是关于暗物质的两个可能是比较新奇的现象，我把它命名为 dark matter break 刹车和 dark matter flip 翻转。那么这个现象主要是在这样两个体系里面发现的，一个是这个 supermassive black hole binary 这样一个体系，另外一个是 binary 这个 EMRI， 也就是说的 extreme mass ratio in spiral 这么一个体系。那么这是一个三体系统。那么首先这个暗物质的这个证据是非常的 robust 的。那么不管是在这个星系尺度，然后星系团尺度，还有宇宙学尺度，那么我们也有很多这样的暗物质的模型。那么不管是这种粒子性的，或者波动性的，或者说干脆就不是属于粒子物理，比如说是这样一种compact object， 或者说就是一种 modified gravity。当然wavelike 的这种 dark matter 也可以模拟这种修改引力的这种效应这种被叫做这个 superfluid dark matter。但是我们现在目前不管是哪一种暗物质候选者都没有一个很好的一个探测的一个结果。那么现在我们就要 prepare for the worst。那么如果说暗物质只有引力相互作用，那么我们要怎么办？要怎么去探测它？就是它跟标准模型或者超出标准模型的粒子都没有其他的相互作用。那么这种可能是最糟糕的一种情况。那要怎么探测它？那么我们今天就看这样两种体系内的两个新奇的现象。那么第一个体系就是这个超大质量双黑洞的这么一个 binary 的一个系统。那么在这个系统里面，当然这样一个系统里面当然会存在一些问题，比如说最后这个last perspective 的 problem。那么这种 stellar 或者 gas 的 hardening 到底足不足以提供它最后并合，然后形成形成一个 binary， 并且最终并合，这个目前还是 under debate 的一个状态。那么我们先不管这个问题的话，那么最后面它们并合之后，在旋进阶段，在 PDA 会发出引力波，然后一直到最后面的并合。那么这部分主要是引力来主导这个能量耗散的这样一个过程。如果说考虑一个纯粹的一个原轨道的一个超大质量双黑洞的并合的话，旋进阶段的话，那么这个 strain 的这个谱就是这么一个 power law 的一个形式。如果考虑妥律的话，那么陈思源这篇文章给了一个非常好的一个解析的一个拟合的一个结果。那么去年黄老师他们根据这个 PTA 的这个结果，然后用这么一个解析的这样一个模板去拟合他们的数据。那么最终他们会发现一个比较有意思的事情是，在这个引力波开始主导的时候，也就是在这个阶段，那么它要求一个非常大的一个妥律。那么问题是这个妥律是怎么来的那么这个妥律怎么来的？有你可以直观的想象它怎么来，比如说有那种dynamical friction 的这么一种效应。那么你本来是这样一个圆轨道这么绕转，如果它在这个运动过程中受到阻力的话，就变妥了那么这样的阻力可以来自于这个 stellar 或者 gas， 但是我们觉得更有可能是来自于暗物质。为什么呢？因为暗物质的话，它可以在黑洞附近进行一个绝热的一个增长，那么增长以后会形成一个这样的 spike 的一个这样的形式那么这样一个 spike 形成完了以后，我们就可以考虑两个超大质量双黑洞，它们各自都有一个 dark matter spike。那么它们在旋进过程中，当它们靠得比较近的时候，我这里用一个 spike 来近似一下它。那么最终的结果就是，即使它们最开始绕转时候的那个妥律非常小，那么在这种暗物质 spike 的这种dynamical friction 的作用下，它这个妥律也会非常快速的增长当它进入引力波主导以后，它才会下降。那么这样子就给出了一个很自然的一个解释，为什么那个 PTA 的那个结果在绕转阶段引力波主导的时候会出现一个非常大的一个妥律这么一个结果。那么在这个模型里面可能比较令人担心的就是这个绕转的这个双黑洞会对这个 spike 的结构会有什么样的反作用。那么如果说它是一种自相互作用的这种暗物质的形式的话，那么它可以吸收这个双黑洞对它的一个反作用，那么可以把能量储存在这个自相互作用的暗物质模型里面去，然后并不会使得这个暗物质的这个结构发生耗散。那么这个时候的话，那么这个结构应该可以当做一个比较稳定的结构，而且在这个结构里面，这个last per second 的 problem 的话，也可以得到一个非常好的解决，可以在那个11年之内可以能够发生并合。 那么我们最终得到的结果是这样子：首先是当妥率固定的时候，那么即使我开始的妥率非常小，它可以最后面会产生一个比较大的妥率，最后引力波的形状就大概跟有妥率的那种形状非常类似。当我增加这个暗物质的时候呢，它的这个IR 部分的这个 power law 就会有一个明显的一个有规律的一个 universal 的一个性质。那么我们可能可以去搜寻这一部分 IR 部分的这个 power law 的性质，对这个暗物质的这个 spec 的这个 index 给出一个很好的限制。然后另外一方面，如果说我固定的这个妥率，然后我就直接去看我这个引力波的这个能谱和我这个暗物质的性质，那么最终会发现它在 IR 端其实除了刚才那个 universal power law 之外，它在中间的这个阶段还会有一个这样震荡的一个信号，这些震荡的信号是来自各个 harmonic 相加的结果，它们最后的这个包络线的这样的结果。然后这个信号对于暗物质来说是比较独特的一个信号。那么这个是我考虑不同的这个初始妥率之后，那么它就会出现这么1次震荡、2次震荡、3次，这么 n 次震荡。那么这样一个信号可能可以用来探测暗物质。然后另外一个结果就是就是这种三体系统。那么三体系统的话，这个系统其实是比较常见的，比如说我们的太阳、地球、月亮组成一个这样的三体系统。那么陈贤老师还有韩文彪老师，他们18年将其中一种特殊的情况，就是当这2个质量比较接近，但是与第3个质量差的比较大的这么一种 binary emery 这么一系统，那么这样子的话，它可以同时有这种高频引力波信号，是来自于这个小 binary 并合，以及这个低频引力波的信号，就来自于这个 inner binary 它旋进的这么一个过程。那么这个过程最后面大家最近也算了它产生的这样一个引力波能谱的这样一个形式。那么这个三体等级式的这个三体系统，如果我们看它最低阶quadruple order 的话，那么它会有一个非常著名的这个 Kozai-Lidov oscillation。它说的是这个第3个这个天体会对这个小的 inner binary 的这个轨道平面会对它产生一个影响，使得这个轨道平面相对于这个大的这个平面产生一个周期性的一个震荡的一个信号。那么这震荡的信号会使得这个相对的轨道倾角和小 binary 的这个妥率之间发生一个相互的转换。如果我们再看下一阶的话，那么这个是最近的一个结果。那么也不是最近了，这是2011年。那么考虑到 quadruple 的这个结果以后，那么这个时候会发现，除了在这个Kozai-Lidov oscillation 的基础上，整个这个轨道平面会发生一次翻转。那么这个事情其实可以理解，因为每一次翻转的时候是在这个妥率变得非常接近1的时候。那么大家可以想到，一开始是这样子的一个妥率，然后妥率越来越大的时候，它可能就换了一个方向，是这样。可以想象得到是这么一个情况。这里本来是有一个动画的，但是因为转成 PDF 我就放不了了。那么最近还发现一件比较有意思的事情是，如果说我的这个中心这个天体的质量远大于那个小 binary 的质量的话，那么这种非线性扰动的这种长期的这个效应就变得非常重要了，因为整个旋进过程的时标变得非常长。那么这个非线性效应主要是由在哈密顿量里面添加一项这样的项给出来。那么在这个项的作用下，它会强烈的suppress 这个翻转的这么一个事情。那么如果说我们考虑这个系统是有暗物质 spec 的话呢，会怎么样呢？首先中心质量非常大的话，那么它会更加倾向于吸积更多的暗物质在它周围形成一个 spec。那么我们前面已经知道这个 spec 会引入一个这个动力学摩擦，然后使得它在运动过程中产生一个非常大的一个妥率。那么这个妥率就有可能使得原来被强烈压制的这个翻转现象有可能得到恢复。那么这个是我们最近的一个工作。那么我们这个事情其实是比较常见的，我们随便试验的2组这样的参数，那么取了2组参数。那么从这个图里面可以很清楚的看到，如果说我考虑 quadruple 和这个8级矩，那么这个时候就是这条蓝色的线，它会发生一次翻转，它的轨道平面相对那个大的那个平面会翻过来。但是如果考虑这个非线性效应的时候，它就不会翻过来了。 但是如果继续再考虑暗物质引入的动力学摩擦，它就又再次翻过来了。它可能可以翻过来一次，也可以翻过来多次。那么这个是它对应的妥律的这么一个变化的新闻。那么我们看另外一组参数，那么这个的话，我们周期设的更短一点，可以大家很容易、更清楚的看到这一点。蓝色的是有翻转的，那么考虑非线性效应以后，绿色的就完全都没有翻转了，而且这个轨道的这个倾角会越来越远离这个90度。但是我一旦加入了这个暗物质摩擦，它就又再次翻转过来那么这个就是我们的这样一个结果，这是相应的妥律的变化新闻。OK， 那么我们今天这个报告就分享给大家这样2个现象，一个是在2体，一个是在3体系统里面的。那么一个现象就是这个暗物质的这个 break， 它会使得这个它会由于这个动力学摩擦，使得这个妥律变得非常大，并且我们在红外端看到一个 universal 的 power law， 并且在中间的频段会发现有一个这样 oscillation 的这样的一个现象。然后另外就是这个 Dagman 的 flip， 那么对于等级3体系统，考虑暗物质的这个摩擦以后，它有可能可以使得原来被压制的这种翻转现象得到恢复。那么这个就是我今天的报告，谢谢大家。
好，我们谢谢王老师，这个时间还比较多，我们可以多问一些问题。
您好，就是我觉得非常有意思，就是这个暗物质最后对中间的这个双黑洞，它会有影响。我想问一下，就是在你做这个 adiabatic contraction 的时候，一个是你这个就是初始的条件是怎么设置，让它如何演化的？另一个是就是当开始演化以后，这个 dark matter spike 是一直跟着这个黑洞吗？还是说你是用一个就是多粒子的体系来去 simulate， 就是一个 n-body simulation 来去 simulate 这个东西？
好的。你应该问的是前面那个部分。那么因为我这部分初始条件并没有给因为
就是其实前面一个问题是说它最后能有多强这个 adiabatic contraction， 比如说跟这个黑洞的质量去比较的话，
这个是我们等一下在这里，我不知道这个台子是不是挡着你了，就这边这个图。那么这个 spike 它的这个大小和我这个NFW profile 的这个特征的尺度，以及最后面这个轨道半长轴的这个 A0。那么实际上你能够看到，其实它还是有一个 order 的一个分离。对，那么这个结果的话，我们其实也是做了一定近似，就是说我们这个在进入旋进阶段，就是进入 PTA 频段的那个旋进阶段，我认为还是有用一个 spike 来近似它，因为我们确实没有办法去做模拟，去模拟2个。超大质量
OK， 我理解了，就实际上它还是挺大的，对吧？就是其实是挺大的一块儿，所以当合并的时候，就可以把它当成是一个来去近似它。OK，
对，
比方
因为它这个比它大概高1到2个 order， 这样子可以认为是一个。
对的。
然后第2个问题是什么？
对，我想这个 related， 我本来想象就是如果它是一个很小的 spike 的话，可能在合并的时候会比较复杂，但如果是就是差了一个 order 的话。可能就是像这样固定成一个应力示景，可能就没有问题了。
对，严格来说是应该做一个模拟的。对，等一下，还是拿一个话筒，听不太清。
就你不是研究了那个3体的那个引力波信号吗？
对。
你跟那个就是我记得这个咸宇他做过这个，就是他那个什么3体还是什么，对，那你这个应该跟他做的很像了。你们信号跟他们一样吗？
对，咸宇的那个，首先他是做了一个比较半解析的一个结果，然后是考虑到这个 quadruple order 这么一个考虑到quadruple order， 因为我们这个8级矩的这个是我们后面第一次做的这么一个结果，就是说他们会在消除那个 ascending node 的情况下做的，但是我们没有消除那个上升点的情况下做的这样一个结果，所以解析上的结果比它稍微要更近一点。然后在这个基础上，我们又再次加入了非线性和暗物质，就比它再多2个效应，可能就做得更复杂一点。
方法是一样的，是吧？
对，方法是一样的，都是从这个哈密通涅出发做的。
那个之前那个韩文标也做过一个极端质量比的一个。
对，其实
对，那个你这个工作就是只是加了个暗物质吗？
他们对这个可能陈老师更有更 qualify 去评论这个问题，因为他们做的这个话，首先应该是没有这个暗物质吧，对吧？对，然后没有非线性项嘛。
非线性是你这里硬加的是吧？
对，然后那个 ascending node 应该是消除了的。对，所以还是刚才那个问题。
哎，好。
我想问一下，那个你说有一个离散的这个风，那个到底是怎么来的？就是
你是说的，
就是那个上一个第一个工作里面。
第一个啊，
就是考虑妥度。你说有不同的 harmonic mode 对吧？就是也曾确定。
对这个对，
为什么会有这个了？这个是对就是一个 case 的参数下是吗？还是
这个是对一个 case 的我想一下。
就是因为你最后要对 population。
这个是这个对 population 求和完了以后，对。
但那为什么还会留下来呢？不会平均掉吗？就是这样的一个风。
我回一下。不对，这个应该是对一个。对，是这样的，我解释一下，这个点的这个线到的这个线的话，就是
加起来。
对，这个是没有暗物质的。这个时候它的妥率我们是取成0.99。然后这些实线初始妥率都取在0.1或者0.01。最后面他们在这个运动过程中，最后会涨到0.99，和它的这个情况能够 comparable。然后这个是对一个情况算的，然后对不同的harmonic最后面加到一块的这个结果，然后每一次都是头一个震荡的这个风，最后面贡献的这个包络线的这个结果。物理上的原因其实我没有太搞得清这个原因，
但观测上就是说很难看到，因为你看的就是 sum up 的 population， 就是很难看那个每个贡献，就你物理上看的是一个这个虚线对吧？就是最上面那个。
不对，我还是纠正一下，这个确实是 sum over 的这个结果，是 sum over 的结果。
OK， 那
对，因为我们后面那个是 sum over 的这个结果。这个是最后面 sum over 的这个结果，因为这个是那个这个 strand 的一个谱，这个我们是 sum over 的。
OK，
对，
行，我们可以讨
论。少将你好，很有意思的结果。就是我不知道，你们有没有考虑，当两个黑洞靠得足够近的时候，因为引力弹弓的效应，事实上他们会把周围的暗物质全部抛掉。这样的暗物质事实上在两个黑洞的，尤其是晚期演化的时候，可能会非常的少。你们有没有考虑这个效应？
对，那个已经离得非常近的这个时候，其实已经就是引力波占主导的那个阶段了。
它可能会在引力波占主导之前，
因为这个频段，你看这个是在这个可能到几十到100年那么一个频段，这个时候应该还是离得比较远的。
这个就要比较两个黑洞的束缚能和周围的暗物质的典型的这个运动动能。当那个束缚能超过的话，就开始抛暗物质了。所以这个半径可以算一下，看看它在什么地方发生。
好的，我们回去会 check 一下这个事情。
OK， 那我们非常再次感谢这个王老师的精彩报告。
好的。
好，下一位报告人是北京师范大学的李仁老师，题目是Mapping the Dark Universe with Astronomical Observations。欢迎。
好，谢谢大家。非常高兴能够来到这里来做一个报告。我稍微改了一点我的题目，就是和这个大多数的报告的主题能够有一点相关。因为本来我想讲就是纯粹的这个对暗物质在宇宙中分布的测量。那么现在呢，我这个报告里边主要包括的是说，从一个星系形成的结构测量的角度上面来讲，到底我们对这个暗物质宇宙里边的暗物质性质还能够给出一些什么样的一些 probe。OK， 那么从这个今天我们对暗物质的研究来说，我们当然知道它是非常重要的问题，有很多的人在去做它，对吧？从这个物理里边，我们想要直接的去在一个探测器里边找到它是什么粒子，然后呢，我们可以到天上去看它的衰变或者是它的这个湮灭，我们希望在对撞机里边把它造出来。那么任何的这样的一个实验如果成功了的话，那么在天文上面去做这种暗物质的研究，暗物质本质的研究就没有任何意义了，因为一旦你知道了这个暗物质是一种什么样的粒子，那么它对结构演化的影响，实际上某种程度上是决定性的。但在前面所有的试验都没有给出暗物质真身的情况下，那今天我们所有对这个暗物质的理解，都来自于天文的观测。我们知道它很多，占这个宇宙实物组分的30%。我们知道它肯定是非重子的。因为这个星系团碰了以后，这个热气体和这个暗物质它发生了分离，我们甚至知道它可能是一种被我们称作是冷的暗物质因为我们可以去观察大尺度的结构形成。那么根据这样的一些逻辑，那么今天我们依然能够从天文上面试图去找到一些暗物质是什么的一些暗示它不能解决这个问题但是它能给我们也许指点一些方向。我们可以回顾一下最早大家是怎么去做这一类的问题的，从这个天文观测上面。那么比如说我们怎么知道这个暗物质它是一个冷暗物质呢？那么实际上是来源于70年代的时候，这个马克·戴维斯他做了一个星系巡天就是这里边这是我看观测是哪一个？这个就是他看了一些星系，他把这些星系在空间中的分布画了出来，然后看到里边好像有一些 filamentary 的结构，有一些空洞的结构，他把这个东西称作是宇宙网。那么人们就思考这个东西是怎么来的。那么正好在同时呢，苏联的这个实验室里边有一些人测出来了中微子的质量，说中微子质量是30个电子伏特。如果中微子质量是30个电子伏特的话，就意味着所有的暗物质都是中微子所以人们就做了一些数值模拟，得到了一些中微子的这个物质，它的就是在一个中微子构成的宇宙中，我会形成一个什么样的结构？那好像也能形成这个 filament 的结构和这个大尺度的空洞的结构。那么这个时候呢，有一些文章被从苏联走私到了美国。在冷战的时候，你需要把一些文章偷偷的运到美国，然后到了马克·戴维斯的手里。然后当时呢，他的博士后叫 Carlos Frank，在圣诞节的时候就跑了一组这样的模拟。那么跑出来以后呢，他发现，如果你认为宇宙里边所有的这个暗物质都是中微子的话 ，OK， 那么你会形成非常粗壮的这种 filamentary 的结构。那么比真正观测里边可能要大个3到5倍。但如果你认为这个宇宙里边的物质呢是一些非常大质量的，在宇宙早期它的运动速度很慢的，不会抹掉小尺度结构的这种比较 cold 的暗物质的话，那么你造出来的宇宙就跟观测到的宇宙一样。这个 Simon White 去这个就是他们4个人合作的这个工作 ，Simon White 到苏联去讲这个工作的时候，苏联的功勋这个科学家泽尔多维奇拍着他的肩膀说哥们儿，说这就是个3倍的误差，这不算什么但最后这个3倍的误差就把这个中微子作为暗物质的一个主要组分给干掉了，对吧？所以今天如果我们在计算机里边去跑一个宇宙学的数值模拟，我们得到的大尺度上面的结构的这个分布的形状，星系在这个大尺度上分布的这个结构，统计上面来讲，跟我们观测到的星系分布的结构可以说是非常非常的类似。而且在模拟里边，我们也可以从宇宙初条件开始形成各种形态的星系那么当然定量上面有很多问题，但是也可以开始和观测进行很多的定量的比较。所以遵循这样的一个逻辑呢，今天依然很重要的一件事情是说，我们通过去比较计算机中或者是理论上面得到的宇宙的结构和我们真正观察到的宇宙里边物质分布的结构，看看我们还能不能得到一些新的关于暗物质的知识。那么从天文上面来讲，虽然有很多种的暗物质模型，但是具体到我们真的去跟结构比较的时候，实际上你关注的某种程度上面来讲，可以把它约化成几类这种观测的性质。一类呢是说你能形成一个多小的结构，那么它实际上决定于我的这个粒子在开始的时候有多大的一个 free streaming scale， 我能够抑制什么样尺度的一个暗物质运的形成。那么另一类性质呢是说这个暗物质它是不是自己跟自己碰撞，对吧？或者它是不是跟重子物质碰撞？那么碰撞当然就会 modify 这个暗物质运它的中心的结构，甚至它整体的结构。OK， 那么这个是 counting， 就是我们怎么去做计算。一件事情是去算这个小的暗运的数目。那么对于这个 WIMP 来说，理论上你可以形成低至10的负6次方太阳质量的一个暗运，就是地球质量的暗运。对，但是对于这个比如说 keV level 的这样的一个粒子 warm dark matter 的话，那么可能在10的10次方太阳质量以下，你这个暗运在宇宙里边的数密度就会跟这个蓝色的 CDM 就会发生差别。那你如果能够数到这些暗运的数量的话 ，OK， 你可以去做一些限制。那么这大概是个什么概念呢？银河系的这个矮星系大概寄宿在一个10的8次方到10的9次方这样的一个暗运中啊，所以还是有一点希望的。那么另一个就是这个还是刚才那个 ，OK， 这个就是warm dark matter 它会这个 surprise 非常小的这个 halo 的形成 ，OK。那么另一个呢，就是说它的这个结构，对吧？就是如果这个冷暗物质的话，冷暗物质宇宙有一个非常明显的就是非常独特的特征，就是这个暗物质运它最后都是自相似的，然后它在中心的部分都是服从一个R-1这样的一个密度轮廓。但如果是说你有碰撞的话，那么取决于实际上你会想象，就是说这个粒子和粒子的这个碰撞截面实际上往往是速度依赖的。那么这种速度依赖的速度截面实际上会让你在不同的暗运的质量区间里边，这个暗运的它的这个密度轮廓的改变其实还不太一样所以这也会有很多新的这个观测量。下面这个杨大能老师的报告肯定会非常详细的去讲这方面的事情。OK。那么观测怎么去做它呢？我们就是实际上是有两个方向你可以去做的。一个是你要到很小质量的这个暗运里边去，因为很小质量的暗运里边的星系都很小，基本上是暗物质主导的。另一个呢，你要到很大质量的暗运中去，因为很大质量的暗运它形成星系不那么有效。一个星系团它中间的星系其实也没有多大，所以在这个地方也是暗物质很主导的，所以在两头可能是一个很好的一个观测场所。那么最早大家是从 satellite 开始的，那么银河系的矮星系，大家天然的认为这是一些去数暗运的一个最好的一个 proxy。那么就是出来了很多的问题，在90年代末的时候丢失了星系，太大的星系那么这些问题本质是什么呢？就是说我们在银河系里边可能看到了几十个这样的卫星星系，但如果你去看暗运的话，低于10的这个大于10的6次方太阳质量的暗运大概有200-300个。那怎么去解决这个问题呢？当然，我们就是改换成 warm dark matter 可以解决这个问题。但是后来人们发现这里边有很复杂的重子效应的影响。如果我有一些重子形成过程中的能量注入，那么我可能会把这个气体从 halo 里边推出去，或者加热这些气体，那么最后使得实际上低于10的9次方太阳质量的 halo 里边就不形成星系了。那么另一个方法是说，我可以去找一些 star stream， 就是这个星流。星流，如果你碰到一个暗物质运，那么它有可能在中间会产生一个 gap， 你过去了以后，你会扰动这个星流恒星的这个密度分布，那么你也可能从这个里边去找到一些暗物质运那么实际上这个现在对这个的测量非常的乐观，大家认为到这个 LST 出来的时候，可以测到低至10的5次方太阳质量的。那唯一的问题呢是说，你可能得要碰一些运气，因为这个银河系里边的星流是有限的。而且这个真正要做这个事情，它这里边可能也还存在一些 model 的这个 complexity， 但这也是被认为非常有希望的一个方法。那我自己比较喜欢的办法呢，是用这个引力透镜系统。比如说我地球和一个星系和一个远处的星系连成一条线，这时候我就会看到一个爱因斯坦环，对吧？这个星系的这个光弯曲了，那我会看到一个环状的天体，实际上是由它来的。那么如果在这个光路上面我有一个小的 structure 的话，你可以看到这是一个星系，它就会在这个爱因斯坦环上去开一个坑儿。如果我看到一个坑儿，但是我没有看到星系，那我就会认为说，哎，我可能数到了一个小的暗运。那么10年前，实际上人们就已经发现了，在哈勃数据和凯克 AO 的数据里面发现了2个暗运。我们可以看到这个质量跟我们要求的已经很接近了。所以我们用这个从这里开始，我们就做了一些 prediction。那就是说我大概有100个非常高星噪比的 lens， 我就可以把一个 keV 的这个 warm dark matter 跟这个 CDM 把它区分开。那另一件事情我们发现很有意思呢，就是说如果你考虑的话，这个暗运它不仅仅存在在这个形成引力透镜的这个 lens 上面，它在整个视线上面都有。那视线上面的这些东西你数进去以后，会比在 lens 上面的这个 perturber 要多个3倍以上，所以会让你最后的这个观测效应更明显。 而且更好的呢是说，这些 line of sight 的东西啊，它可能完全是纯的暗晕，它没有经历过掉入到大暗晕里边的潮汐剥离啊这些现象，所以理论上也更好去 interpret。我们花了非常多的精力，在过去的10年里边，发展各种各样的方法。我们和这个杜伦大学的合作组。那么我们做了这个，就是以这个 James Nightingale lead 做出来一套软件，叫做 Pi Auto Lens。那么我们可以看到，如果你拿它去拟合一个哈勃望远镜的图像的话，那么你可以把它这图像里边的各种细节都拟合得非常的清楚，对吧？然后我们也做了很多的 mock test， 我们从数值模拟里边去找一个很复杂的星系，生成一个引力透镜，然后我们放一个假的 subhalo 进去，我们看我们能探测到，那么也证明整个的这一套办法是可行的。然后还有一些就是说，你如果找到了一个 perturbation， 你怎么知道它是 perturbation， 而不是你的观测数据的一个问题呢？那么还有一些无参数化的方法可以去帮你做诊断。如果你是一个 subhalo 造成的一个 halo 造成的 perturb 的话，那你最后产生的这个扰动，它如果无参数化的把它的这个 perturb 表示出来，它应该是像一个圆形的东西。那么其他的一些不同的效应，比如说你这个这个外部的这个剪切场的影响啊，或者是你这个星系自己长得不规则的影响啊，那都能够用这种无参数化的方法把它们的 perturbation 的形式把它确定下来。OK， 那么这是最近的一些观测的研究，这是所有哈勃，我们分析了所有哈勃里边这个比较高信噪比的引力透镜，发现了有5个 candidate 里边可能有一个小的 dark perturb。那么其中这个是这个非常的这个 promising 的，因为不同的这个模型，最后我们都就是不同的模型假设，我们都找到了这个 perturb， 而且有一个10的14方左右的质量。那么这是另外一个，但它质量更大一些。那么其他的一些 candidate 可能不那么好，因为就是说它在有的参数化模型里边，就是有的这个 lens 假设里边你能找到它，那有的时候你又找不到它，你就需要更加的做一些更好的这个 follow up 的观测。这个是在詹姆斯韦伯望远镜里边的一个透镜，这个是我们合作组今年发表的投递的一篇文章。我们可以看到这是韦伯里边的一个引力透镜环，我们在这个地方找到一个 perturb。那么这个韦伯有3个波段的图像，那么我们对每个图像去进行建模，那么都在就是这个红的地方啊，是说你可能存在 perturb 的地方。那么至少3个波段我们都在这儿看到了一个 perturb。那么这些 perturb 除了你数它之外，其实还就是它的 structure， 如果你有很高信噪比的这个观测，你也能去做的。这个是这个SLAC 0946，那么这上面有一个 dark perturb， 好几个研究组，包括我们都在这里找到了一个 subhalo。那么如果你去测量这个 subhalo 的 compactness 的话，你会发现它跟数值模拟里边那些暗晕的 compactness 差很远，它非常的 compact。OK， 就根本不像一个 NFW halo。如果你拿一个这个 CDM 里边自相似的 halo 去拟合它的话，它的这个致密的程度可能要比一般的 halo 要高个十几倍甚至几十倍，而且它的质量可能很大。那么这么大的一个 halo 里边，为什么没有星系？这是现在一个非常有趣的问题。就不管是 CDM， 就是最近我们去做了一些 CDM 的拟合，发现可能都没有办法很好的解释这个观测实例。那么我们从这个最小的尺度再回到，就是我们刚才说2个这个地方，一个是小尺度，那么大尺度上，大尺度上就是星系团。那么星系团的互相碰撞会提供一个很有趣的实验，就是说我的这个星系你可以去看2个星系团碰撞，那么这个星系呢它是一个无碰撞粒子，那它不会阻碍对方。那么暗物质呢，它理论上也是个无碰撞粒子，所以它碰完以后呢，这个星系的分布应该跟暗物质的分布很相似。那么你可以用它们的相似程度来去给出暗物质的这个弹性碰撞截面的一个上限。那么另一个呢，就是说你碰完了以后，这个中心星系它会在这个暗物质运的视景中心震荡一段时间，最后回到这个视景里边。那如果说你这个星系团中心由于暗物质自相互作用有一个平坦的密度分布的话，那么这个星系回到视景中心的时间就会变得很长那么你就会看到更多的星系团，它的中心星系不在它的视景中心。那么人们用10个星系团的观测呢，就显示说，好像这当然是一个比较早一点的工作，后边大家有一些争论。那么就好像是说我这个中心星系偏离星系团中心的程度， 稍稍的有那么一点点偏离 CDM 的 prediction 啊，更像是一个有很小的一个 cross section 的这个dark matter 的结果。然后这个呢是一个非常有名的，13年的时候，这个 Newman et al 分析了7个星系团，而这7个星系团中心它的密度都非常的平，就跟 CDM 的预言的差很大。那么这个是我们最近做了一些近邻的星系里边的密度轮廓，但是这个最大质量端大概是跟这里差不多。那么至少到10的14次方，其实我们没有发现这个纽曼做的这个结果，所以是不是到这儿突然长出一个 core 来 ？It's not quite clear。好，那么就是说，现在这个有很多的办法。那么未来我们期待什么？那么对于暗物质的全景测量，其实现在从小尺度 kPc 尺度到100 kPc 尺度，到非常大的到 GPc 尺度，实际上都有各种各样的方法。但是这个我们实际上需要更多的数据。那么一个很重要要发生的事情，在未来的几年里边，中国可能会发射一个2米口径的巡天望远镜，叫 CSST。那么它将会对全天17500平方度，也就是说，大概我们完整的除了银河系占据的天空以外，其他的天空去进行一个深度的巡天。那么它的能力呢，是可以将我们看到的强透镜样本增加100倍，把我们看到的这个弱引力透镜的样本增加10倍左右。这个是我们做的一些 prediction 里边，就是未来的这个巡天里可能会有5000个这个那种爱因斯坦环这样的星系，它的星噪比是大于100的。那么这个是一个大于100星噪比的一个爱因斯坦环3色和单色的情况。然后这个里边，如果你去做一些 prediction 的话，你会发现可以找到几百个甚至到1000个左右的这种 dark subhalos， 然后当然也包括很多的 cluster lenses。OK， 我就在这儿就停下了。好，那么就是总结呢，就是说这个天文测量通过精确的去测量物质的结构，那么能够对暗物质的冷或者温或者碰撞或者不碰，还是给出一些有趣的probe。那么未来的这个10年里边，观测将会极大的丰富这个领域，将会是一个有非常有趣的多的有趣的工作可以去做。好，谢谢大家。
非常感谢李老师。我们欢迎提问。
好，谢谢李老师精彩报告。就是我想问一下，未来比如 CSST 测到了那么多的 subhalos，我们能够比较准确的对 subhalo mass function 给一个好的限制吗？
我们在10的10次方能够给一个好的限制，更低的话就很难。就是相当于说你的探测 limit 是10的10次方太阳质量。但真正你知道，就是你要去做这个 cut off， 比如说，如果我们想要彻底的 rule out 10K 以位的 stereo neutrino 的话，你需要到10的7次方太阳质量，所以那还有一个很大的 gap。那么怎么去做这个事情呢？一个呢，就是说我们还是要从这里边去选择高信噪比的这些 lenses， 用 JWST 或者是 ELT 去进行 follow up。那么如果到10的7次方的话，你算一下，在每一个 ring 里边，实际上你都会有一个或者2个 dark matter halo 在爱因斯坦 ring 的附近，所以实际上用 ELT 这样的观测，只需要去看很少的高信噪比的爱因斯坦 ring， 你就可能找到1到2个10的7次方太阳质量的 halo。然后你有了那1到2个，实际上你如果去看前面的这个halo mass function 的话，那么就已经能够给你很强的这种能够给你很强的限制了，因为到这个低质量的时候，实际上这个 CDM 跟比如说3个 K 以位的 WDM 就有好几倍的差距，对吧？但是如果是10个 K 以位的话，那就到这个地方依然会非常的相像。那么就是说取决于说你的目标是什么，对吧？那么有的暗物质模型，比如说它到10个 K 以位，它可能就没有它的这个理论的 motivation 了。但是有的暗物质模型，它可以一直种下去，它会非常的像 CDM， 那你 never gonna to rule out it。
对，那另外就是相关的一个问题，可能就是这个如果只是用 strong lensing 的 approach 来看 subhalos 的话，它是不是有一个 selection bias 在那里？你看到的总是那种非常致密的。
对，这个是会有的。那么这个实际上我们写过2篇文章去讨论它，主要是就是说你会倾向于看到更小质量的、更 high concentration 的 halo， 那么有两种办法你可以去讨论，就是你可以去想这个事情。一个呢是说，就是在一个 CDM 里边到这么低质量的 halo， 它实际上完全是有引力控制的，它的重子在这个里边的影响就没有那么大了。所以它的 mass concentration rate 就是它有多 compact 这件事情不是那么任意的。也就是说，理论能够告诉你你有多少非常 compact 非常小的 halo， 所以你还是可以把这部分放到你的模型里边，然后来去做你的预言。OK， 那么当然呢，你也可以说 OK， 我的宇宙是很奇异的，就是实际上我看到的并不是 high concentration low mass 的 halo， 而是比如说 core collapse halo， 或者是 supermassive isolated black hole， 对吧？那当然就是那是另一个问题了，那需要其他的东西来去帮助我们。
好的，好，谢谢。
我问一下，就是这个是相当于是就是暗物质对于光的弯曲，对吧？我
纯粹是引力的弯曲，对
啊，
纯粹是引力效应，不是没有散射或者什么东西。
对。我开始以为你要讲那个引力波透镜。
对对对，因为我回了2次信，我感觉可能你没有办法 get 到我的点，所以我就没有再去纠结这个问题。
你不是，就你本来想讲
我没有做过引力波的 substructure 探测。对
啊，就是你做的是光学的引力透镜啊，不是做的引力波透镜。
对，我也做过引力波透镜，我跟陈先同志曾经有一个半途而废的合作项目，做过引力波透镜。对，但是我不是我的主要的工作，我的主要的方向是用这个方法。
光学啊，光学也很重要。好，谢谢。就我开始有点误会。
对，我理解到，我看到你的回信，我想你可能大概没有看懂到底是怎么回事。
对，当然在这个引力波探测器提高分辨率之前，光学找引力透镜绝对是主流的方法。我忽然有一个奇怪的问题，就是当你在那个 arc 上看见有一个暗的 gap 的时候，我们能够确定它不是因为有些什么 extinction 然后什么造成了那边暗下去了吗？
对，我觉得这个是个很好的问题，就是你要找到很多的话，当然会有一些。要是有1、2个事例的话，你有很多的话，你可以做比较，然后你可以知道有一些可能是 dust。
对。
但是你就1、2个的话呢，确实是。
是，但是偏偏如果看见一些非常特殊的，又得到了很奇怪结果的，
就是 this one， 就这个是某种程度上想要去回答这个问题的，就是我们希望把我们看到这个 perturbation，因为你一旦有了 lens model 以后，你可以做一个非参数化的拟合。你可以知道造成这个 perturbation 的这个影响是什么。如果是一个 subhalo 的话呢，最后你需要的这个就是这个改正，这个物质密度峰的改正就会很 compact。如果是一个这个比如说 dust extinction 啊这样的东西的话，那么当然它就会更复杂。这是 one。Second 呢是说我们还是可以去做一些 ALMA 啊这些观测，然后来去看看它里边的 dust 含量。对，我还是寄予厚望我们合作的这个引力波 lensing 的事情，对吧？
好，我们还有其他问题吗？我想问一个比较外行的问题，就是你这边那个暗物质模型的话，都是均匀分布的呢，还是说它会有一些这个致密星体的这种考虑过？
你是说我在这里考虑的这种 double perturb 还是说整个的暗物
质？就是因为你说有些那个 halo 嘛，对吧？你有考虑过更致密的情况吗？
你说这个作为 perturb 的这个 halo 对吧？就是首先它有2个，一个呢是说我们作为这个大的这个就是中间我们看看我翻到哪一页，就是这里边实际上涉及到2个透镜。一个呢是说产生爱因斯坦环的这个透镜，那么这里边是一个大的星系，它也在一个暗物质晕里边。那么这个暗物质晕一般认为是一个 NFW 的暗物质晕，因为有很多大尺度的这个观测去限制它。那么另一个呢是说可能在这上面开一个 gap 的这种小的暗物质晕。那么这个暗物质晕呢，就是说我们尝试过各种各样的就是参数化的模型 ，compact 的或者是这什么的。那么实际上就是说对于现在人们看到的这个东西。21就是实际上是这个 lens， 那么也有一些人已经开始尝试说 ，OK， 它就是一个 就是 point mass 来去做它，然后看看它到底对应着一个多大质量的一个 point mass。那么至于如果它能够用一个 point mass 很好去拟合的话，它到底是一个黑洞还是一个刚才有的老师讲的这个暗星，那么这个我想是理论家去做 interpretation 的。
好，谢谢。对 ，OK，那我们再次感谢这个李老师的精彩报告。我们下一位报告人是紫金山天文台的杨大能老师。OK， 那报告题目是这个 Impact of Baryons on the Signatures of Self-Interacting Dark Matter Halos。欢迎。
好谢谢介绍，今天非常高兴能有机会。哦 ，microphone。Where is it？ 哦 ，over here。这个能听见吗？好的，好，谢谢。今天非常高兴能有机会在这里介绍我们的工作。Sorry one second。对，就是我今天报告的题目大概是自相互作用暗物质，然后会讨论有 baryon 和没有 baryon 的情形。对，就感谢刚才几位尤其是李兰老师的背景介绍，所以motivation 这部分我可以稍微简单一点，就 focus on 自相互作用暗物质了。自相互作用暗物质呢，就是通常情况下文献里边讨论的比较多的就是一个 diversity problem。我们什么是 diversity problem 呢？是因为暗物质我们只能通过引力手段去探测它，间接的探测它。那怎么去间接探测出来呢？就是我们去看那个星光或者是21厘米谱线，然后去重建出 rotation curve， 再根据 rotation curve stellar kinematics 去反推出来 dark matter 的 content 是什么。然后观测上我们如果去提取这个 rotation curve 的特征参数的话，就会得到蓝色的一些点。然后我们把这些点和CDM 里边 hydro simulation 去做一个对比，我们会发现 CDM 面临着一个 challenge， 就是它的那个 spread 非常的小。就是这个时候呢，大家就考虑，那如果暗物质它自己和自己有一个弹性的散射，会发生什么事情？然后这是一个 motivation， 就是我们发现，如果我们考虑 SIDM 的话，有挺大的一个可能去能够解释那么一个大的 spread， 这个是叫做 diversity problem。在近2年呢，就是又有一些新的 context， 然后非常有趣，可能也 support 这样的一种 novel scenario。就比如说刚才王绍江老师提到final parsec problem， 那今年也有文章说，如果你没有自相互作用暗物质，那实际上 supermassive black hole 它的旋进的时候就会把你这个 density spike 给破坏掉。但如果你有自相互作用暗物质，那个角动量的这个损失，它就可以通过 dynamic friction， 它就可以通过 SIDM 给传递出去。所以除了 final parsec problem 就是和 black hole merger 相关的，还有包括 dark matter deficient galaxy、ultra diffuse galaxy 和strong lensing perturber， 就刚才李然老师说的那一种的话，这些都提供了一些新的 context， 让我们去做一些和观测相关的研究。然后SIDM 呢，就是它这样的一个 scenario， 实际上在我们做粒子这一边也是有一些动机去做它，尤其是现在我们望远镜比较多，观测的数据也越来越多，那我们去联合拟合各种星系它的旋转曲线的时候，我们会发现SIDM 下边它实际上很多的星系它去拟合都能拟合得非常好，而且的话就是这个拟合的结果它你反推出来这个黑洞的性质，它和宇宙学模拟里边是吻合的比较好的。当然这样的问题，你涉及观测了之后，背后有很多的那些 degeneracy 需要去讨论。但是至少这是一个窗口，就从15年一篇比较 seminal 的 paper 里边就已经指出，这个通过天文观测，我们反推出来这些 rotation curve 的话，它是对暗物质自相互作用的粒子性质是有一些敏感度的。 所以这就是一个motivation。那今天我的报告呢会大概3个部分。第一个部分呢，我还是说传统的没有 baryon 的情形。这种情形的话，就是我大概给大家留下个印象，现在我们能做到什么程度，我们能理解的多清楚 ，model 的有多么的准，然后diversity problem 为什么我们可以比较好的去理解它。然后第二部分我会说这个 baryon 它到底会对我们现在的这个理解这些结果产生多大的影响，我会举几个例子。然后最后这一部分的话就还比较初步，我会简单的说一下这个在有 baryon 的情况下，我们 SIDM 的 signature 可以做哪一些更新。先给大家一个例子吧，就是一个例子比较直观，这是一个 dwarf galaxy。然后 dwarf galaxy 的话，这个 in this case， 它的 baryon 的质量相比于 halo 的质量小了挺多个两三个量级。小了很多。那这个情况下，从右边这个图，这还是 rotation curve radius velocity， 它的观测这些点是这个黑色的，然后 baryon 红色这个非常的少。我们可以看见，在这个 case 里边，你有没有 baryon 可能影响不大哈。如果你有在右边这里，我实际上是对这个 rotation curve data 做了一个拟合，然后拟合出来的结果的话，就是基本上也只有 dark matter。这种情形的话，它是一个 ideal case， 就是我们即使是没有 baryon， 我们依然能够去对这个data 做比较好的理解，就只考虑 dark matter 就行了。这个 PPT 我做了一个对比，左边是没有 baryon， 右边是有 baryon。OK， 那这和 SIDM 有什么事情是吧？这个就是做一个对比，如果没有 SIDM 的话，至少在这一个 case， 你会发现，你要去拟合这个 data 就非常的困难了。然后这是一个 dwarf spiral， 当你加入这个当你考虑 SIDM 之后，实际上这个截面也不用特别的大，然后你就会发现拟合的非常好。但这只是一个 case， 要具体说事情，我们还是要看很多的 case。这里介绍一下这个 baryon 和 dark matter 它到底在黑洞里边怎么个回事。这个图的话是一个叫做stellar to halo mass relation， 它就 x 轴的话是 stellar mass， x 轴是那个 halo 的 mass，y 轴是 stellar mass divided by dark matter halo mass。 然后就刚才李然老师也提到了，就是我们看的时候，很多时候最好是找2个情况，要不就是你在最左边 stellar mass 非常的低，halo 的 mass 也非常低，这是对应的 dwarf galaxies， 要不你就往右边跑去比较重的。为什么呢？它这个 stellar to halo mass function， 它大概就是在我们银河系这样的一个质量这里的时候，它的 stellar mass 非常的多，然后这部分你去看的话，它又不干净，是吧？所以我们传统上就去考虑 diversity problem 或者是做一些拟合，比较理想的情形都是在往2头去。然后为什么会有这样的一个结果呢？它主要是 feedback 不同的 feedback 的影响，我就不详细的说了。所以我们还是先看 dark matter only 的情形，主要是我们和合作者们，我一开始做的工作也是只有 dark matter only 的这种情形。这一页 PPT 呢，我想介绍的是一个银河系尺度的那么一个 zoom in cosmological simulation， 它里边既有一个像我们银河系一样的那么一个系统，它里边也有 LMC， 还有一些 dwarf galaxies。我们把这些 dwarf galaxies， 它的 rotation curve 拿出来，然后就可以同样的是提取出它里边的2个特征量，然后就可以和观测的一些点，这个是黑色的这些点做一个对比。这里我们明显的如果对比左右2个 panel， 我们就能够看到 CDM 的话，它和 data 就是相差的比较多，而且它这些点分布也比较集中。但如果有 SIDM 的话，它的那个 spread 就会比较大，而且的话，它有2种类型的，一种是 core forming， 一种是 core collapsed。什么是 core forming、core collapse 呢？意思就是说，如果你去看这个 dark matter halo 的 density profile， 它的密度分布 ，core 的就是说它中心的分布比较平。cusp 呢是说它中心比较尖，而且在 SIDM 下边，它的这个尖的程度可以比我们知道的那个比较熟悉的 NFW profile 还要更尖，所以它的那个 predictions 本来就比较 diverse。为什么会有这种一个比较 diverse 的 density profiles 呢？主要就是因为你考虑那个弹性散射了之后 ，SIDM halo 里边它就有一个重热演化，重的话就是它有 gravity， 热的话就是你有弹性散射之后，它的 energy 有一个 transport。那在这个 energy transport 下边就会一个非常简单的过程，但是会有一些比较novel 的 predictions。而且的话，就是这个 predictions 今天我想强调一点的就是，我们除了看起来你 population 的 level 你能够解释这么一个 diversity， 实际上我们现在已经能做到 case by case 的一个 prediction， 这样的话就能够丰富我们 对观测信息的理解和模型的 comparison。为什么能够做到这样一个事情呢？是最近几年理论上这边我们也有一些进展，就是我们能够有一个比较 unified 的一个理论框架去理解这个 SIDM halo 它是如何演化的。我们把这个 SIDM halo 当做一个热力学系统，那这里边 SIDM 的效应，实际上它是会破坏你这个 halo 它随时间的演化。你可以想象，如果一个 NFW halo 没有 SIDM， 那它基本上就不演化的。那它的演化是怎么去理解它呢？我们就可以引入一个 transport equation， 然后在这个 transport equation 里边 ，SIDM 效应只会通过里边的一个 heat conductivity 这个 kappa 这个量进去，它是正比于 cross section 的。然后如果这是 kappa 是正比于一个常数的一个 constant cross section， 那我们可以做的一样事情，就把这个截面吸收到这个演化的时间里边去。那这样的话，整个这个系统就和 SIDM 没有关系了。所以注意到这一点之后，我们就可以有一个和 SIDM 截面 specifically 的这个截面没有关系的那么一个框架去得到各种不同的gravel thermal stage 下边的halo 的结果。OK， 那我们想要做的是想要做到的一个目标是我们对于你观测的一个 population 的 galaxies， 我们从里边都能提取到一些 SIDM 的信息。那这些不同的 galaxies， 它的 SIDM 信息会是不同的。为什么可以有就是虽然我们是理论上我们发现了那么一个可能有不同信息的那么一个来源，然后这个来源是什么呢？就是说。我们发现实际上给定你一个 particle physics 这边 SIDM 的一个 model， 它是会和暗运它里边的那个速度分布velocity dispersion 的分布有一个 coupling， 然后这个 coupling 它给你了一个每一个 halo 里边都有了一个 SIDM 的信息。那有这样的一个信息之后，你就可以结合很多的一个 halo 的观测去提取出不同的 SIDM halo 它。不同的 halo 它对于 SIDM 的敏感度了，所以pictorially 我们可以想就是至少在 leading order 我们可以有那么一个图像，就是说你给每一个在一个每一个暗运都给它 assign 一个 quantity， 在 CDM 里边它全都是0，但在 SIDM 里边它可以取不同的数，然后这些不同数它的分布实际上是对我们的 SIDM model 有敏感度的。更具体一点，就比如说 in terms of 刚才。就是说 rotation curve 它里边的两个特征量，比如说 Vmax、Rmax， 它大概对应的就是这个 rotation curve 最高的这个点最大的 Vmax 和它的这个位置。我们可以把刚才的这个所谓一个 gravel thermal phase T 比上 TC 这个量给不同的 halo 它都给画出来。那通过它的这个分布，我们就能够对不同的 halo 有敏感度。然后基于这些年的理论上的一些工作呢，我们也是把这些理论的东西做成了一个工具，所以它能够有什么用呢？就比如说昨天王伟老师他们报告的里边提到的一种SIDM 的 model， 这一种新的 model， 那只要给出它的那个velocity dependent cross section， 我们就能够很容易的，比如说10分钟，我们就能够拿到刚才的cosmological simulation 里边 SIDM 的 halo 它都长什么样子，我们能够做到这样一件事情。然后这样的一个工具呢，也是被一些同事他们做到了一个叫做 Sashimi SIDM 的一个 semi-analytical 工具里边，所以这是类似于一个蒙特卡罗 generator， 你可以去在不同模型里边去产生一大堆的暗运，然后来做一些study。小结一下呢，就是这个在只有dark matter 的情形，没有 baryon 的情形，我们这些年和合作者，我们既做了 n-body simulation， 也做了semi-analytic modeling， 然后我们的结果是可以相互验证的，而且是 case by case predictions。什么意思呢？就是比如说这一页 PPT 我画的一些图，这些图里边它其实都是有2条线，实线的话是理论模型的结果，虚线的话是 n-body simulation 的结果。可以看到，对很多的这些线条就对应的是不同 halo， 我们都能给出 predictions， 而且它 prediction 的结果都还比较准确。所以这是一定程度上我们对只有暗物质的情形里边自相互作用的暗物质它 halo 长什么样子，我们心里边比较有一个底，有一个理论的预期。但是的话，我们去看实验观测数据的时候，我们会
每一个暗运里边，实际上它都是在非常中心的区域有 galaxies， 尤其是 star。这个的话是左边是 dark matter， 它的 density 的 distribution 比较弥散；右边这里的话是像银河系一样，它这中心有一个盘。这种情形的话，那这个图它告诉我们，就是实际上很多的那个星系暗运里边，它都有不少的。star， 然后它会对我们的观测产生各种不同的影响。这里我就举几个例子，一种的话就是说，如果你一个 sub halo 它有比较 radial 的轨道，那它在一个 host halo 里边演化的时候，它的它的 mass loss 在有 star 和没有 star 的时候会有比较大的区别。这里一个例子，这是针对一种叫做 dark matter diffusion 的 galaxy 它的起源，我们来做的 control 的 simulations。在在有 star 的情形，我们模拟是有 star 的，然后我们可以看到最后它的这个系统啊，实际上它是会被 star 的质量主导。但如果没有 star 的话，这个系统它就被 destroy 掉了。这是说这个例子呢，就说明这个baryon 的存在啊，它是会对 tidal stripping 会有比较大的影响。作为另外一个例子呢，我们去看一个 cluster 里边，这个是质量非常重的一个例子，它里边的卫星的那个质量，卫星 halo 的质量就都和我们银河系差不多，或者还会更重。在这种情况下，它中心的这个 star 实际上是会加速你这个系统的重热演化。这种加速呢，在这个系统里边，体现在它的这个 Vmax 后边会涨上去了，这是对应着gravel thermal evolution 它进入到了比较晚的时候，就是会有 core collapse， 暗运的 density 它变得更尖。然后这样的例子呢，在另外的 study context 里边，比如说就是冯卫翔同学他们的工作，会利用这种加速来解释早期高红移的时候那个超大质量黑洞的一个起源。这是第二个例子。第三个例子呢 ，OK， 这也是质量比较重的。我们研究的一个对象是所谓的 ETG， 它的质量的 scale 大概是10的13次方太阳质量。在这种系统里边，它的 star 的质量其实也不是特别多，但是它很致密，那就造成一个什么问题？这所引起的一个物理现象就是说，在暗运的中心，它这个 star 的存在会有一个 adiabatic contraction 的效应。这个 adiabatic contraction 它会改变你原有的 density profile。所以呢，当观测上大家看到了有 NFW profile， 大家可能觉得很开心，这个应该是和冷暗物质模型对得很好，但实际上不是这样。我们发现，你加了 baryon 之后，它 density profile 变得不是 NFW 了，反而如果你去加入一点 SIDM 的话，反而它倒和NFW 对得好了。所以这是一个非常有趣的 coincidence。OK， 就是前边举了几个例子，就给大家看，就如果有 baryon 存在的情况下，它是如何会影响我们的观测结果。实际呢，就是这个故事还会比较复杂。除了这3个例子之外，我这里画了一个图。这个图是什么呢？就是它里边基本上就是横坐标是 density， 纵坐标是 radius， 然后我们ρh 和 rh 是说这2个量在star 这边它的对应的量是什么，然后 ρs 和 rs 呢是说它在 halo 里边这2个量是什么。所以我们把这2个量在 star 和 halo 里边 take 一个 ratio， 然后看它在一个 cosmological simulation 里边的分布，我们会发现它这个分布啊实际上非常的弥散。这展示的是一个什么问题呢？就是说我们要面临的理论的 context， 我们要面临的这个观测上实际的这个 context 是比较多的，有很多种情形。我们对它的那个理解还相对比较初步 ，model 也会比较的困难。但是 whatever， 我们 leading order 的 theoretical understanding 还是有的。就比如说刚才提到了有 baryon 的时候，它的 gravel thermal evolution 可以被加速。那它到底会被加速多少呢？就今年我们也做了那么一个努力，就是我们基于一些有限的很有代表性的那个 controlled simulations with baryons， 然后再做一些理论的推导。我们能够把这个gravel thermal evolution 它有重子情况下的加速，到底会加速到什么样的情况，可以做一个理论上的估计。然后这个估计呢，我们把它表现成这个 core collapse time 它的一个加速。有 baryon 的情况下，它这个collapse 的时间会变短，所以这个量是小于1的。在左下角，你的那个 baryon 比较少，它效应就不明显。但是的话，再往右边右边过去，它是 log scale， 实际上这个效应会非常的明显。 另外一个方面呢，就是除了时间方面，radio 方面的话，当你有 baryon 存在的时候，它 adiabatic contraction 实际上也会改变你有 SIDM 下边它能够达到的 core 的这个 size。我们这里画它理论上有可能达到的最大的一个 core size， 然后把它用这个系统里边 stellar 的 size 来作为 measure。那我们会看到，在左下角的话，实际上这个效应非常的小，在右上角这边，它这个 baryon 的效应会非常明显，它会让你即使有 SIDM， 它的 core size 也非常的小。那个这样的一个理论的理解，它对我们观测会有什么样的一个影响呢？这里我举一个比较有意思的例子，就是左边这个是今年一篇文章里边他们做的一个 cosmological SIDM simulation with hydrodynamics， 就是说它星系的形成什么也有了 ，SIDM 它也有。然后他们看到非常有意思的一个事情，看的还是 Milky Way 的 system， 在这个 Milky Way system 里边，他们看到这个 halo 的这个 density 只会往上边涨。这个红移的话是更早的时间啊，红移等于2在这里，然后红移等于0的话，就今天反而是这个橙色的这个线，它一直涨上去了。其实这样的一个情形的话，也是和我们的theoretical expectation 是比较一致的，就我们会发现有一些这个 SIDM halo， 当你考虑了 baryon 的影响之后，它就 bypass 它的一个core formation 的阶段了，它的 density 会变得越来越高，而且的话，这种系统的话是在Milky Way 里边，就通常我们觉得哈，在 Milky Way 这种质量的星系里边，你 baryon 那么多，可能你的观测效应就全都说不清楚了。但是如果你有一个 population 的话，说不定这些东西就还值得挖掘一下。作为一个例子呢，就是比如说 lensing 这一方面。在2021年的时候，我们有一个GGSL 的Galaxy Strong Lensing 的这种 study， 我们研究的比较 generic 的 signatures， 就是它有 SIDM core collapse 的 halo， 它对这个 GGSL 的特征有什么影响？但是那个时候的话，我们没有比较仔细的考虑这种它只会变得更compact 的这种系统，比如说 Milky Way 的这种质量 scale。那今天呢，我们也许就可以再去 revisit 一下这些类型的 study， 然后就可以看一下它这种变得更 compact 的系统，它对我们的 lensing 的效应lensing 的东西会有什么影响。然后另外的话就是几个月前开会的时候，李然老师还在问我们能不能有一个全解析的办法来计算SIDM halo 这边 lensing 的效应。尤其是你的那个 halo population 很多的时候，这个是非常 computationally demanding 的事情。然后我们最近已经把这个东西基本上做出来了，就是可能再过几个星期或者1个月再给您汇报一下。OK， 然后因为我今天的 audience 有很多都是做 particle physics， 我自己原来也做 particle physics， 我们感兴趣就是我自己这些年的一个感觉就是，我觉得就是从 particle physics 出发的话，实际上 SIDM 也还是有一些可以觉得可以很有意思的地方，可以去挖掘的东西。尤其是对我来说的话，我觉得至少理论上哈，咱们的天文观测里边有那么多的 galaxies， 而且每一个 galaxies 它可以承载不同的 SIDM 的截面的信息，这一点的话，我觉得它是和 fuzzy dark matter 比起来很不一样的一个地方。就是这个东西怎么进去的呢？我又放一遍我们这个公式，就是它这个粒子物理这边，你不同的模型可以给不同的一个 differential cross section， 然后它不同的那个暗运的话，你把它 couple 起来之后，会得到一个不同的等效截面。所以也就是说，你同样的一个模型下边，也许你在 dwarf galaxy scale 这里，它的截面可以高到100个平方厘米每克这样的截面，但是你在 cluster 这边，它可以是一个很小的一个截面。这在一个 velocity dependent cross section 里边是非常自然的，而且即使是在同样的质量的 scale， 你不同的 halo concentration 啊什么的，它也会有不同的 predictions。所以我感觉这部分其实它是有 rich data， 但是只是我们的理论的 prediction 还有观测的那个 uncertainties 我们 control 的不够好，所以我觉得这里还是有很多的 opportunities， 就是大家不管是理论还是观测，其实都可以做好一些有意思的工作。我的报告就到这里，谢谢大家。
好，我们非常感谢杨老师的报告，有问题欢迎提问。
非常精彩的报告，感觉跟前段时间在山西听的又有变化。 那个 analytical 的那个 formula 我非常感兴趣，因为最近有一个学生在用这个就是 CIDM 的这个 density profile 再去拟合strong lensing 的这些 perturb， 所以如果你们直接有一个这个 analytical potential 的话，可能我们也可以直接用一下，去把这个事情做起来。然后就是关于你的 Milky Way 的这些，就是较大一点质量的这些研究，一个问题呢是说在观测上面，实际上不管是这个 Meneghetti 的这个observation， 还是说其他的一些这个 elliptical 的 observation， 它都涉及到这个就是 IMF 简并的问题，对吧？就是因为你原则上可以去调整这个有多少的 star， 它是很暗的、不发光的，然后来去得到同样的这样的一个质量。所以你在这里边这个是怎么考虑这个问题的呢？
对，您说的这一点非常的关键，就是实际上我们是没有办法只通过一个观测你去理解的多好去来解释这个问题的。我觉得我个人的感觉是我们现在就是需要某一个 population 它的那个观测上的准确程度都要提上去，然后的话就是然后的话，我们还需要去去研究它反推出来的暗晕它的性质。这里是一个例子，这是
矮星系的，对吧？这些应
这个不是
该都
矮星系的，
都是矮星系 DDO 什么 UCG。
对，它这里可能比较混，就是各种都有一点。但是它这里这个文章它的一个 point 就是于老师和其他的一些合作者他们做的工作，就是这里我自己take away information 就是实际上这些 rotation curve 你可以用 SIDM 拟合，你也可以不用 SIDM 拟合，你也可以用 feedback 拟合，好像拟合都还不错。但是 SIDM 下边的话，你去看它的那个反推出来的 halo 的性质，它可能会和你的那个concentration mass relation 啊这些符合的比较好。
对，我觉得这个很有意思，就是我们其实上次当然我们也讨论了，就近邻的这个我不知道多少个兆 BC， 红移到0.2以内的这么10000个星系，实际上我们都有它的旋转曲线和这个 profile。然后矮星系当然手里边也有一些，也许我们考虑一下去做一些分类，把它的这个恒星的形成历史和它的这个这些东西分成几类不同的星系，比如说看看这种就是有共性的星系，它最后是不是有一个有共性的 profile， 还是说有共性特征的星系依然有这种 diverse 的 profile， 可能能够从这个角度来去回答一下，就是到底我们是不是能用这些 diversity 来，就这种 diversity 到底是来自于星系的，还是是来自于 dark matter 的？就比如说，如果我们对所有的星系去做一个自组织图的分类，我们就找到类型很类似的星系，我们知道它的重子物质 probably 影响差不多，但是你去看一看它的 dark matter 是不是非常 diverse， 对吧？
对，这个point 呢，就是我们知道文献里边解释 diversity 不止 SIDM 嘛，其他的 mechanism 也可以解释。但是 SIDM 这边我觉得接下来可以去比较好的挖掘的一个点，就是说 SIDM 它的 prediction 是不只是说你能解释那么一个 spread， 就是我们实际上只要你基于一定的假设，我们是可以 case by case 给 predictions 的。这样的话就你其实是可以理论上是可以 case by case 去检验，那虽然实际上这个会更困难。对。
我们还有其他问题吗？我问一下那个你除了这边主要是考虑这个自相关的这个 dark matter 有考虑很多那个 WIMP 之类的这个情况吗？
就是SIDM 这边的截面它是sigma over m， 它自己本身是对 dark matter 的质量没有敏感度的。
OK，
所以对，你可以很轻，也可以比较重。
OK， 好，行，那我们再次感谢这个杨老师谢谢。下一位报告人是波尔所的陈一帆老师。报告题目是这个Probing fundamental physics via supermassive black hole observations。欢迎。
好。我首先想感谢那个组织者，然后给我这次机会，就是我是波尔所的博士后，就是我的报告题目是换页是，怎么换页是？那怎么往前呢 ？OK， 好，谢谢，行，对，就是 所以我的报告会就是关于超大质量黑洞，所以就是为什么要讨论黑洞呢？就是说黑洞对于这个 dark sector， 就比如说暗物质或者这个极星玻色子来说呢，它是一个聚集作用，就是它在这个黑洞的附近呢，它可以就是这种标量或者矢量的玻色子，它会就是通过超辐射机制形成非常致密的这个所谓的超辐射云，然后这些超辐射云呢，它的那个场强可以非常强，所以它可以就是在黑洞附近有很多的现象可以发生，就是放大了它的信号，就相比地面的暗物质搜寻。另外一方面呢，就是刚刚那个邵江老师也说，就是在一个超大质量黑洞附近，你如果有这个一个星系的暗物质分布或者这个恒星分布的话，它这些会通过一个所谓的绝热袭击，是那个冈多罗苏克提出的，在这个超大质量黑洞附近呢，会形成非常陡的一个能量密度，然后所以你就放大了你的这个比如说暗物质的湮灭的这个可能，然后它们的那个能量密度可以是这个地球上暗物质的这个10的14方到24方的这个倍数，所以它是一个非常强的这个 enhancement， 所以我们一般可以认为就是黑洞它是一个非常强的这个转换器，对于这个 dark sector， 甚至就是包括这个重子物质，然后所以也就是说，我们可以通过对黑洞的观测去搜寻对这个暗物质或者对这个星系分布的这个影响。然后这其中呢，就是最近有2个非常重要的结果，就一个是这个黑洞世界望远镜，还有一个就是脉冲星计时阵列对超大质量双黑洞的这个随机背景引力波的这个观测。就是因为我自己是这个下一代 EHT 和那个 Nanograph 的成员，所以我会简要的介绍一下这2个结果，然后就是会非常简略，然后如果有问题我们可以之后讨论。所以我讲的第一部分呢，就是说，就是关于这个所谓的黑洞照片，然后黑洞照片是由这个所谓的黑洞事件世界望远镜拍出来的，然后这个合作组呢，基本上就是你把不同的这个射电望远镜在世界各地你组成一个阵列，所以这样的一个好处呢，就是你等效的这个口径就可以相当于地球半径那么大，就是你有一个地球半径那么大的一个望远镜，然后这是这一代，就是说你会拍出一个这样的一个甜甜圈一样的东西，然后我们之后还会有这个所谓的下一代这个黑洞事件望远镜，就会有更多的望远镜加入，然后还有一个就是空间的这个射电的阵列，这个有一个项目叫 BEX， 就是会放一个卫星到天上，然后所以你会得到一个更好的这个有效分辨率。然后其中非常重要的一个目标呢，就是测所谓的光环。光环的意思就是你如果去解一个科尔背景下的这个测地线，然后它的这个就是所谓的 new geodesic 在一个科尔 background， 就是你这个 geodesic 呢，你会发现它形成一个 bound state， 也就是说它可以绕着这个黑洞转好几圈，然后再最后到达地球，就是原则上可以转无穷多圈，但是这个实际会就是受限，所以这就给了一个非常精密的测量这个新物理的一个方法，就是我们有反正一系列工作，就是用来比如说测那个超辐射云，因为超辐射云会辐射引力波，还有就是如果是有一个黑洞合并的时候，你这个合并完了以后，它会有那个所谓的 rain down， 其实也是一种引力波，然后你可以就是通过这种光子的 lensing 去看这个 rain down 的这个空间分布。还有就是我们搞了一套算法，叫这个向前发射，可以去用来计算点光源绕黑洞附近转好几圈的这个成像，这是一方面。然后还有一部分很重要的就是说，黑洞事件望远镜还揭示了这个光的偏振，就是这个由这个黄色的这个虚线这个告诉的，就这个是偏振呢，就其实是线偏光的这个投影方向。它同时因为这个线偏光呢来自于是同步辐射，所以它告诉了我们这个在黑洞附近磁场的这个分布，这个磁场分布就是可以告诉我们很多天文的过程。然后另外一方面呢，就是说有一种新粒子，就是通常说的轴子，它和光子的耦合呢，可以去改变这个线偏光的投影方向，会造成一个周期性的振动。所以就是我们有一系列工作专门去就是去用黑洞照片的这个偏振数据去限制轴子和光子的耦合，还有就轴子和暗物质的这个限制。然后这个大概是一些示意图，就是第一个是一个光子测地线，它这个在黑洞附近它发生劈裂，就是由于引力波的这个微扰作用。还有一个就是这个可能动画这个用的软件不对，可能没显示出来，就是说它的偏振的这个投影原则上可以震荡，就是这个绿色的虚线可以震荡。OK。但是就是我这个报告主要还是讲的就是不是这种极轻的玻色子暗物质，因为这个之前讲太多了，所以我主要会讨论就是粒子型暗物质，或者这个就是一般的星系重子物质。然后 但是有一点我觉得非常重要，就是这个黑洞事件望远镜，就是先不说新物理啊，就是说在下一代的黑洞事件望远镜，它可以看一个东西叫所谓的 inner shadow， 就是这个里面这个 inner shadow 呢，物理定义其实就是你的这个黑洞的世界。就是和那个黑洞赤道交的那个圈，它被 lens 的这样一个投影，也就是说我们在下一代的 EHT 可以直接看黑洞的世界。它的原因在于什么呢？就是说通过我们这一代的 EHT 的观测，我们可以知道，就是说你黑洞附近这个物质的分布，这个是一个电子的分布图。我们可以看到呢，大部分的电子是就聚集在这个赤道平面，就是所谓的这个吸积盘，它是一个相对比较薄的这个几何薄的一个这个东西，它是通过这个 GRMHD 的 fit 这个得到的。它不是非常准，但是这个 more or less 就是告诉我们这个 feature 是这样的。所以就是说你在这个 jet 附近呢，就是说它是一个喷流，就是它的磁场很强，但是它的电子疏密度相对比较稀薄，因为它电子疏密度都会被踢走。然后这就造成了什么呢？就是你的光的辐射呢会一直截断到黑洞的外世界，和这个赤道的交点，就是这个点。你在这个里面呢，它的那个辐射就一下子剧烈的下滑了，这也就造成了这个所谓的 inner shadow。就是这里面有个误区，因为过去大家说这个 shadow 就是说是这个 critical curve， 也就是说这个虚线是光子转无穷多圈的这个边界的定义。但是这里面呢，你其实还是有辐射的，所以它并不是完全黑的。真正黑的就是这个 inner shadow。但是我们这一代的 EHT 看不到的原因在于，就是我们的因为我用的这个图是一个 log scale 的图，我们这一代的 EHT 呢，你只能看这个最亮和最暗之间1/10差别的这个地方。然后这个就是所谓的动态范围，就是比如说你打开手机摄像头，它有个 HDR 模式，就是 High Dynamic Range 的一个意思。然后下一代呢，你这个下一代 EHT 可以看这个倍数，就最亮和最暗大概有1000倍，这个就使得我们可以把这个黑洞的阴影真正的给看出来。然后看到以后，我们就可以就是通过一些时间平均的一些算法，我们可以大概知道你的这个外世界的这个轮廓形状，就是这一点是非常重要的。然后我为什么要说这一点呢？就是因为就是刚刚说了，这是一个真正的阴影，这个阴影呢就可以用来限制一些这个暗物质，其中之一就是所谓的暗物质湮灭，就是这也是一个这个比较传统的暗物质搜寻方法，就是所谓的间接探测，就是然后刚刚说了，就暗物质呢可以在这个黑洞附近就是造成非常强的这样的一个这个袭击，就是所谓的这个绝热袭击，就是你从一个 NFW 的这个红线出发，这个不对，这个黑色虚线出发，然后你在这个黑洞附近呢，由于黑洞引力势的这个作用呢，你对暗物质的相空间进行一个绝热映射，就这假设你这个超大质量黑洞长得是非常慢的，所以它是一个绝热的太氧化，然后红线呢就表示你这个暗物质它是没有任何的相互作用，是一个纯引力相互作用。然后这个不同颜色的线呢就表示你有一个截面，就湮灭截面，你可以湮灭到标准模型或者其他的什么东西。然后这时候呢，你的中间就会变成一个平坦的 core， 就是这依赖于不同的这个截面。然后我们考虑的呢是相对就是比较简单，就是说我们考虑你莫泰可以湮灭成正负电子对，因为正负电子对呢，你可以有同步辐射，然后它的一个效果呢，就是所谓的我们说它可以照亮你的这个黑洞阴影，然后就比如说这两张图，左边这张图就是标准的这个 GRMHD 的这个图，里面一个非常漂亮的这个 inner shadow， 然后这右边这个像个龙珠一样的，就是说你加了暗物质，加了一个这个暗物质的，就我们考虑了它的传播，就是说我们还同时考虑一个就是各项异性的这个基于这个 GRMHD background 的一个这个 cosmic ray 的 propagation 的 equation， 我们把它给 solve 之后，然后就是说可以得到右边这个电子疏密度，你看在 jet 附近它就很多，它可以占据这个 jet 的主要区域，然后这个深色的蓝色区域呢，就是说它 jet 以外的，这个就是我们不考虑这个区域，所以就是说这个暗物就是take home message， 就是说你这个暗物质可以把这个黑洞阴影给照亮。所以呢，假设我们看到了这个阴影，那我们就可以对黑洞暗物质呢进行一个非常强的一个参数的限制。就是这个下面这个图呢，就是一个一维分布的这个 intensity， 这个红线是这个暗物质，蓝线是就是 GRMHD 的背景，就是。然后这个是通过一个高斯斯米尔的，然后右边这个图呢就给出了我们这个对暗物质这个湮灭 channel 的这个限制，就是这个是考虑 BB8， 然后蓝色的这个线呢就是基于你如果要求它的总辐射强度小于你这个看到的这个，就是没有利用它的 morphology 的这个feature， 然后这个绿色线呢就是基于这一代的 EHT， 就是这一代 EHT 虽然看不到 inner shadow， 但是这中间一块还是暗的，就我们就用现在这一块暗的去做一个限制，你看明显就比这个蓝的要好很多，然后黑色呢就是用下一代 EHT 的这个动态范围，就是你可以看到1/1000最亮的这个地方，所以它限制的范围就大很多。这个是对于 BB8 channel， 就是说它是一个非常简洁的这样 样的一个形状。然后我们同时考虑的对 E1 就是电子道的这个散射，就是说这个就可以探索 sub-GeV 的这个区间就在这里。然后这个紫色虚线是那个就是 freeze out 的那个 thermal relic 的那个线。OK。所以这个就是我第一部分要讲的，就是还有一部分呢，就是讲的就是跟那个邵江老师说的是有部分雷同，就是说我考虑的是脉冲星计时阵列。那脉冲星计时阵列的原理呢就很简单，就是说你的那个引力波传播会对光子的测地线进行一个扰动，然后呢这个扰动包含了这个传播路径和你这个观测者和这个发射的地方，就是大概是这样的一个示意图，就是你一个脉冲星嘣传到地球，然后这时候呢，你可以通过去关联不同脉冲星的这个信号呢，你可以去就是大概100个左右，就是其实是小于100，就是你把不同的加起来，然后你可以去做这样一个红移的这个关联，你可以得到就是一个这个对随机背景引力波的这个一个判断。这个判断呢是基于你这个关联是有一个这个所谓的 quadrupolar nature， 这个就是非常有名的叫 Helling-Stone correlation， 就这个。公式是非常漂亮的，就是它告诉了我们看到的这个信号呢，它确实是一个有张量性质的东西，那就只能是一般是引力波，因为其他的噪声是不能 mimic 这样的一个空间关联的。然后另外一方面呢，就是说这个。就是这个 violin 啊，就是这个是我们看到的数据。这个 violin 呢，就是显示它目前探测到的这个引力波背景谱呢，它跟超大质量黑洞population 带来的预言呢，它拟合的非常好。但是有一点很重要，就是说它第一个病呢比预计的要低一些，就是说这个紫色的虚线就是你假设它是完全超大质量黑洞，然后只有引力波辐射，然后都是原轨道下来，然后这个蓝色的线呢，就是说你考虑一个这个 population model， 就是然后这个第一个病就是你考虑一些环境效应或者就是有 eccentricity 的时候，它会比预计的要低一点，然后所以未来呢就是去研究这个。spectrum 它为什么有这个 turnover， 然后这个 spectrum 在高频它的一些性质，我觉得是非常重要的，因为这首先是区分你这个宇宙学和那个黑洞起源的一个方法。所以就是说我们还有一个工作，就是说利用这个其他的天文观测，就有一种就是所谓的这个天测，就是那个我不知道怎么翻译 astrometry， 就是你看一个恒星的演化，就是在这个图里面，你看一个恒星在2维平面上的这个投影，然后其中有就是比较重要的就是盖亚卫星，因为盖亚卫星有时间的观测，就是对那个非常精密的测量，因为你光子的测地线就是这个 star 传来的测地线也会被引力波传播，所以原则上这些可以就是进行一个交互关联，然后可以得到一些这个参数估计。然后我刚说了，就是说。在这个原轨道下呢，它是一个非常简单的这个 power law， 就是这个 strength 是走的频率的负的2/3，但是呢，这个刚刚说了，这第一个病有一个 turnover， 所以有不同的解释，就是说刚刚说的有eccentricity， 还有就是可能有一个环境效应。然后比如说在这篇文章里面，他们讨论了就是说妥度的影响，就是或者说怎么去区分妥度。然后一般呢，他们用的那个环境效应，就是在这篇文章里面都是一个 phenomenological environment effect， 就是它假设有一个额外的 hardening 的一个东西，OK， 然后就是说因为它只有最后一个饼，所以你更长的观测时间，原则上可以就是把这个 turnover 去就是加深理解。然后在我们这个研究里面呢，就是我们是基于一个就是比较 minimal 的假设，就是我们就假设你黑洞附近有一团物质，这团物质呢就是说要么是这个恒星，要么就是冷暗物质，就是说我没有假设它有任何相互作用，就是说就跟邵江老师可能不太一样，所以就是说你一开始就是相当于2团东西，然后这个东西呢 ，N-body simulation 别人很多都做过，它有非常强的所谓的 back correction， 意思就是就是陈贤老师刚刚说过，就是你黑洞在绕转的时候呢，你黑洞的轨道能量会就是通过这个3体的引力弹弓踢走这个一部分的分布，所以你最后呢就是说你会形成一个这个合并成一个，这个合并成一个的时候呢，你的中心的能量密度就相当于被抹平了。就是这样一个过程，所以它是一个非常动态的过程，就是说你同时要考虑轨道的这个演化以及这个中心的能量密度的这个演化，所以就是说你如果要去拿它去做这个数据分析呢，它其实是很困难的，因为你不同参数这个演化情况还不一样。但是呢，有一些就是简化的方法，就是考虑的所谓的3体散射。这个3体散射呢，就是说我放一个固定背景是一个双黑洞，然后这时候呢，我往里注入一个这个简单的 test particle。这个 test particle 呢不改变你这个双黑洞的轨道，但是呢，我这个 test particle 可以绕着它做这个测地线。这样一点就会和那个钱德拉塞卡的那个就是 dynamic refraction 的有很大的区别，就是你现在背景变成一个时间绕转，就是时间变化的一个绕转的背景。这时候呢，你这个 star 可以绕其中一个黑洞。 分别绕转好几次。这样一来呢，就导致你这个所谓的三体散射比钱德拉塞卡考虑的那个两体散射，它的截面要大非常多，因为你这时候截面就变成了这个黑洞的这个轨道的这个半径决定的那个截面，然后。你如果是只有一个黑洞的话，它的截面大概就是一个黑洞它的一个引力范围，所以在这个过程呢，一般是就是认为你有一个所谓的 hardening radius， 当你的轨道半径小于这个 hardening radius 的时候，这个三体的效应会主导，然后。这个过程呢，你可以去和那个 N-body simulation 进行一个比较，就是这个 Cesena， 就是那个陈思源老师的这个导师，他们比较以后呢，发现这两个过程其实可以就是去做一个解析的近似。这个解析的近似呢，就是说你取一个这个 uniform 的背景 ，uniform 的 star 背景，然后这个 star 你把这个rho 和 rho 就是能量密度 ，sigma 就是这个 velocity 的 dispersion， 你把它取在这个初始这个分布，就还没有碰撞之前那个分布的所谓的 inference radius 处。就是这是黑洞的引力势能，就表示在这个地方的相空间，它的那个就是它的那个太空间是比较满的，因为你这个天文上会有很多的讨论，就是讨论所谓的 loose cone 的 population， 所以在这个 loose cone 的 phase density 上，它永远是满的，这也导致为什么你可以比较 N-body simulation 和这个三体的散射简单的，所以我们就用了它就是定义的这个关系，我们同时考虑了就是你的那个妥度，因为妥度也会造成你的谱的这样的一个偏折，所以我们进行对这是一个星系的物质的分布进行一个参数化，就是我们考虑的它 normalization， 还有它的伽马，就是它的就是 slope index， 然后你比如说你伽马可以取这个0到3，一般是0到1/2呢，我们认为一开始是个 core， 然后1就是所谓的 NF 的 reprofile， 然后7/3呢就是刚多尔苏克 spike， 然后其实就3个参数，就一个初始的偏心率，还有你的伽马和你的 ρPC， 所以最后的结果呢，就是说我是一个正面的信号，就是说告诉我们你的那个 ρPC 和你的 E0， 就是你的偏心率之间呢，它有一个微小的简并，就是说你就是偏心率越大呢，你需要的物质密度就越小，这是因为你引力波辐射本身也强了，然后它 fit 的区域呢，大概就是这个所谓的这个是一个太阳每PC cubic， 这大概就是10^5次方太阳质量 PC cubic， 然后差不多就是10^6 GeV cm3 应该是。然后这个能量密度呢，它不是一个非常大的能量密度，因为就是说，你如果考虑这个银河系的这个恒星或者银河系的这个暗物质的这个一些模型的话，当然 spike 很困难，因为 spike 它这个伽马太陡了，太陡之后呢，就导致就是刚刚说的那个 argument， 就是你取在这个所谓的 inference radius 处的值呢就比较小，所以我们这边反倒是不是特别 favor 一个就完全是 spike 来解释这样的一个 hardening process， 我们倾向一些比较平坦的这个恒星分布，一些这个平坦的 core， 因为这个也比较好理解，因为你这些超大质量双黑洞合并呢，它一般就是它这些超大质量黑洞一开始都是由这个合并产生的，所以它有一些过去的合并史，所以它可能已经把这些就是暗物质已经就是相当于抹平了，就这也是解释就是刚刚说的那个杨大能老师说的，就是它会有一些 diversity， 就是说不同星系它有的比较陡，有的比较平，就是一般大家会用超大质量双黑洞去解释，OK， 所以就是未来呢，我们有一个要接着就这是我们就是和Nanograph 合作组发的这个合作组文章，然后未来呢主要目标就是为了去打破这样的一个能量密度和你这个偏心率之间的简并，就是大概有不同的方法，就是说我们可以做这个不同的数据分析的方法去检验这样一个妥度，所以我大概总结一下，就是说黑洞是非常这个有效的一个这个转换器，对于这个暗物质或者对于这个重子物质来说。然后这个我大概讲了2个例子吧，就是说其实可以有很多，一个是这个黑洞事件望远镜，就是说你因为你高分辨率，然后高动态范围，你可以看这个暗物质湮灭，就是说你湮灭把这个所谓的 inner shadow 给照亮。还有一个就是脉冲星计时阵列，它可以做一个所谓的星系的这样一个拓扑。我不知道怎么说 tomography， 就是说就你探索星系的这个在 parsec scale 的这个物质分布，就是然后用这个目前看已经有这个倾向的这样的一个谱线上的 tune over 去看这个东西。好，非常感谢的。
好，我们谢谢陈老师，欢迎提问。OK。
那个你们做的那个暗物质的和这个双黑洞的相当于三体散射，这个当然是很有意思的。那么原来用恒星的那个方法做散射呢，事实上是因为恒星和恒星之间 和黑洞之间只有引力相互作用，对吧？
对对对。
如果现在考虑的是 self-interacting dark matter，其实更像流体。
没错没错。
事实上又跟他们考虑情况不太一样，你要
对
加一点那个流体的心进去，不知道有没有考虑过？
我们考虑过，就是说这种过程呢，是这样，我觉得其实是分3种，就是一种是纯粹的粒子散射，就是我每次扔进去一个 test particle， 或者我做纯 n-body simulation， 然后 n-body simulation 呢，跟那个流体其实某种意义上也能 match 一些。就是说，你那个流体，如果你认为它的那个就是你 property 是完全就是你可以定义一些 property， 它最后会比较接近，就是但是呢，你那个 loose 控的补充你是体现不出来的。就是
可能流体跟这个纯引力相互作用的恒星之间的作用是流体跟流体之间多长时间碰撞一次。
对，它那个
时间太长的话，那你就可以做纯散射实验了。
对。然后我们在做的一个东西呢，是比流体更极端的一种，就是所谓的极轻波色子。就是这个，比如说那个杨环老师、张军老师他们也在做，就是说你考虑双黑洞附近，你加一个欧出来的波送，然后它的波送呢，它的那个德布雷波长很长，然后它是有一个离散性质在那里，然后在那个情况下呢，就是说它很有意思，它有的像2体，有的像3体，就是这个我们没有发出来，但是这个我们也想用那个 nanograph 去解释。对。
听上去。
然后 self-interacting dark matter 这个就是我觉得不同的模型，这个最后结果会很不一样，就是我们也在做，就是等等，对。
我问一下，我其实就是因为我知道他们就是如果是在 dark matter halo 的话，它黑洞是有一个不同的 metric 的解。
对。
这种方法能不能直接算引力波呢？
算引力波的话，这个很复杂，就是看黑洞的度规是可以的，因为它那个度规就是测地线，它首先可以
shallow 是可以 shallow， 然后
shallow 可以，
轨道都可以。
然后算引力波的问题是，就是说它这些暗物质跟着黑洞一起动，还是说它只是均匀的分布？因为你现在是一个双黑洞背景，对吧？然后你是看 rain down 还是看那个，比如说 in spiral， 这个可能也不一样。
它这个应该就是整个把 metric 都变了，所以确实它在这个合并的过程中，它可能你要算一个双黑洞对应的 metric 再去解。
如果是合并的过程中呢，就合并完了以后呢，它可能那些暗物质原则上都已经被弹掉了，就是说，就它在合并的末期，它的暗物质的影响应该是很弱的，因为你这时候肯定是黑洞度轨主导的。就是说，你暗物质就是我刚刚说了，就我这个是完全 in spiral 阶段，就是这个 PTA 的 in spiral 阶段呢，我根本不需要科尔背景，因为它就是它离得很远，相当于我就用牛顿力学就够了，一个开普勒轨道去算那个引力波，就 in principle 就 OK 了，因为你看不到那种广相的效应。
那就是你正常算，然后加一个暗物质的微扰，是吧？
在这里就是不是围绕，就是如果你问的是那个就是 merger 的那个东西，你就跟我这个不一样，就是那个的话，就是你要原则上你得解数值相对论，我觉得，因为那个本身你 merger 过程就不是一个可以围绕解的过程。然后，但是我的意思就是说，在那个过程下，你暗物质原则上已经被弹掉了，它的影响不可能很大，这是我的理解。就是它的环境效应，你想用目前的 LIGO 去看，我觉得很难。然后你如果用 PTA 看呢，就是我们这边的暗物质呢，原则上就确实就是也不能叫微扰，就是说它对你就是它是一个相对绝热的一个，就是它是一个比较慢的演化，就是它提取能量是一个很慢的，就是你每个轨道周期它提取的能量都是一个很小的能量，但是它对你的轨道的能量损失呢，它是就是至少在这个 turnover 的地方，它是比你引力波的辐射要强的，是这个意思。
OK， 我这边孙老师你先。
我就是在想你做的这个就是你就算了个 merger 嘛，然后呢就是
我不是 merger， 我只是 in spiral，
这个是
我只是 in spiral， 因为 PTA 看的还是比较早期的，就是我没有到那个 merger， 我只是就是还 pass 一个 skill 的。
但是你有3个黑洞。
我只有2个黑洞再加一个小的天体，就是说一个小的这个可以是暗物质，也可以是恒星，比它们轻很多。
就是 dress 了一下，看看
对
spectrum 有没有什么小波动。
没错。
哎，好。
我有一个跟那个孙老师的问题相关的问题，或者说是 comment 吧，就是这个，因为包括你第1页前面提到这个有就是黑洞周围那个超轻波色子的情况，对吧？那这会涉及到那个超辐射，然后超辐射的话，其实它是这个会有一定的这个可能的观测效应，因为它会你是相当于那个暗物质是在那边被黑洞生成的，然后它会这个相关的就是像包曼他们的文章里就是说这个 它会有一些这个会让它潮汐变形，有一定光测效应，但是他们只算了量级，没有算具体的这个数。
但是那个也是就是 in spiral， 就是它不是就是合并。
对对，就是
合并那个
前期的那个情况。
对，它而且它那个是全是 Emery， 就是不适用于这种等质量。其实这也是为什么刚刚跟陈老师说，就是我们考虑双黑就等质量双黑洞就完全不一样，就变成引力分子了，就是。
然后还有一个小问题，就是你关于它那个 tensor 的那个情况的分离变量有了解吗？
tensor 的东西就是你说 equation 模型的分离变量，那个我的理解是没有人做出来，就是。
OK， 就是现在就是还有就是只能到 vector 是吧？
对，到 vector。tensor 那个 Well East 他们想做，但是目前应该还不成功。
OK， 好，谢谢。
谢谢。
好，还有其他问题吗 ？OK， 那我们再次感谢陈老师的精彩报告。好，我们接下来这个4点半回来啊。现在是茶歇对吧？
about probing dark matter with gravitational wave interferometers in space. So this talk is based on the following recent publications. So I don't need to emphasize that there are a lot of evidence for dark matter, and then there are also a lot of theories. And in this talk, I will focus on two particular kinds of dark matter. One is weakly interacting dark matter. Another one is ultralight dark matter, where action is one of the examples. So I think everyone is very familiar with the WIMP, and it has very nice motivation, and also it can have a very nice explanation for the radical density. And there are a lot of experimental and theoretical motivations for this. So actually, there are a lot of progress from indirect, direct, and kinetic search. So this is a very attractive dark matter. And another candidate is ultralight dark matter, which mass is less than 1 electron volt. QCD action is one of the example. And the number density for the light dark matter is very large, so it's basically behavior like classical wave. And these three plots shows that we have simulate the 3-dimension, 2-dimension, and the 1-dimension oscillation of the ultralight dark matter. So in this talk, I will focus on two kinds of dark matter, ultralight dark matter. One is scalar. So it depends on the property of the scalar. It can couple to effective operator of standard model operators, like couple to the mass, then it can affect the mass of the fermion particle. If the dark matter is a vector, then it can, if the standard model particle has another vector charge, then it can have a similar QED interactions. In such a case, it have a Lorentz force, so the particle moving in the dark matter background and induce additional oscillations. So there are a lot of physical effects for this ultralight dark matter, and I think you have heard a lot of things in the past talks like Huaike and Liu Jia, and also the superradiance effect. So here I list some reference, but I'm going to focus on the space telescope, space interferometer, that including LISA, Taiji, Tianqing, and there are a lot of other proposals like DCIGO, BBO, LISA Max, and also GW, and also a lot of future projects. For example, this one, the MURS is kind of a project with 3 satellites orbited on the orbit of Mars. So it has a lot, much longer arm length. So for LISA, Taiji, Tianqing, it has such kind of structure. Usually it's the 3 satellites orbiting around the Earth or around the Sun. So this plot shows that it has a different sensitivity curve. So the basic principle is that gravitational wave can change the structure of space-time, then it can change the physical distance between objects. So we use a laser light to measure the distance change. And then from the phase change, we can infer the frequency change. And the frequency change depends on the gravitational wave form. So we can use a data analysis to infer the information from the gravitational wave. So for WIMP, these particles can be aggregated by the black hole, so it can form the dark matter spike. You probably already heard from the Shao Jiang's talk, and also the Yifan's talk. So in these plots, actually, we include the velocity effect. So we simulate the dark matter accretion around the black hole, and we take into account the velocity distribution so that the dynamic friction from the dark matter particles can be included. So this plot shows that if we include the dynamic friction, it shows that change that the gravitational wave have a phase change in the waveform. And then we can do a Fourier transform to the frequency spectrum, and you can see that there is a suppression in the low frequency, and there is an enhancement in the high frequency. So this is the fitting plot, fitting formula. So we take the relativistic treatment, and the profile around black hole can be fitted by this formula. The first factor is just power law, and this power factor is around 2. And the second factor is that it can goes to 0 when the radiance is equal to 2 times of the horizon. And this factor is also around 2. So this is the fitting factor we gave for this universal density profile. And also we show some the distribution of velocity around the black holes. So and this is the fitted formula for the velocity distribution. We can simply use the Gaussian distribution with the central value, and also uncertainty depends on the radiance from the center. And take all this into account, we can show that there is a difference with or without dark matter density profile. So this is for wind particle. And the second part is about the ultrawave dark matter. So actually, the detector does not know whether the signal is from gravitational wave or from other source. All it knows is that the distance between the two free falling tensor mass is changing. So we can also calculate the response of the tensor mass when it's moving around the dark matter background. So it depends on the interaction. We shows that for scalar field or scalar dark matter, for vector dark matter, there is a factor. This factor depends on the propagation direction, or depends on the polarization for the vector. And this is different from the gravitational wave factor. So you can see that they have a different form. So later I show that because of this difference, we can construct a different interferometer channel that can distinguish between the scalar, vector, and the tensor. So this is the interferometer we are going to use, because it has 3 satellites. So it's not just one interferometer. It actually has a lot of combinations. And you can have a Michelson, a segnetic, and a symmetric zeta signal. A zeta channel. So if each different combinations give different response sensitivity. So this is the transfer function shows that the difference between gravitational wave, which is the red curve, and the scalar dark matter and the vector dark matter. You can see that it has a different response transfer function in the low frequency range. So this is for segnetic combination and symmetric zeta combination. You can see that there is a difference can tell the gravitational wave, scalar, and vector. Now we have the transfer function, and then we can use the transfer function and also the noise function from the different group, like Lisa, Taiji, and Tianqin. So you can see that they have a different response, different noise parameter. And we use the noise function divided by the transfer function, then get the sensitivity curve. So this 3 plots shows that this space telescope has different sensitivity curve for scalar fields, vector field, and a gravitational wave. Okay, this is we make another recombination, combinations that shows the optical channel. So in such a case, you can distinguish scalar, vector, and gravitational wave. So now I come to specific models. Suppose you have a scalar. It couples to the strong interacting sector, like a gluon or the fermion mass. Then it can have an effect on the effective mass. So we can use this telescope we can use the interferometer to probe this kind of coupling. This coupling is DG. You can see that the different experiments give different sensitivity curve, but the most sensitive one around this 10 to minus 16 electrovolts is given by Taiji. So this is actually about 1 order of magnitude better than the current best one, equivalence principal test from microscope, which is France satellite. And that one we use the plane wave approximation. But if we take into account the velocity distribution, and then we also do a likelihood analysis, and then we can have a conservative limit or sensitivity, which is given by the red one, which is a little bit worse than the original one. So you can, but still in the same order. And this one shows that the most recent one by microscope, it has a factor 2 improve of the previous result. So compared to their result, the projection of future Taiji sensitivity is still a factor 2 better than their limit. And for vector dark matter, we consider 2 models. One is that the vector coupled to a baryon number, another one is a neutral number. So you can see that in such a case, the sensitivity from Taiji is much better than the equivalence principal test, like microscope. Actually, it's about 3 to 4 order of magnitude better in the mass range, around 10 to minus 16 electrovolt. Next one is that it's a very recent proposal that we can also consider action photon coupling, because the laser from each satellite is traveling through the action dark matter background. Suppose they have such kind of similar interaction, then the left and the right-handed polarization have different phase velocity, so they have a different phase change when they travel through the dark matter background. So we can change a little bit about the 3 satellites polarization of the laser. The clockwise and the counterclockwise each have a different polarization. In such a case, we can construct the Segnac channel and shows that it's sensitive to this coupling. And to our surprise, that the sensitivity is much better than the current best one from supernova and also other from quasar or some X-ray observation. So this is the most sensitive one from Taiji is the green curve. You can see it's around 10 to 17 electrovolt. And the future one by this orange line is BBO, which is the Big Bang observatory proposed by US. It has an arm length of about 50,000 kilometers and orbiting around the sun. So you can see that with this space interferometry, we can have also very good sensitivity to the action dark matter. Finally, let me mention that the previous one all assume that dark matter has a coupling to the standard model particle. Suppose that there's only gravitational interaction. And actually, there are a lot of theoretical motivations. And we also did some work to study the production mechanism in the universe. And it shows that there are a lot of Faraday space for such kind of dark matter. So for production, there is no limit for this kind of candidate. Then, if the dark matter is very light, it can oscillate and induce the metric fluctuation around the solar system. So we actually can calculate the metric fluctuation from dark matter oscillation. So in such a case, the 3 satellites is orbiting around the sun or around the Earth. It can feel the metric fluctuation induced by the dark matter oscillation. So we can also infer from the data that whether the signal has a monochromatic signal, which is just 2 times of the mass. In such a case, we can calculate the sensitivity from each different interferometer. So the left one is for scalar dark matter, and the right one is for the vector. And the vertical axis is the sensitivity to the dark matter density. So if it's equal to 1, then which means the experiment has a sensitivity to the local dark matter density. If it's less than 1, then it means it can probe the local dark matter density. So you can see that for scalar dark matter, the most sensitive one is around 10 to 3, which means it has not reached the limit yet. But for vector dark matter, it can be less than 1. It's around 0.1. So we can have such kind of sensitivity. And this property line is from the MURS. It's a future plan. I don't know whether it can be launched, but it must be after LISA or Taiji, maybe 20 or 50 years later. But the good news that with such kind of interferometer, we can have a sensitivity to the local vector dark matter. Let me summarize. So I have discussed how the gravitational wave detector in space may help to understand the nature of dark matter. And I consider two kinds of dark matter. One is weakly interacting dark matter, and it can form spikes around black hole and affecting the orbiting compact object, and then implement on the wave of gravitational wave. So we consider the velocity distribution of dark matter particles. The previous one has not, the first study has probably neglect or incorrect take such kind of effect. And then we also consider relativistic effect. People usually do the Newtonian analysis, but around the black hole horizon, then relativistic is actually effect is very important. And the second part is about ultralight bosonic dark matter, which is probably it's wave-like, so it can come to normal matter and induce the oscillation of test mass, so leading to the signal in detectors, and it can have a very good sensitivity around some mass range, and it's much better than the current other kind of experiment. So the final one is that even dark matter only has a gravitational action. If its mass is very light, it can induce the metric perturbation around the sun or around the solar system. Then the detector can also feel this kind of oscillation. So that's all. Before, also I have to kind of introduce this journal, and you are welcome to submit your work to this very good journal. It has a very high impact factor, and it's run by the Chinese Academy of Science. So that's all. Thank you.
Okay, great. Thanks for this interesting talk. Questions?
Thank you for a nice talk. So my question is that if the black hole is like a primordial in nature, so what do you expect, for example, asteroid mass range black hole?
I didn't hear. So suppose dark matter is primordial black hole?
No, let's say there are some fraction of the primordial black hole.
Okay.
And on the surrounding of that, there is a particles like you are mentioning. So what do you expect that can you detect possibly like those mass of PBH or some possible way to look for that?
So I'm not sure whether it has some effect on the gravitational wave, but if it's annihilating, maybe density around this black hole is very high, so it can annihilate to gamma ray or other charged particles, then it can have a large signal. So that's probably is from the indirect detection. So I'm not sure whether it has effect on the gravitational wave. Yeah, maybe there are some other works.
Like if like PBH in the binaries, and then you are saying possibly effects may be negligible, not so strong.
BBN? Right?
No, it's like a binary primordial black holes.
Yeah, but usually when the binary black hole, it's very close. If the dark matter is not self-interacting, then the dark matter spike is usually destructed.
Mm. Okay, then the effect will be like lower in that sense.
Yes.
Okay, thank you.
Other questions? I'll ask a question. So in the first scenario, you talked about we had scalar, vector, and gravitational wave. I guess there's no sensitivity there to pseudoscalars.
Pseudoscalar.
Right. Because
think-
the coupling is spin dependent, right? So
probably it's not. Yeah, for pseudoscalar, actually, I consider such kind of coupling.
No. I don't mean here. In the previously when we were looking at the gravitational wave interferometer sensitivity, yeah, we had these curves, for example.
You are right. Yes. So for scalar, because the coupling I consider is it can affect the mass. So for pseudoscalar, I don't think it can affect the mass, because it's CP conserving. Then probably it can couple to the spin.
Yeah, I wonder if you could just attach a magnet to either side, and then having polarized spins in the sample would give you some sensitivity.
There may be some other experiments.
Oh,
They use some laser to travel around. So there's some European.
I think there's dance, but that's slightly different, right?
I'm not sure this gravity probe B is some kind of experiment.
Well, I mean, gravity probe B is already concluded, yeah. But that was like a precession of a gyroscope.
Yes.
Yeah. I mean, in principle, it seems like it should be sensitive. Actually, I think some people had a paper about that. But anyway, okay, I understand. Thank you. Other questions? We have time.
So for the final part, you mentioned the matrix stuff in the solar system, right? My question is, for this wavy dark matter, do you use like plane wave and you add some randomly or what?
Randomly. Yes. Actually, there are two kinds of contributions. One is that you have a just monochromatic, which is picked around 2 times of the mass. So that part, if you use the plane wave, it's the same. But there is a low frequency contribution from the random part. But that part usually is in the low frequency, maybe around PTA range. So people consider about use PTA, the pulsar time array, to probe dark matter. Yeah, that.
Okay. Yeah. Thanks.
Okay.
There's another question.
Oh, there is? Where? Oh.
Oh,
please. Okay.
Actually, for QCD axion, in the loop level, you can have A square coupled to the mass of the nucleon, which I think will have similar effect as.
So that's but that's highly suppressed, right?
Not highly suppressed,
No?
depending on the mass. Actually, for the lower mass, I would suggest maybe you can also change the coupling to the axion's parameter space, FA. Because that's how atomic clock can be used to constrain QCD axion.
You mean this one? But
no, not this one.
With gluon.
With gluon, exactly. With FA, the parameter space of FA, decay constant. Because they have a lot of constraint coming from the atomic clock, which have similar principle as you.
But clock then usually is a scalar, so it can.
That's why I say the two unique. In the loop level, you will have this A square coupling. A square, I mean, then you can forget about it. Still
I see, yeah.
So maybe you can also constrain that.
Right, yeah. Thank you.
Okay, yeah, thanks. Good comment. Okay, so that's probably enough time for questions. So let's thank the speaker again. And our next speaker is, let me see, Zhang Hong from Shanghai University. So, please.
Thanks a lot for the introduction. And right, let me try this. Okay, so first I'd like to show my gratitude for Professor Sun Chen to invite me here. And I really glad that I could join this great workshop. And but unfortunately, I have classes like both yesterday and tomorrow, so I have to leave soon. And indeed, I could find someone to teach for me, but I'm afraid that the substitution will teach better for me than me. Okay, so and also like here, like how to use this, Lisa? Okay. I'm thanks this smart student called Jing Yiwu, and actually he's actually the student of Professor Tang Yong, and he graduated from Shanghai University. So I'm still like ask him to work with me, and sorry and thank you, Professor Tang. Okay, so basically it's based on some recent works this year and last year, and. But unfortunately, this actually one of this paper is still not published yet. I will give you some excuses later. Yeah. So mainly I worked on superstring theory for a long time, and but from 2018, I spent half my time on gravitational waves. Not merely for grant, but also for the indeed interesting subject, and which gave me this chance to meet you here. And actually. By doing those on both sides, gradually I found that there's some deeper links, deeper link inside, and which I could apply some dualities from superstring theory to like the black hole studies or like neutron star studies. But today's, since the topic is dark matter, I will talk about focus on this dark matter part more. And but still, I would like to mention something which might be interesting for you. That, for example, around the black hole, then some other professors already mentioned that there are like so-called ultra-large bosons existing, which could have this super-radiance around the black hole. And also like for the black hole, if you want this kind of detection during the merger, the final stage is called like the rundown period. And for that period, this black hole is governed by this quasi-normal modes. And for the society in the gravitational wave side, this is mainly done by like numerical studies. But actually, we could using some dualities from superstring theory, like we could have some Seiberg-Witten curve that using this kind of link through some equation called the Hall equation, we could find those quasi-normal modes. The frequencies could be found like analytically using this method. So that's kind of an interesting step towards this. And also like the super-radiance we mentioned before could be also done similarly using this duality. And further, there's another duality, like maybe which is more famous to those who read like science fiction. It's called the ADS CFT. It's like the duality between this gauge theory and this gravity theory. So it has one application called ADS QCD, which we could use this holographic model in the superstring theory to find some application of the neutron star equilibrium states. So that could be further applied to to compare with the observation for gravitational waves. And yeah, we did something on that. This side I will omit, but during our study for neutron stars, we found like sometimes like we want to add some other paths inside the neutron stars, which gives you the hybrid stars or mixed stars. That like we could like add, for example, we could add dark matter inside that, or like it depends on like how they are evolved. It could be found like from different layers or just mixed together. And then those could be used to like interpret these gap events for gravitational waves, and also they could serve as neutron star or black hole mimickers. And of course, like pure dark matter, pure dark star are also like was a lot of discussion. So that's mainly what we wanted to do. So let's first focus on this dark star part. Let me check the time. Okay, so. For this dark stars, like mainly like there are many equilibrium states for dark star candidates. So for example, this is one with the forming star, equilibrium states. This rho is like energy density, and this P is the pressure. And this is given by the group of Kokatas and Nielsen, like in 17. And so this is for the Munich model. And somehow we focus more on this kind of like a boson case. Boson case like it's that's mainly why that's interesting, because like this is linked to the self-interacting scalar fields, or like the simplest model for SIDM. And actually for their equilibrium states is already given for a long time ago. Like yeah, I could tell this it's like right nearly 40 years ago. So at that time, like they have derived this equilibrium state through some numerical method, like a shooting method, and then take some limit, and finally they could get this result from actually it starts from this Lagrangian. And with this is the potential, and with this U is the self-interacting part, and this is like a 5-4 model. And so they spend some method to get this seemingly like an analytical result, but during the derivation they need numerical shooting method and also limitations. But then since then there are a lot more models for dark matters, but it is always difficult to extract the equilibrium states from the known dark matter model. For example, when this 4 becomes 6 or 8 or 10, like people don't know how to extract that, mainly because the numerical difficulties. You have to use the shooting method that you have different boundary conditions on both sides. But then we found that we could actually use a method called the isotropic limit method. That means like we just need the limit they take in this method is like just taking some derivatives to have this approach 0. And you see, like although this method is called limit, but it is actually accurate. Why? Because like later when we found this mass radius relation for neutron stars and other compact stars or dark stars, like we need to solve this TOV equation. And that TOV equation already requires this isotropic limit. So we need to take the limit sooner or later. So we could take that from the beginning, and then we find a systematic way to solve this kind of Lagrangians with different potentials, that we taking this limit, then we could get this kind of equilibrium states. And this kind of equilibrium states with actually is like accurate when you apply these TOV equations. So then actually the details are written in the paper, I will skip here. So for example, there are 4 different well-known dark matter SIDM models that are called Lewis field and Cauchy-Gaussian, Sine-Gaussian, and non-topological solid stars. Like the difference is their interacting part. And using this isotropic limit method, and we could find them their like equilibrium states easily. That rho and p, the relation are given by some parameters. So yeah, using this we could draw the pictures of the equilibrium states, and of course we could find their relations or MR relation, and also MR relation, and also their tidal lambda number and mass relation like this. But now for here, you might already notice that we like make most of these masses like around the masses of neutron stars, because one of the reasons like we want to try whether those kind of dark star equilibrium states, so the dark star could mimic neutron stars. And the other reason is that actually there's like a so-called scaling symmetry existing. This scaling symmetry is very interesting, that as long as your equilibrium state could be written in this way, like they could be written as some parameter like this. Actually, most of the analytical equilibrium states could be written this way. Then when you adjust this parameter, all the pictures you draw is actually self-similar for mass radius relation. And also for the tidal lambda numbers, the similar thing exists, but only the this horizontal axis is similar, and this axis does not change. So yeah, this is like actually because we were doing string theory before, so we first check this symmetries first, and then we found this. But actually, this is actually already found like in this paper. We check when we check the references. But still, it's like already astonishing because like people are working on this equilibrium states for like decades. But this scaling symmetry was only found like this 7 years ago, and also like this for this symmetry like it was found in our paper. So then this scaling symmetry is very one of the why it is useful is that like we don't need like to draw all the different masses and the radius. For example, if we have like a mass radius like this, then we could like magnify it proportionally, that you can just adjust the parameters. And if this dark matter, dark star could have this mass and this radius, then you could find another one here and here and here, like proportionally. Just you just need to adjust the parameter. Okay, so that's like we found several equilibrium states for dark stars. And then like there's another interesting like thing called the R-Q relation for neutron stars. The R-Q relation for neutron stars, it mainly shows the relation between this moment of inertia and the tidal lava number, and also the quadratic momentum for like quadratic moment for like neutron stars. And actually it also like may work for some other for some other compact stars. The interesting thing is that like we know like if you are some expert on like the neutron stars, like there are all kinds of different equilibrium states and they vary a lot. So that gives you like different mass and radius relations and also different tidal lava numbers. But interestingly, those people found like that's why it's published in Science, that like there exists a universal relation between those parameters. So if you see the picture, like for example, this is like for the moment of inertia, and this is the tidal lava number. So those curves are like different models for like for neutron stars and dark stars using different equilibrium states. So you see those curves like they have very small deviations from each other. This is very useful discovery and also like useful in the observations, because like for now we still do not know. We haven't fixed the equilibrium states for neutron stars. But with this relation, we could like find some thing regardless of this like equilibrium states. This could check that whether the new star you found is a neutron star or not. And also it could test this kind of general relativity, like because for like modified relativity, you will have different curves here. But also it is said it is like a universal relation, which is irrelevant to this kind of equilibrium states. But there's like one thing that those equilibrium states must obey. It is very actually not so strict. It says like those equilibrium states should be realistic. But what does realistic means? It means like you should have a star which is like compatible to the normal within the range of the normal neutron stars. But actually, like for the following paper, also the same guys, like their long paper in PID, it already shows that like for example, for this kind of polytropic case, like this is like the N is here, it actually already has some big deviation from this universal relation. That is not so astonishing, because like if you draw this MR relation for this case, it's already deviate a lot from the neutron stars. But still, that means like we should not treat like every continuous equilibrium states are not the same. Actually, the paper I said that our paper is not published yet because yeah, the original ones was published in Science, and we did something for dark stars because we have a lot of dark star equation states. Then I think they are in Science, then maybe we could try PIL, and then we got rejected, of course. And then we tried, and then one of the reasons of the referee, he said that there is already, it is already shown that any smooth equation state satisfies the universal relation. But we don't get the chance to rebuttal, but actually this is not true because for example, this is a smooth equation states, but it already deviates a lot. So we still need to test whether a new equation state satisfies this or not. So actually, we did this for our models for dark matters, for dark stars, both for Munich and this kind of bosonic case. And the equation states could be a lot of varieties. And actually, this model, this line, and this line is the same model. Is the same model because, as we said, they are scaling symmetries. If we draw a curve like this, then it could have someone like this. Why we draw it like this is because this might be some candidates for neutron star-like stars, or it could be something within the range of gap events, which is between the masses of 2.6 and 5 solar masses. Then you don't know whether it is a neutron star or black hole if you do not know other information like tidal deformabilities. But a dark star could be some candidates there. It has some masses larger than neutron stars, but have it's different from black hole because it has this tidal deformability. So actually, we found that, and before that, there's another thing. Again, that's a Cockta's paper. They have this formula star models we mentioned before, and in that paper, they found that there's obvious deviation when for formula stars when this lambda is big enough, and they wrote some explanation for that. But actually, after checking, it turns out that in their paper, this curve, they're using this numerical fit in the science paper, and but actually this numerical fit was fitted until lambda is 10 to the 5. So this fitting is correct only until this range. So they use this fitting analytically extended to this one, and then got this deviation. And so actually after our checking, it's actually the formula stars and this dark stars all satisfy the same curve for the same curve for the neutron stars. So this universal illusion exists still for dark stars. And the other reason for another PIL reference, they said we cited this paper, but why we did not comment about this? That's mainly because in the new version we have comment about that, but in the original version that's up to the traditional votive Chinese, we did not point out that that paper have some mistakes. We just said we have this result and cited that paper. But then I realized that I should point that out in this new version. And then later there are some mixed stars, you have different models. If we add new dark matters inside, there could be two different scenarios. One is if the interaction is strong, then you could end up with different layers. But maybe more realistically, the dark matter will only interact with normal matter like neutrons by gravitations, by gravitational force. Then in that case, they will be mixed together in the middle, and then in the outer layer, what is the other part will be left. Okay, so that's basically two different scenarios, or you could see three. It depends on which is inside. Okay, so in that case, we consider this kind of three models, and also for the first time we derived that this tidal deformability for this case. For this case, it's already known, but that's in Latin paper. For the first case, the tidal deformability calculation is already known. but also there are some mistake in the original paper. In the paper, they don't have this P, and also there's a minus there. So actually we fixed that. And again, we did not really say like they are wrong. And so in the later version, we just say that typos here. And then after our paper, we found that there's another paper like, our paper there's only 21 citations, but there's another paper, only 3 pages. Like they discovered that mistakes later and published in PRD and found 30 citations. Anyway, so I'm just saying that we are actually doing something useful, and we could find some corrections for like for those like right. That paper is by Latima. Yeah, I think he's quite expert in this area, but still like there might be some mistakes, and I'm looking forward like to the further studies. And yeah, so thank you much. Yeah.
Okay, thank you for this nice talk. Questions? I saw Tianjun first. So.
Okay, thanks. So for that dark I love Q, you have this equation. So how can I understand it like from physical intuition? Because maybe just some physical intuition, we can have some result like that. So what's the physical intuition to understand it?
You mean for the different kinds of equations?
No, you have this equation. There are states. So you go back.
Yeah.
Back.
Sorry. Yeah, it's here, I think, right.
No.
The I love Q really.
I love Q. That's I mean, various parameters satisfy one equation. But how can I understand this from my physical intuition?
Which parameter?
Keep going. No, keep going. I know. Okay. Keep going. Yeah.
Yes, this equation. Because,
right.
Because it's simple. I mean.
Yeah, those parameters. It's like if you want to some physical interpretation. It's like first, this expansion is like something like Taylor expansion, right? So it's like the relation between like y and x. And for the pure value for the why we have this universal relation, for the original paper, like in the long paper, they have some derivation for not for non-realistic case. For the Newtonian limit, they have discussed that like this I and lambda, they are related to the compactness, and also like they are related to this kind of single polytropic case with n is 0 and 1. And for that case, like they found like they have some either n is 0 and 1, they satisfy the same relation. And for our interpretation, yeah, I did not mention in our talk, but in the paper, like why we have this universal relations, because like for here, like for all those like equation states we use, when we take the limit, when p is small, they reduce to some single polytropic case when this n is like 1. This n is like here, given here. I don't know whether you could see it or not.
I can see it.
Yeah. Or like this gamma is like from 0 to 0.0. Then, so when all those equation states, when we take this limit, they end up with this for the outer layer. And I think it is that outer layer with the stars, they matters a lot for this deformations of this tidal deformations or like this quadrupole moment stuff.
Okay, another question is because like for me, you come back to that equation. Come back to that equation.
Yeah.
And another question is log xi is a small number or not? Because for me, this is like expansion. Let's say log xi is epsilon. Then I do some expansion like for x and ai. AI to epsilon nth power. So if we think this is correct, they have more terms maybe beyond this like fourth power.
Right. It's this is actually something really like a Taylor expansion. It's a relation between this log y and this log x. It's like Taylor expansion. So it just means like they are like this yi and xi, they are stand for this I and lambda, but the different values they come. This fit comes like what different kind of EOS you use, these AIs, BI, they still have similar values. Of course, if you expand to higher levels, it may have some deviations.
Yes, that's what I think. You have you saw some deviation, maybe from some like high power.
Right. You could also see from this Z-slim arrow. The arrows are listed here, so you could see the relative arrows like is something about 1% for the curves, like a deviation from the curves.
Okay, excellent talk.
Thank you.
Okay, thanks. Questions? We have time for one quick question.
My question is that you told that dark star can be mimic to neutron star.
Astropic limit. Sorry.
They mimic neutron star.
Mimic a neutron star. Yeah.
Yeah. So my question is, when black hole and neutron star merger takes place, or whenever the neutron star is a part of binary merger, there is a electromagnetic spectrum on top of the GW spectrum. But here, dark star, there is no like electromagnetic spectrum unless it interacts with the standard model particles.
Sure. Like it depends on like your if you have like now we have this multi-messenger discovery abilities. So of course both the waveform and the electro waveforms like will be different. But sometimes like you don't know whether you could have this because usually the electromagnetic discovery is weak usually. But sometimes we only have this gravitational wave method. And but you could, for example, sometimes if you have a big black hole and a small neutron star, you cannot detect this tidal differentiability. But if you are it's like a neutron star and a dark star, you could have this tidal differentiability.
Okay, maybe I will discuss them. Thank you. Yeah.
Okay, thank you.
Okay, great. So let's thank Zhang Hong again. And let's move to the next talk, which is Chen Qing, who is going to be telling us about general WIMP direct detections.
Good afternoon, everyone. So first, thanks to the organizers for giving me this opportunity to present our works. I'm Qing Chen from Anhui University of Science and Technology. So today I'm gonna talk about direct detections of general heavy WIMP dark matter. So this talk is based on the works with my PhD advisor, Richard Hill, and as well as Guijun Ding from University of Science and Technology of China. So first, I assume the participants here, if not familiar with WIMPs, are at least aware of WIMPs, weakly interacting massive particles, and direct detection experiments for these WIMPs. So these experiments, they have achieved very unprecedented sensitivity limits. As you can see, all the region above these colorful curves have been excluded, and they are really approaching to this background, which we call neutrino floor, this light blue region here. So I feel like currently there's some kind of anxiety atmosphere among theorists that but I want to say that we should not worry. There's a reason that we don't see them in these experiments, because actually, as I will tell in this talk, the cross section is really very small. That's why we haven't reached that sensitivity to see them. And also, I don't want the experimentalists are discouraged by this kind of atmosphere. I just want to cheer up the experimentalists. And you are doing a great job, and I think you should keep going. Okay, so today I'm considering heavy WIMPs by heavy, I mean they're heavier than electroweak scale. Why do I consider they are heavy? First, if we look at collider searches for neutralinos, which are neutral supersymmetric particles at colliders up to a few hundred GeV, we haven't found them. So that's first. And second, if we assume these WIMPs were in thermal equilibrium with other standard model particles in the very early universe, and we compute that annihilation cross-section and compare with astronomical data, we find for a Higgsino-like particle, the mass is about 1 TeV, and for a Wino-like particle, it's about 3 TeV. So these suggest these WIMPs are much heavier than electroweak scale and probably are at TeV scale. So today I'm talking about to construct an effective field theory for these heavy WIMPs. So the idea is very simple because weakly interacting massive particle by definition is some representation of SU2 cross U1. So you assign some isospin J to this SU2 and hypercharge Y to this U1. And also, it could be any representation of this space-time symmetry. It could be a Lorentz scalar, fermion, vector, or even a spin 3/2 particles, all these Noor spin particles we are considering. And then you can write down an effective Lagrangian for a self-conjugate heavy particle using the heavy particle effective theory, which is a very mature effective field theory in heavy quark effective theory. But we are really replacing that quark with our WIMP heavy particle here. So the V is the velocity of this heavy particle. And for WIMP, this V is about 200 kilometers per second from astronomy data. That's like 10 to the -3 compared to speed of light. So it's very cold, non-relativistic. And capital D represents the general covariant derivatives. Of course, the SU2 cross U1 gauge are inside. And through this 1/m power corrections, you could also have interactions with Higgs, W from SU2, B from U1, because they are all participating in this weak interaction. And these kinetic terms are universal, and these interaction terms are UV and representation dependent. But we could, as I have said in the last slide, we could consider all general representations. Okay, so this effective Lagrangian is written at the weak scale. As I have said, I'm going to compute the cross-section for dark matter direct detection experiments. These experiments are very low energy experiments, so it's very impractical to directly apply this Lagrangian to compute the cross-section in that experiments. So first, we need to match this weak scale effective theory to some lower energy effective theory, which is about the scale of direct detection experiments, the nuclear energy level effective theory. So what we do is we need to integrate out the weak scale physics. And obtain an effective theory consisting of our heavy WIMP, the quarks and the gluon operators. And in this table are the QCD quark and the gluon bilinear operators. They are building blocks for this quark and gluon sector, the low energy QCD sector. And for the heavy particle, heavy WIMP, this sector, you could build them with the heavy particle effective theory structure operators. These are pretty standard. And then you have these operators. Now you need to do the matching to obtain the coefficients of these operators, which we call Wilson coefficients. Here, the CQ for quarks, CG for gluons. And then when you match that weak scale Lagrangian to the low energy QCD operators, you will obtain these Wilson coefficients. Finally, we integrate out WZ, Higgs boson, non-Goldstone bosons, and top quark, which is about 80 GeV as well, to obtain a 5-flavor QCD effective theory. And then this Lagrangian is for spin-independent process, which is the main process in dark matter direct detection experiments. And the operators relevant here are just these 4 types: quark spin 0, gluon spin 0, quark spin 2, and gluon spin 2. And the matching are performed just by computing these diagrams directly. These heavy lines, they represent the heavy WIMP, and the solid line is a quark, and the curly lines here are gluons. So all the weak scale particles we need to integrate out. They are just in the loops, like the zigzag or WZs. The dashed lines are Higgs. And you could also have, say, top quark here in the solid line here. Inside the loops, you integrate them out. And then for quarks, these diagrams are 1 loop. And for gluons, they lead a quark loop to talk to the electroweak sector. So you have 2 loop diagrams. And the crossed circle here represents an effective vertex between Higgs and WIMPs, as we mentioned in the beginning in the 1/m interaction term. Okay. And then when you are done with these Feynman diagrams, you obtain those coefficients, those Wilson coefficients. But note that we are still at this weak scale. So we need to run those coefficients by solving these renormalization group evolution differential equations to obtain the coefficients at some lower energy. So these gammas are the anomalous dimensions, which I list them in this table. And then by solving these equations, you get a solution of a set of Wilson coefficients, and these operators, they will mix. And so you have some results in this matrix form. So you have the final no energy mu sub L scale Wilson coefficients expressed in terms of the high energy scale Wilson coefficient C sub J with this capital R matrix. Okay, now we have this Wilson coefficients at no energy scale. So we have basically from electroweak about 100 GeV scale and integrate out this electroweak physics and run it down all the way to a 5-flavor QCD scale, about 5 GeV, the bottom quark mass scale. And now we have the Wilson coefficients, and the other thing we need is the operator. We need to insert them into the nucleon states, like the protons, neutrons, which are the targets in our dark matter direct detection target. But in this scale, the QCD is non-perturbative. We don't know what they are yet. And so we will resort to lattice QCD. And lattice QCD currently, they only work well to up to 3 flavor, the light flavors UDS QCD. So further, we need to integrate out these heavy quarks, the charm quark and bottom quark, and evolve this theory to some about 1 GeV 3 flavor QCD. So what we do here is we do a heavy quark threshold matching. So we relate the N sub F plus 1 flavor QCD with an N sub F flavor by matching them. The amplitude should be equal, but with prime is the NF plus 1 and unprime is NF. So we have this C prime. We need to solve this C. How to solve this is we apply QCD sum rule, which is basically you have QCD energy momentum tensor T mu nu. You decompose it into the trace part. It constrains the quark spin 0 and gluon spin 0 operators, and as well as traceless spin 2 part, T mu nu. It constrains the quark spin 2 and gluon spin 2 operators. And you apply these equations to solve this. And finally, you could obtain the light flavor, the N sub F flavor coefficients C sub I in terms of C sub J prime. They are also linked by a matrix, which we call capital M. So finally, after we do all these effective theory matching and running, we can get our result. Let's remind ourselves. We start from the electroweak Lagrangian. We integrate out weak scale physics. We obtain C sub I at about top quark scale. And then we do the RG running from top quark scale to bottom quark scale with this R matrix. And then we use M matrix to integrate out bottom quark. And then we use R matrix again to evolve from bottom quark scale to charm quark scale. And then we use this M matrix again to integrate out the charm quark. And then we again evolve by this R matrix from charm quark scale to some mu naught, which is the lattice QCD working scale, about 2 GeV or 1 GeV. Then we obtain this Cj of mu naught, our desired Wilson coefficients. And then we insert those operators, the quark and the gluon operators, if you remember, to nucleon states. And these matrix elements, they are computed by lattice QCD. And we just have those numbers you plug in with the coefficients we have computed. Altogether, we obtain our amplitude. And numerically, you would find there's a major accidental cancellation between these two types of operators, two types of amplitudes, the spin 0 and spin 2. Here, I normalize the amplitude by making the spin 2 amplitude as 1, as like there's an overall constant I'm dropping here. And then you see if spin 0 is also of order 1, then you get something like order 1. But spin 0, it has a different sign from spin 2, and they cancel. So you have this 0.1. You have an order of magnitude separation. And even worse, you have a minus sign here, that you have a you have a cancellation between this J isospin and this Y hypercharge, because they are also of order 1 numbers. Finally, you could get something like 0.01, like 2 orders of magnitude separation, and the whole cross section could get 4 orders of magnitude separation. And this is just leading order, is model independent, like I said at the beginning. And the 1/m correction, you have some UV parameters, and like you have some model dependent here, which is represented by this coupling, the WIMP coupling with the Higgs, this C sub H. And then if you use this result, this pretty general WIMP nucleon scattering amplitude or cross-section result,
Okay, yeah.
You got it.
Sorry, yeah. First, I would like to thank the organizer for giving me this opportunity to present my work here. So, so today I'm going to talk about topic on dark matter properties from survival of neutron star. So this I have done recently with Professor Wu Lei and Cheting Lu and Professor Ning Liu. So, okay. Okay, so I think we have already discussed this thing that dark matter exists and from different observation. So I'm not going to, okay. So we know that dark matter exists, but we don't know its microphysics. So for example, we don't know what is a dark matter, what kind of particle it is, what kind of like cross section with the standard model particles, or like what kind of coupling and all those things. So we don't know any microphysics of the dark matter. So, but we know that when we do the dark matter detection experiment, then typically we assume some form of dark matter interaction with the baryon by assuming that if dark matter interacts with the nucleon or any like standard model particles, then it can lead to some signal. And so there are different kind of experiment. So, but like we have not detected any dark matter. So, but we have different experiment. So in like collider, like not like direct detection kind of experiment, they are sensitive to like only GV up to some GV, if you like 100 GV or let's say 10, like TV scale dark matter, but they are not very sensitive to massive dark matter case. The reason is that when dark matter interact with the nuclei, it doesn't transfer much energy so that you don't get signal in the direct detection experiment. And on the other hand, if dark matter is very, very light, let's say less than sub GV of that range, then again, you don't get any signal in detection experiment. So in that way, we cannot probe these two extreme dark matter masses. And on the top of that, if we have some like velocity or momentum dependent interactions with the baryons, we don't have any method with the like direct detection to probe that thing because they are very suppressed because relative velocity is very, very small. So this, so in case if dark matter is very massive or very light, so these experiment cannot probe them. So what we have to do that, then we need to look for some other region of the universe where dark matter properties is very sensitive to the baryonic interaction. It's like where dark matter density is high. So, okay, in this way, neutron, so all the compact objects which are the end product of the stellar evolution, like neutron star, white dwarf, and black hole, they can act as a dark matter laboratory. The reason is because they have very strong gravity. Sorry. They have very strong gravity, and also they have very high density. For example, neutron star density is very, very high. It's order of like nuclear density. And also its gravity is very strong, very compact object. So what happens that whenever, if the dark matter is in surrounding of the neutron star, so because of this extreme gravity, they can accrete the dark matter particles surrounding it and increase the number inside the neutron star. And therefore, with this process, they can unstabilize the properties or like mass radius relation and other properties of neutron star. And therefore, in this way, one can probe the dark matter baryon interaction. Okay. So the one thing what's very important that when dark matter can accrete in the neutron star, so these captured dark matter can heat the neutron star material. So this can be done by two different ways. So first way is like dark matter directly interact with the neutrons and then transfer its energy. So it's direct heating. Here you see that dark matter can directly just interact with the nucleon and give some part of its energy and get bound in it. So this increase the temperature of neutrons. And on other hand, if dark matter is like a annihilating, dark matter particles are annihilating in the nature, so once they get at, they are inside the neutron star, that they can annihilate and produce the photon or neutrinos. So it's like they can increase the temperature of neutron star. And with this and with these, if they increase like a temperature up to this, like 1750 Kelvin, or roughly order of that, and if the neutron star are quite near to, it's like 10⁻²2 parsec near to us, so the JWST and other observation can detect this these photons. Okay, so these what I told you, that when dark matter what accreted inside neutron star, the fraction is very, very less. But what happens that if there are accretion is quite high, then dark matter can form a black hole and destroy the neutron star. So what happens that, so this is the way how, sorry, okay. So what happens that when dark matter can get captured inside the neutron star, then it start interacting with the neutron star material, and after some time it can get thermalized with the neutron star and lives in like in the typical thermal radius. And if the number of the particles inside the thermal radius is quite high, it's like higher than the Chandrasekhar limit, then they can make a mini black hole, just the center region of the neutron star. And so what happens once there is a black hole formation takes place, then it start accreting the nearby material and start growing with that. And after some time, it can accrete all the material and then form a big black hole. So you will not observe black hole after some time. And this will happen only when the dark matter density is quite high around the neutron star. Okay. So let's discuss more about it. So for capturing, so it is needed that dark matter should give a lot of energy to the neutron star material, so that the velocity of dark matter should be less than the typical escape velocity of the neutron star, so that they get stuck inside the neutron star. And also, it's not like all the dark matter particle will accrete. So there is a typical limit on cross section, above which it's called geometrical cross section. This is the maximum cross section that is allowed with the dark matter accretion on neutron star. If sigma is like cross section is higher than this cross section, the probability of capturing will be very, very small. So this is a limit where total dark matter can be accreted. Okay. Something is not working, I think. Oh, okay, yes. Okay. Okay. So what happens that, so how this dark matter is captured? So the capturing can be happen in different ways depending on dark matter mass. So first we will discuss about single scatter capture. So in this capturing, so what happened, dark matter just collide with the neutron and then give its energy to, most of its energy to neutron and capture in the single scattering. So, and for that, the dark matter mass should be quite small. It's like small, it's like 10⁶ GeV, and it can be up to like lower than that. So in that case, you can calculate what is the capture rate, and it's basically depends on various factors. So for first factor is called degeneracy effect, because we know that neutrons are like degenerate objects in like particles inside the neutron star. So to excite neutron, you need to provide energy high or momentum higher than the Fermi momentum. So once the transfer momentum is quite high than the Fermi momentum, then only the energy can be exchanged between dark matter and baryonic particles. So this is one thing. Second thing is like omega W is proportional to called collision probability. So how this dark is, all the dark matter microphysics goes in this particular term. So, okay. Okay, so we assume that dark matter interact with the nucleon, and we don't assume any kind of self-interaction. Then we focus on asymmetric dark matter because we want more and more dark matter should be collected on the neutron star. And we also neglect the evaporation effect. So evaporation effect happens for the light dark matter case. What happens that when light dark matter are inside the neutron star, so they, after some time, after thermalization, they get enough energy inside neutron star itself so that they can come out from the neutron star. So we neglect this evaporation effect, which means that we are not going for a small mass range, evaporation mass. Okay, then with this simple assumption, you calculate the capture rate and then you and multiply with the age of universe, age of the neutron star. Okay, so what here then, as I told you that for most like direct detection searches, you cannot explore the velocity dependent cases or momentum dependent case. So here, but you can, because here the relative velocity between dark matter and neutrons is quite high. It's order of like 0.5 C or something. And therefore this sigma can be enhanced. So it means that cross section is higher, then number of accreted dark matter can be high. And in the same way, we parameterize the momentum dependent case and with this particular form. And we assume dipole form factor because people have not previously not assumed that they just consider very low momentum or velocity transfer case. So therefore, they neglected this kind of factor. Okay. So once the dark matter is inside the neutron star, so this dark matter particles start interacting with the thermal medium of neutron star, and therefore they got thermalized when the thermalization time scale is less than the typical age of the neutron star. And once they got thermalized, then they drift towards the center of neutron star, and they form a isothermal distribution, and they are just inside a thermal radius. And you see that if you consider like a 100 GeV dark matter mass with a like 10⁵ Kelvin temperature, then this thermal radius is very, very small. It means that dark matter particles lives very tiny space inside the neutron star, the center. Okay, so once what happens that because dark matter is accreting on the neutron star on top of that, so it happens that when the density of dark matter becomes higher than the baryonic density, then they start self-gravitating. And self-gravitation is very important condition because once then number becomes, so what happens that if the number of accreted dark matter is higher than the Chandrasekhar limit, then they can form a black hole. So this is one like this is without BC. So there is another possibility if dark matter is like a bosonic dark matter, then there is a possibility of Bose-Einstein condensation. So this happens when the temperature drop down like a typical critical temperature of the, it depends on the number density of particle. So in that case, if the dark matter satisfy all the BC criteria, then it forms the BC condensate state, and the number of particles is increasing because dark matter is accreting in the neutron star. And whenever this number becomes higher than boson, like Chandrasekhar limit of bosonic particle, then they can automatically form a black hole. So here you see that as we know that's like because of fermionic pressure, the Chandrasekhar limit for this number is quite high because of fermionic degeneracy pressure. But for bosons, like Chandrasekhar limit is slightly smaller because there is no degeneracy pressure here. Okay. So what happens when the black hole formation takes place? Then black hole start evolution of black hole can be governed through this equation. So here you see that the first equation is just accretion of the black hole, and the second is because dark matter is also there, so black hole also will accrete the dark matter. And second is like Hawking evaporation, because here the black hole mass is quite low, so it is possible to evaporate via Hawking radiation. So there is so the sign of this thing, we know that Hawking evaporation, because of that the mass of black hole decreases. In that case, so there is a competition between these two terms. So if we assume that dark matter accretion is very small, this term, then so if they are small, then if we assume and we put the value, if assume that they are non-relativistic, Newtons are non-relativistic, then we can calculate what is a critical number. And if with this critical number, so if black hole formed, it's like initial formed black hole mass is higher than that, then black hole will grow due to accretion, and after some time it can destroy the host neutron star and they form a big black hole. But in other case, in opposite case, if the if the Bondi oil accretion is smaller than the Hawking radius, like Hawking evaporation rate, then the mass will decrease, and after some time, black hole will evaporate. Okay, so with this, we can constrain what is the upper limit on dark matter mass is typically 10 power 8 GeV, and for bosonic case and for fermionic case, it's like 10 power 10 GeV. Okay, so let's just, this is just a number of accreted dark matter particles as a function of mass in the single scattering capture case. So here you see that we have put, we have calculated for all the cases for like alpha is equal to 0, alpha is equal to 1. This is velocity dependent case, and this is for momentum dependent case. Here you see that dark matter number of accreted dark matter particle increases for low mass. It's like roughly constant and then start decreasing. And this is saturation limit. As I told you that after, like, this is a maximum number of particles that can be accreted, because you cannot cross sigma saturation. And this is for momentum dependent case also. And here you see that the number are quite high. It's like 10 power 45 to 10 power 55. It's like 10 power 45. So depending on dark matter mass, it can be, so you can form black hole up to 10 power minus 10 solar mass or something. Okay, thank you. So, and we have used this pulsar data to constrain the dark matter, this property. So here we consider, so because to consider the black hole formation, we need to take the central temperature of neutron star and also the age of neutron star. These two terms are important, and we don't have much data, but only two data are available. There are one more, it's like pulsar. They are near to galaxy center, but we don't know what is the central temperature. If we get any pulsar near to galaxy center with this center temperature and age, then this will put a strong constraint on the dark matter. And but we don't get, it's quite near to the Earth, so the constraints are not too strong. So here we have plotted for constant cross section case. Here you see that for BC, so what happens that this is the cross section that is excluded with a BC condensation, and this is and with different, of course, pulsar. This is one pulsar, this is second pulsar. And here you see that like cross section is order of 10 power minus 47 centimeters square for like 10 power minus 1 like GeV. So these parts are excluded with the black hole formation. And this is for velocity dependent case. Here you see that it strongly constrains the like velocity dependent case. It's like 10 power minus 54 centimeters square for 10 power minus 1 gram. scattering. It's like, so this is for constant, okay, so this is for constant cross section with the single scattering. But here you see that if for the positive power of momentum dependence, the number start increasing, and this is for like for n is equal to 1 case, and this is you see that for n is equal to let's 100 and like beta is equal to 2 case. So the number of accreted dark matter start increasing, and say this is also valid with the velocity dependent case. So in that case, this multi-scattered captures is important for the massive case, and then and this increases, the number increases with the number of accretion as well as depending on the power of sigma. Okay, so this is a typical thermalization temperature, and here you see that for like positive q power 4 dependent sigma, this is a thermalization time scale is like 10 power 10 years, but most this for q power 4 case, it's like above 10 power 10 year. So this kind of dark matter cannot be, they cannot be thermalized inside the neutron star. But for other cases, they can be thermalized because the time scale of their thermalization is smaller than their typical age of neutron star. And this is typical constraint. Here for massive case, here for constant case, the parameter space are not very strong. It's very limited parameter space. But if you go for, momentum like dependent case, so here you see that's like a cross section is constrained up to 10 power 47 centimeters square for 10 power 6 to 10 power 8 GeV mass range. Of course, there is a limitation. Otherwise, after the one thing which I showed you, that number of accreted dark matter is inversely proportional to the mass. So if mass increases, number decreases. After some mass, they cannot form a black hole, or they form the black hole, then that black hole mass is very, very small. So therefore, there can be evaporation. So these are, in this region, in black hole evaporation region, the constraints are not very, they are not like tight constraint, because we know that they cannot be. And this is for baryon, like bosonic case, and this is for like fermionic case, dark matter case. It's red one for that. Okay. Okay, this is, we have again plotted for the positive v power 2 dependent case, and you see that this constraint is quite stronger in the positive velocity dependent case, v power 2 case, but for v power 4 case, most of the parameter space are relaxed because of the non-thermalization of the dark matter. So in this way, you can probe like 10 power 8 to 10 power 9 roughly up to GeV. You can put the constant. Okay, this is summary. So we found that dark matter particle capture is enhanced because of dark matter baryon interactions, and this could lead to black hole formation, and black hole formation suggests that either you can constrain the dark matter properties, or you can look for like solve another problem called missing pulsar problem. And then we use existing neutron star data. Of course, data is not, as you see, that's very like 2 only data sets, so it's not too strong constraint. But we found that the single scattering limit up to 10 power 2 GeV mass dark matter, but for multi-scatter capture limits like 10 power 10 GeV. It's depend on the bosonic or fermionic dark matter case. But in future, the observation of old neutron star will put tight constraint on the dark matter microphysics. Yeah, thank you.
Okay, thank you to Arvind for this interesting talk. I think we have time for one question. Okay.
So I have a very naive question. So do you have any uncertainty from the equation state of the neutron stars?
Yeah, that's a nice question. Actually, it depends, of course. Here we have considered a very simplified equation of state.
Yeah.
But if you consider like more general, if you are like use correct equation of state, then it will change the constraint a little bit.
But the effect is a bit. Okay.
Yeah.
Okay.
But I'm not sure like how much, but like rough estimation tells you it's not too high. Okay. So, yeah.
Okay, great. So I don't see any other questions. So let's thank Arvind again. So our next talk, which is the final talk of the session, is Chen Xian, who's going to be talking about Moon as a gravitational wave detector.
Okay, good evening. My name is Chen Xian. I'm from Peking University. First of all, thanks the organizers for inviting me and giving me this opportunity to present my work about Moon as a gravitational wave detector and its applications to dark matter search. Right now, we have direct observational evidence of gravitational wave in two bands, actually, at about hundreds of hertz band. We have LIGO, Virgo, Kagra, trying to detect gravitational wave, we think, from merging compact objects. Most of the sources are 10 solar mass black holes. We think they are formed due to stellar evolution, or probably from primordial black holes. At lower frequency, nanohertz, we have a pulsar timing array detecting a background. People are still debating the nature of this background. Astronomers think they are merging supermassive black holes. They have to be supermassive because there's an equation here. Actually, the frequency is inversely proportional to the mass of the black hole because black holes have finite size. You cannot put black holes closer than their structural radius. That's limit the maximum frequency you can get out of a gravitational wave. Theoretical physicists think that this background might come from the early universe due to, for example, phase transition, which also produces dark matter. In between, there's a band in about millihertz. We think there are also all kinds of sources here, including mergers of a relatively massive black holes, say 10 to the 6, 10 to the 5, 10 to the 4 solar masses. The standard way to detect a gravitational wave in this band, it's interesting to the standard because 20 years ago when I was a student, it was considered to be an unconventional way, but now it's kind of standard to detect gravitational wave in this band with a space interferometry, such as a Taiji, Tianqing, as well as a LISA. I think you have heard a lot of it during today's talk. This middle band, let's call it, for a while people think it's a good band for dark matter search. For example, we have heard several talks about dark matter forming a mini-cusp around a supermassive black hole. There are two ways to form this mini-cusp. One is due to so-called adiabatic contraction when the supermassive black hole grows. There's also a concentration of dark matter around it and forms a mini-cusp. Or if the dark matter is self-interacting, many speakers before me talked about it, it will also form a mini-cusp. At the same time, you can have a small compact object like the stellar mass black hole circling around a supermassive black hole, and they form a gravitational wave source. But this small body will inevitably feel the interaction with the background dark matter cusp. So this will modify your gravitational wave signal. You can try to model this. This idea actually has been there for a while, and try to look for signatures of the existence of mini-cusps in these gravitational wave sources. I want to highlight two works here. One is from my collaborator, Yue Xiaojun and Han Wenbiao. Back in 2018, they studied the interaction between this small body and the background dark matter cusp. They considered several processes. The gravity of this dark matter cusp will cause an additional precession of the orbit, for example, and the friction against the background will also cause the orbit to decay. And this small body might also accrete dark matter, which effectively changes momentum with the background, and this will also alter the orbit. All these effects, if you put them together, you can see that then in gravitational wave, because you detect phase, you can see the phase is different from a standard vacuum kind of a source, and they call it phase shift. The phase shift is frequency dependent. If you detect its signature, you can claim that you have detected dark matter mini halos. A year later, we followed up this idea and studied the chance that such kind of things are actually happening, the event rate. The solid line here is the event rate without dark matter mini-cusp. This is a function of the mass of the central massive black hole. Okay, but after we put in the dark matter mini-cusp, you see a huge enhancement of the event rate at small mass scales, 10 to the 3, 10 to the 4 solar masses, a range which we call these black holes intermi-mass black holes. Remember, I just pointed to you the frequency of gravitational wave is inversely scaling with the mass. So small black hole mass meaning higher frequency. So we need a little bit higher frequency, maybe towards 0.1 hertz, to try to catch intermi-mass black hole as well as a dark matter mini-cusps around them. Another way of detecting a gravitational wave through gravitational lensing, we have heard lensing of light, right? A foreground galaxy or cluster will gravitationally lens a background galaxy and form these beautiful images. This intervening galaxy can also lens a background gravitational wave source. Same thing, will form different images of gravitational wave sources. And you can try to measure the time delay of these gravitational wave images and use it. You can constrain a range of things related to dark matter, including the mass density of dark matter or the density profile of the dark matter halo of your lens, as well as substructures, because if there's substructure in the lens, it will induce some time delay anomaly, which I can also tell you the size of the substructure. I also want to point to you that if you are considering the millihertz gravitational wave and look at the wavelengths, it's already hundreds of millions of kilometers. And this wavelengths start to be comparable to the gravitational radius of some small structures, say 10 to the 8 solar masses. So this is actually a very, very different character of gravitational wave because of its long wavelengths. And this mass scale here, 10 to the 8, is also interesting because if you remember earlier Li Ran's talk, it's actually a characteristic boundary between warm dark matter and cold dark matter. So this relationship tells you that you can try to look for wave optics effect induced by structures smaller than this one. Okay, if you find one, you can claim that you detected very, very small structure, and that might be a signature of, say, cold dark matter. But a couple of years back, we also wanted to study this signal. So this is just a simulated signal. Different lines are for different black hole mergers. The solid line is unlensed signal, and the dot dash line is a lensed signal. And you see this dependence of the magnification as a function of frequency. And this is a character of wave optics effects. Also, what's interesting is that we find that we don't need the lens and the background source to be perfectly aligned. Even if the impact parameter is, say, 50, you can still see a clear signature because our detector, say the space gravitational wave interferometry, is very, very sensitive. However, we also found that the biggest effect happens here for the smallest black hole, actually, 10 to the 4 solar masses, and appears at about 0.1 hertz. This region is a little bit below the space detector, like LISA. So again, we find that we will need sensitivity toward 0.1 hertz. Are there detectors very sensitive at 0.1 hertz? There are a lot of them, actually, conceptually. But here I want to point out a possibility, that is to use a moon as a gravitational detector. The idea was actually quite old. The pioneer of gravitational wave detection, Joseph Weber, in the 1960s, 70s, when he was building these aluminum bars in his lab, he already conceived the idea that he can replace his bars with the moon and use a vibration of the moon to detect passing gravitational waves. In the 70s, when Apollo missions, all kinds of Apollo missions were trying to explore the moon, Weber even took the chance and PI'd a device like this. It's actually a seismometer, and asked Apollo 17 to take it to the moon. Okay, and this is a device actually on the moon. Unfortunately, the device malfunctioned, so there were not much data sending back. But today it is understood that even if the device perfectly worked, it would not have the sensitivity to detect gravitational waves. Then almost a half a century has passed. There was no more seismometer until last year, actually. India's Chandrayaan-3 landed close to the south pole of the moon and deployed a seismometer, which sent back a brief signal. But also the seismometer was not designed to detect a gravitational wave, so it didn't detect any gravitational wave signal, let's say. But the future is bright, or people would say more louder in this community, because both US, Europe, and Japan have plans to send seismometers to the moon in the next 10 years until maybe 2030s, okay. China also has a plan, Chang'e 7, which is expected to launch in about 2 years, will also carry a payload which is called a lunar seismograph. This is a seismometer which has a sensitivity close to the seismometer on the Mars. For example, the InSight also carries a seismometer which is now on Mars, and this is a sensitivity curve. Given all these projects, it's actually very urgent to study the response of the moon to gravitational waves. So what's the theory? The theory actually is also an old one. It's basically you want to describe how an elastic body is oscillating under the force of a gravitational wave stress. How can you write down the gravitational wave force? There are conventionally two views. One view is that use a so-called TT coordinate. So the idea is that the coordinate doesn't change, so there's no acceleration, even if you see a distant change. The apparent distant change is caused by the change of the metric. Okay, this is one view. Another view is that the distance is your coordinate. So the particles are indeed accelerating when gravitational wave passes by. So whatever view you take, you choose a coordinate system so you can write down the force. But if you look at the form of these forces, they're a little bit different. Anyway, you plug these forces into this equation and try to solve the response, the surface response of the moon, and you get basically how the moon oscillates under the force of a gravitational wave. This part is actually decompose gravitational wave into spherical harmonics. And relating these two parts is a so-called transfer function, which depend a lot on the structure of the moon. And that's where the calculation is the most difficult. People have been trying to calculate these transfer functions, and this is a result done by this European collaboration, Lunar Gravitational Wave Antenna. They are trying to put 1, 2, 3, 4, actually 4 seismometers in the permanently shaded region close to the south pole of the moon, basically in a crater, to have a stable temperature environment. And you have to power these seismometers with laser. Anyway, they calculated this just to guide your eye. This is actually the size of your moon, but it also characterizes the amplitude of a gravitational wave if a gravitational wave passes by. And at low frequencies, you see these very high spikes. Okay, the response of the moon in these frequencies actually is much higher than the amplitude of the gravitational wave. This is due to resonance. Okay, this is good for your gravitational wave detection because the moon kind of amplifies your gravitational wave. But at higher frequency, where we are interested in, 0.1 hertz, you see huge discrepancy between A and B coordinates, right? So why is that? Given that the final sensitivity to gravitational wave is inversely proportional to the transfer function, we think it's a serious problem here, which needs to be resolved. So we started looking into this. Now we try to understand the meaning of the so-called B coordinate. What is it? So you see in this coordinate, the particles kind of oscillates relative to the center that you define, okay? But don't forget, these are free-floating particles. They're free-falling. In general relativity, free-falling particles don't feel acceleration. If you try to attach lunar seismometers to these particles, there's no readout. So you will notice that the B coordinate is problematic. Actually, it's the A coordinate, which you use TT gauge, that is telling you directly what is measurable by the lunar seismometers. And this is ideas for, say, you just take away the moon and look at the free-floating particle, but if you put the moon back, it's the same thing, and we can prove it. Actually, this is done in our work. We find this very simple relationship between the results from the two coordinates. This is the coordinate of the so-called local inertia frame. It is the acceleration relative to the local inertia frame that can give you a real signal that is detectable by the lunar seismometer. And in the past, people have been using this wrong coordinate to calculate a transfer function. So it's very flat over a large range of frequencies. But now with our correction, we find that the transfer function decreases with frequency. No matter what coordinate you use, you do the correct, let's say, the correct way of understanding it, you will see that both results will agree very well in almost all frequency range. At high frequency range, there's still some discrepancy. This is not theoretical. This is due to numerical resolution. We cannot use infinite number of layers to simulate our moon, okay? So at least we have a consistent understanding of how the moon should respond to gravitational wave. But looks like the transfer function is decreasing. Does this mean we lose sensitivity to gravitational waves? Not so fast, jump to your conclusions. In our model, or mostly any other group's model, we all assume that this so-called heterogeneous sphere model for the moon. So it's a bunch of layers. In each layer, you have homogeneous property, like the velocity of the seismic wave and the density, etc. So with this simple model, if you ask how my seismic wave would develop, the seismic wave is always very, very short. It will be damped very quickly. But that's not a reality. Don't forget, Apollo has sent back some data. And from the data, looks like the seismic wave is very, very long lasting. So something significant is missing in our simple model. And people think this is because the moon actually is not homogeneous. It's very fractured. There's a lot of these small rocks embedded in the moon. And these rocks basically scatters the seismic wave. A lot more energy actually is stored in the moon, which I think is very good for gravitational wave detection, because you do need the moon to amplify the gravitational waves, right? But this structure can no longer be modeled by our simple semi-analytical calculations before, so we have to go to numerics. So we have just started doing this finite element simulation to simulate this 2D moon, and what you are seeing here is the displacement of the moon when a gravitational wave passes by. And we're trying to generalize this model to a 3D to make it more realistic. Anyway, using our transfer function, and if we think of a real lunar seismometer design, and we can calculate the sensitivity. And this is a conceptual design of a lunar seismometer from our colleagues actually from Beijing Normal University. And this is an instrument noise. At high frequency, it's dominated by a readout noise, at low frequency dominated by thermal noise. And if you combine it with our transfer function, you get this sensitivity, okay? So 0.1 hertz is here, as I promised. It's if you use the old transfer function, if you use the old transfer function, people think lunar seismometers will be very sensitive to 0.1 hertz gravitational waves. And with such good sensitivity, you will be able to detect binary, say, intermediate mass black hole mergers up to a distance of about 20 gigaparsec. But that was when you use the old transfer function. Now, if we use a corrected transfer function, you see a significant decay of the sensitivity. You compare here and here, you see the sensitivity has dropped by orders of magnitude, but still very good. You can detect intermediate mass black holes up to a distance about 1 gigaparsec, a redshift of 0.2, 0.3. So we think it's still good. Again, that's not the end of the story yet, because if we use realistic moon models, maybe the sensitivities will be much better than what is shown here. Another way of there's some, it's just a conversion. But anyway, another way of using our transfer function is try to use it to predict the sensitivity of lunar seismometers to the stochastic gravitational wave background. In this case, you will have to combine two seismometers to do this kind of a correlation. So we considered two Chang'e seismometers, which is shown by this blue line, and the dotted line is kind of its average sensitivity. So orange one is a LGW, it's the European concept, okay, seismometer, and this is its a sensitivity. Some of you may spot that, okay, if you look at Chang'e, the constraint on the gravitational wave background is even higher than 1, okay? It's non-physical, so what's the point of studying it? Here's a point. This is basically the same plot, Chang'e here and the LGWE here. And overplotted here are all the previous experiments trying to measure stochastic gravitational wave background with all kinds of ideas, okay? Even if LGWA or LISA is very sensitive, but they will be launched in 10 years, if not more. Chang'e seismometer, we will have them in 2 years, and maybe in 4 years, we'll have 2 on the moon. So as long as they are properly working, we will immediately have so far the best constraint of gravitational wave background in this 0.1 Hertz range, okay? That's why we want to do this. Of course, over the years from 2028 to 2035, there will be a lot of more seismometers on the moon, so the constraint will be much better. So finally, I want to summarize by saying that gravitational wave at 0.1 Hertz is very useful for dark matter search. The lunar seismometers probably offer a potential solution to try to catch these kind of signals. The last picture, I want to advertise this small collaboration in China, try to study all kinds of concepts of building gravitational wave detectors on the moon. And including build interferometry in the crater. So this small collaboration is called Crater Interferometry Gravitational Wave Observatory. And one of the leading figure is sitting there, our organizer, Sichuan. If you are interested, you can ask her or you can talk to me. Thank you.
Okay, thank you to Chen Xian for this very interesting talk. Questions? We have time for at least 1 or 2.
Thank you for interesting talk. I have a very naive question about the background event for these seismometers. Do you have any possible background event like a core activity of the moons or something like that?
The moon is very, very quiet compared to the Earth or the Mars. The moon doesn't have atmosphere, so we don't have that background noise. The moon doesn't have any ocean, so there's no tidal kind of a background. From the Apollo missions, we know the moon is extremely quiet. So only seismic activity we know is excited by these mini meteoroids falling onto the moon. But that signal is very different from gravitational wave. Gravitational wave has this quadrupole structure, so you can easily use this character to pick up only gravitational wave signal.
Okay, thank you.
So I have 2 questions. The first is how you distinguish a stochastic gravitational wave background?
You have to have 2 seismometers and you use them to do correlation. As I mentioned, the moon is very quiet. So far, we don't know any other possible noise that can cause that kind of a signal.
That for coherent, I understand, but for stochastic, do you think there's some correlation? Because you don't have, you just have 1 signals, right? Which in principle cannot be distinguished from the noise.
But we have 2, hopefully. Actually, the idealist case is we have 5 seismometers. Then you can really break the degeneracy and try to constrain any parameters that is in the gravitation. Don't forget, gravitational wave still has this quadrupole structure. It's like PTA.
Yeah, but that we have different detector in principle.
Yeah, we can think of. But now we think of 2. But
this is just 1 because moon is the detector, and you are using this seismology.
No. Let me go back to hopefully the.
It's the Weber bar, right? Basically.
Look at this oscillation. Okay, it also has quadrupole structure. So you place seismometers at different places of the moon. You try to.
For coherent, I agree, but for stochastic, I'm not sure if that is. You can see this correlation.
That's still the case. Okay. That's still the case. Yes.
Another question is what's the advantage compared to other this project, for example, atomic interferometry and the BBO and also the interferometry on the moon?
I think the advantage is that the projects are there. Chang'e project, China has it, and the technique is not too difficult. Currently the seismometers on the Earth already has a sensitivity if it can be transported to the moon to use. But unfortunately, that's not the case. The Earth seismometer cannot withstand the vibration during the launch. the very low temperature at the surface of the moon can basically spoil the electronics. So we need a new design, basically. But to me, there's no barrier in technology.
Okay, thank you.
Okay, maybe one last quick question, if anyone. Okay.
Very impressive, sir. May I ask a question? What's the relationship between the mass of the moon, the radius of the moon, and the frequency of the gravitational wave?
Yeah. The moon only amplifies a certain frequency of gravitational, as is shown here. The response of the moon is frequency dependent. Because there's some resonant frequency in the moon. So if the gravitational happen to be at that resonant frequency, it's very good. It resonantly excites the moon. That answers your question about the frequency dependence. The structure of the moon, we have some data, actually, using Apollo data as well as using some remote sensors. Those geophysicists actually has roughly some idea of what the moon structure should be. That's also the motivation that they want to build a more sensitive seismometer, place them on the moon to measure more accurately the structure of the moon. So the model will get better as the measurement is carry on.
Thank you so much.
Okay, great. So if anyone else has other, okay, you're the organizer, so you can ask.
Well, thank you. I know everyone wants to go home now, probably. We have a dinner box outside. So which software you used for the simulation?
For the semi-LNG, for these ones, we use a standard software called the Minios, which do kind of the normal mode decomposition of basically any body. Okay, that's a very commonly used in the geophysics community. For the finite element simulation, we are relying on our collaborators in CAS. Actually, they have this they have developed this code when they were studying Earth seismic activities.
So okay, another question: Does moon has this like I love dark Q relation?
Of course. Moon also has a tidal kind of number. I have no idea how large or how small it is, or whether it will be important for gravitational activity. I have no idea.
I think it might be interesting to study the relation between the large Q number and the gravitational wave response, because that's a quadrupole tidal thing.
It certainly has a quality factor Q. The Q people think is around maybe 600, several thousand. That's which is important because it kind of determines what this peak is, how high this peak is. The quality factor.
Okay, great. So I think that's all we have time for today. So let's thank all the speakers from this session again. And now we can have dinner.
请注册的时候登记需要晚餐的老师和同学们在中午茶歇处领取盒饭，谢谢。